The universe is an immense expanse, a realm where wonders and mysteries stretch far beyond our comprehension. From the infinitesimal particles to the massive galaxies, it encompasses a scale we can barely begin to grasp. With billions of galaxies, each teeming with millions or even billions of stars, the cosmos is an endless source of intrigue. These stars, accompanied by their orbiting planets, create solar systems that glide through the vast emptiness of space. But how did all this come to be? Join us as we embark on an extraordinary journey through the cosmos, diving deep into the heart of space's most fascinating secrets. We begin with our very own solar system, anchored by the Sun, our medium-sized yellow dwarf star. This brilliant ball of burning gas is at the core of life on Earth, exerting influence on everything around us. About 93 million miles away, the Sun radiates energy through the process of nuclear fusion. In the heart of the Sun, hydrogen atoms collide and fuse to form helium, releasing an enormous amount of energy in the form of light and heat. This constant supply of energy is the foundation for life on Earth. Plants capture sunlight through photosynthesis, converting it into chemical energy and producing oxygen, a critical component for most living organisms. Without the Sun's steady flow of energy, Earth would be a frozen wasteland, its oceans solid and its atmosphere lifeless. The Sun's gravitational pull also keeps our solar system in balance, holding Earth and the other planets in their orbits and preventing them from wandering into the cold void of space. The Earth's journey around the Sun, completing one orbit each year, creates the seasons. These natural cycles dictate everything from plant growth to animal behavior and even agricultural practices. But that's not all. The Sun sends a continuous stream of charged particles, known as solar wind, sweeping across the solar system. As these particles interact with Earth's magnetic field, they give rise to the awe-inspiring auroras, painting the skies with stunning colors. The Sun is not merely a glowing sphere in the sky. It is a powerful, life-sustaining force intricately linked to the rhythm of life on Earth. Looking deeper into the origins of our solar system, we must travel back more than 4.5 billion years. It all began in a vast molecular cloud, a cold, dense region of gas and dust made mostly of hydrogen and helium. This cloud was part of a larger nebula, a stellar nursery where stars and planetary systems are born. Then something remarkable happened. A disturbance, possibly from the shockwave of a nearby supernova, triggered the collapse of a section of this molecular cloud under its own gravity. As it collapsed, it began to spin, and at the center, a protostar was born, destined to become our Sun. As the cloud continued its collapse, it flattened into a rotating disk called a protoplanetary disk. Within this disk, dust particles began to collide and stick together, slowly forming larger and larger clumps in a process called accretion. These clumps, known as planetesimals, became the building blocks of the planets. Over millions of years, these planetesimals grew into protoplanets, which continued to accumulate material through gravitational attraction. In the inner regions of the disk, where temperatures were high, only metallic and rocky materials could condense. This is where the terrestrial planets like Earth and Mars took shape. Further out in the cooler regions, gas giants like Jupiter and Saturn began to form, primarily from hydrogen and helium. Beyond these behemoths, icy bodies and comets emerged, creating a fascinating outer realm of frozen worlds. What began as a swirling cloud of gas and dust gradually morphed into the intricate and diverse solar system we know today. Each planet in this cosmic family carries its own set of unique characteristics, contributing to the spectacular tapestry of our celestial neighborhood. From the birth of stars to the formation of planets, the universe's transformative processes are a testament to the grandeur and complexity of creation. The cosmos continues to evolve, with every discovery revealing new layers of wonder. Through it all, our solar system stands as a remarkable example of the beauty and power of the universe's unfolding story. Starting with Mercury, the closest planet to the Sun, it is a small rocky body that experiences the most extreme temperature fluctuations in the solar system. During the day, temperatures soar to nearly 800 degrees Fahrenheit, while at night they plummet to a frigid -330 degrees Fahrenheit. Without an atmosphere to moderate these shifts, Mercury's surface is heavily cratered, much like our moon, a reminder of its geologically inactive state. Venus, often called Earth's sister planet because of its similar size and structure, presents an entirely different set of challenges. Shrouded in thick clouds of sulfuric acid, Venus has surface temperatures that hover around 900 °F, making it the hottest planet in our solar system. This extreme heat is caused by a runaway greenhouse effect, where the dense carbon dioxide atmosphere traps more heat than is released. Venus has a curious feature. It rotates in the opposite direction of most planets, causing the sun to rise in the west and set in the east. Then there's Earth, our unique home. What sets Earth apart is its liquid water and abundant life, supported by a balanced climate system. The combination of oceans, an atmosphere rich in nitrogen and oxygen, and a protective magnetic field creates an environment conducive to sustaining life. Mars, the red planet, is a world of contrasts. Though barren today, it once featured rivers, lakes, and possibly oceans. Now it is a cold desert with vast polar ice caps. Mars hosts the tallest volcano in the solar system, Olympus Mons, and a canyon system, Valles Marineris, that dwarfs Earth's Grand Canyon. These remarkable features suggest a history shaped by immense geological forces. Jupiter, the gas giant, is the largest planet in our solar system. Comprised mainly of hydrogen and helium, its most iconic feature is the Great Red Spot, a colossal storm larger than Earth, raging for centuries. This immense storm, along with Jupiter's many moons, including the volcanic Io and icy Europa, makes it a fascinating subject for exploration. Saturn, known for its spectacular ring system, is another gas giant. The rings, composed of ice and rock particles, create an awe-inspiring sight, though the planet itself is also a giant of gas and hydrogen. Saturn's moons, like Titan, with its thick nitrogen-rich atmosphere, add complexity to our understanding of this distant world. Uranus, the seventh planet from the Sun, stands out due to its extreme axial tilt. Unlike most planets, Uranus rotates on its side, which creates seasons unlike any other planet in the solar system. Its faint ring system and blue-green color due to methane in its atmosphere add to its mystery. Neptune, the outermost planet, has some of the fastest winds in the solar system, reaching speeds over 1,200 miles per hour. The deep blue color of Neptune is also caused by methane, but it's the storm systems, such as the Great Dark Spot, that make this planet particularly intriguing. Lastly, the dwarf planet Pluto, though reclassified, remains a compelling subject for astronomers. With its icy surface and heart-shaped glacier, it continues to captivate. Despite its small size, Pluto has 5 known moons, including the large Charon, which suggests that there's still much to discover in our distant solar system. The solar system is a vast and varied collection of worlds, each one unique in its composition, environment, and history. The inner rocky planets, Mercury, Venus, Earth, and Mars, are small, dense, and have solid, well-defined surfaces. These planets also possess thin atmospheres, if any, with Earth sustaining life and Venus's creating a hellish environment due to a thick layer of toxic gases. Meanwhile, the outer gas giants, Jupiter, Saturn, Uranus, and Neptune, are massive, made up primarily of hydrogen, helium, and frozen gases. These planets lack solid surfaces and feature immense atmospheres, with Jupiter and Saturn boasting enormous magnetic fields and an impressive number of moons, and Saturn's famous rings. The classification of Uranus and Neptune as ice giants emphasizes their composition, rich in frozen water, ammonia, and methane. These giants, especially Uranus with its sideways rotation, offer a glimpse into the diverse range of conditions that can exist in our cosmic neighborhood. While the inner planets tell a story of solid ground and active geology, the outer gas and ice giants reveal the wonders of vast gaseous atmospheres, extreme weather systems, and unique features that make our solar system an endlessly fascinating place to explore. The diversity of planetary formation is nothing short of captivating. The moons of our solar system stand as extraordinary witnesses to the vast array of celestial bodies, each offering unique characteristics that reveal the underlying complexity of our cosmic neighborhood. From icy oceans to fiery volcanoes, these moons have become key to our understanding of the conditions that define a planetary system. Europa, one of Jupiter's Galilean moons, commands attention not only for its striking appearance, but for its potential to harbor life. Beneath its frozen crust, scientists believe a subsurface ocean exists, sustained by tidal heating caused by Jupiter's immense gravitational pull. This ocean may contain more water than all of Earth's oceans combined. The possibility that life could thrive in this deep, dark water raises profound questions in the field of astrobiology. Could Europa be a cradle for extraterrestrial life? In stark contrast, Io, another of Jupiter's moons, is an active and violent world, home to the most intense volcanic activity observed anywhere in the solar system. Eruptions on Io are so powerful they eject plumes of sulfur and sulfur dioxide hundreds of miles into space. Its surface is constantly reshaped by volcanic forces, with sulfuric lavas flowing across vast plains and massive calderas created by the gravitational tug-of-war between Jupiter and its fellow Galilean moons. The ever-changing landscape of Io provides a dynamic insight into planetary geology and the forces that sculpt celestial bodies. Then there is Ganymede, the largest moon in the solar system, even surpassing the size of the planet Mercury. Ganymede is unique in its possession of a magnetic field, a characteristic not seen in any other moon. This magnetic field suggests that the moon's core contains a partially liquid iron-nickel core, similar to Earth's, and may be responsible for the spectacular auroras visible at its poles. Ganymede's auroras, influenced by Jupiter's magnetic environment, provide a fascinating glimpse into how magnetic fields interact with a celestial body in deep space. Saturn's moon Titan is another standout in the quest to understand our solar system. With an atmosphere dense in nitrogen, Titan's thick orange smog resembles that of early Earth, shrouding its surface and hiding a world filled with methane and ethane lakes, rivers, and seas. Beneath this thick atmosphere lies a complex and alien landscape, one that includes a suspected subsurface ocean composed of water and ammonia. Titan stands at the forefront of astrobiological interest, providing a rich environment that could one day reveal clues about the origins of life and the chemical processes that preceded it. Enceladus, another of Saturn's moons, continues to captivate the scientific community with its extraordinary geysers that shoot plumes of water vapor, ice particles, and organic compounds into space. These geysers, originating from the moon's south pole, point to a subsurface ocean beneath the icy crust. The material ejected by these geysers contributes to Saturn's E-ring, and studying these particles offers a unique opportunity to explore the potential for microbial life in an environment far beyond Earth. Enceladus has become a prime target for missions seeking to understand the possibilities of extraterrestrial life. In the distant reaches of the solar system lies Neptune's moon Triton, whose retrograde orbit suggests that it was likely captured by Neptune's gravity rather than forming in place. Triton's surface is a frozen, reflective mix of water and nitrogen ice, with strange, cantaloupe-like terrain that continues to puzzle scientists. The moon also exhibits geysers that spew nitrogen gas, further pointing to subterranean activity. Triton's retrograde orbit, combined with these active surface features, makes it an intriguing object of study for understanding the dynamics of captured celestial bodies and the geological processes that may take place on such moons. Beyond the moons, the asteroid belt, located between Mars and Jupiter, plays a crucial and multifaceted role in shaping our solar system. This region is home to a vast array of rocky bodies, ranging from tiny dust particles to massive asteroids hundreds of miles across. The belt is composed of leftover planetesimals that never coalesced into a planet, likely due to the disruptive gravitational influence of Jupiter. It's estimated that the combined mass of all the objects in the asteroid belt is less than that of Earth's moon, yet its significance in planetary science cannot be understated. The asteroid belt serves as a cosmic dividing line between the inner, rocky planets and the outer gas giant worlds. Its origins trace back to the primordial solar nebula, and it continues to shape the evolution of the solar system. Occasionally, the gravitational pull of Jupiter can nudge asteroids out of their stable orbits, sending them careening toward the inner solar system. Such interactions have had profound impacts on Earth, with the most famous example being the asteroid impact that contributed to the extinction of the dinosaurs around 66 million years ago. The moons and bodies in our solar system provide invaluable insights into the formation and evolution of celestial bodies, as well as the conditions that might support life elsewhere in the universe. From icy oceans to volcanic landscapes, from mysterious atmospheres to distant orbits, these objects challenge our understanding of what is possible in the cosmos. Each moon, asteroid, and planet is a unique story in the grand narrative of our solar system, a testament to the incredible variety of astronomical bodies that exist within our reach. Rogue asteroids float through the vast expanse of space, offering us more than just fascinating celestial sights. These asteroids, often classified as rogue because of their unpredictable orbits, can serve as invaluable windows into the early solar system. When captured and studied, they reveal pristine material untouched by time, giving scientists the unique opportunity to examine the building blocks of our solar system's formation. The asteroid belt, often overlooked, is like a natural laboratory that holds secrets about planetary formation and differentiation. Massive asteroids like Ceres and Vesta stand out in this belt, offering us significant insights into geological processes that we thought were exclusive to the larger planets. Ceres, a dwarf planet, for instance, is not only a testament to the early solar system, but also contains signs of water ice and even cryovolcanism, which hints at potentially complex and active geological history. Vesta, in contrast, reveals a differentiated structure, similar to Earth, comprising a core, mantle, and crust, suggesting that it underwent internal melting in its distant past. But the asteroid belt's importance doesn't stop at offering scientific discoveries. It also holds potential resources that could change the course of human space exploration. Asteroids are rich in elements like iron, nickel, and even water, all locked in the form of ice. With the rise of space exploration and the idea of establishing long-term human colonies on other planets, asteroid mining becomes an exciting proposition. The notion of extracting these valuable materials directly from asteroids, rather than relying on Earth for supplies, could provide crucial resources for building spacecraft, life support systems, and even entire space stations, enabling us to reduce our reliance on Earth-based supplies for long-term space missions. Comets are often portrayed as the dirty snowballs of the solar system, and indeed, they have a multifaceted role far beyond their icy nature. These small celestial bodies, composed of dust, ice, and organic compounds, originate from the distant regions of our solar system, such as the Kuiper belt and the Oort cloud. As comets travel toward the sun, they undergo dramatic transformations, revealing critical information about the primordial conditions that existed when our solar system was in its infancy. The intense heat from the sun causes the ices in the comet to sublimate, releasing gases and dust that form a glowing coma around the nucleus, often accompanied by spectacular tails that stretch millions of miles into space. But comets are more than just dazzling light shows. They are ancient relics, almost unchanged since their formation over 4.6 billion years ago. They act as cosmic time capsules, preserving materials from the early solar system, giving scientists the ability to peer back in time. By studying the composition of these ancient bodies, researchers have uncovered clues about the solar nebula, the cloud of gas and dust that birthed the planets. Missions like the European Space Agency's Rosetta, which landed on the comet 67P Churyumov-Gerasimenko, have revolutionized our understanding of comets. The spacecraft provided unprecedented data, revealing complex organic molecules, possibly essential for life, shedding light on the early steps toward life's formation. Comets have also played a pivotal role in Earth's history. Some scientists hypothesize that comets were responsible for delivering water and organic molecules to the early Earth. These crucial compounds, potentially essential to the emergence of life, may have arrived via cometary impacts, as isotopic similarities between water found in comets and that on Earth suggest. Additionally, comets have influenced Earth's atmosphere and geological history in both catastrophic and beneficial ways. Their impacts might have triggered mass extinction events, yet they may have also sparked evolutionary leaps by altering Earth's chemistry. Their role in distributing vital ingredients across the solar system and their ongoing interaction with planetary bodies cannot be understated. The Kuiper belt and Oort cloud, regions far beyond Neptune, continue to redefine our understanding of the solar system's boundaries. The Kuiper belt, extending from about 30 to 50 astronomical units from the Sun, is home to thousands of small icy objects, including dwarf planets like Pluto, Haumea, and Makemake. Since the discovery of these objects in the late 20th century, our view of the solar system has expanded dramatically. These discoveries show us that the solar system is far more intricate and vast than we had previously imagined. The Kuiper belt helps define the transition zone between the inner solar system, where the gravitational influence of the major planets is felt most strongly, and the outer, more sparsely populated regions of space. Objects in this belt, known as Kuiper belt objects, KBOs, have likely remained relatively unchanged since the solar system's early days, preserving ancient material that offers insight into the processes that governed planetary formation. Beyond the Kuiper belt lies the Oort cloud, an even more distant and enigmatic region. Though no direct observations have been made due to its extreme distance, the Oort cloud is theorized to be the origin of long-period comets, which have orbits that last thousands to millions of years. Models suggest that the Oort cloud formed from the remnants of the primordial disk of gas and dust that once surrounded the early sun. The gravitational interactions of nearby stars and giant planets likely scattered these objects to far-reaching distances. Together, the Kuiper belt and Oort cloud serve as boundary markers of the solar system, providing clues about the sun's gravitational influence and its reach into the interstellar space. They also act as archives of our solar system's history, offering us glimpses into the processes that led to the formation of planets and the intricate dynamics between celestial bodies. Studying these regions not only helps define the outer limits of our solar system, but also sheds light on the formation of planetary systems across the galaxy. These far-flung regions of our solar system, along with the rogue asteroids and comets that pass through, reveal the untold stories of our solar system's creation, and in turn, the future of human space exploration and discovery. In the vast expanse of our solar system, Pluto's story remains one of the most fascinating chapters. Once heralded as the 9th planet, its reclassification as a dwarf planet in 2006 didn't dampen its allure. In fact, Pluto has only become more intriguing as we delve deeper into its enigmatic characteristics, offering valuable insights into the outer limits of our cosmic neighborhood. Its very existence challenges our understanding of planetary bodies, and its dynamic nature keeps scientists and the public captivated. Unlike many of the icy, seemingly lifeless bodies within the Kuiper belt, Pluto's geology defies expectations. The 2015 data from NASA's New Horizons mission shattered the notion of Pluto as a frozen, inert world. Instead, it revealed a surface full of contrasts: vast plains of nitrogen ice, towering mountains made of water ice, and signs of recent geological activity. Among the most notable features is the heart-shaped region known as Sputnik Planitia, which is believed to be a colossal, slowly convecting glacier of nitrogen ice. This formation sits in a massive basin, likely created by an ancient impact. This discovery alone has prompted scientists to reconsider the geological dynamics of dwarf planets, revealing that Pluto is anything but static. Adding to its mystery, Pluto's atmosphere is another remarkable facet. Though thin, it is composed mainly of nitrogen with traces of methane and carbon monoxide. Pluto's atmosphere is far from stable, as it experiences seasonal fluctuations driven by its highly elliptical orbit around the Sun. As Pluto nears the Sun, the ice on its surface sublimates, replenishing the atmosphere with gases that freeze back onto the surface as the planet moves farther away. This delicate dance between surface ice and atmospheric processes showcases the complexity of even the smallest, most distant worlds in our solar system. These changes aren't merely academic. They offer a glimpse into the processes that govern planetary atmospheres across the cosmos. Yet, Pluto's tale is not one of solitude. Its system of moons, including its largest moon, Charon, adds a new layer of intrigue. So substantial is Charon that the center of mass between Pluto and Charon lies outside Pluto's surface, making them a binary system rather than a planet-moon arrangement. This gravitational relationship results in tidal forces that influence both Pluto and Charon's geological features. Charon is home to its own geological wonders, such as a colossal canyon system and a mysterious, dark reddish region at its north pole, dubbed Mordor Macula. These features prompt scientists to consider how these celestial bodies interact and evolve together. Smaller moons like Styx, Nix, Kerberos, and Hydra also add complexity to the system. Their chaotic rotations are likely influenced by the gravitational intricacies of Pluto and Charon's relationship, hinting at the dynamic nature of the entire system. Astrobiologically, Pluto teases with the possibility of chemical processes that could shed light on the origins of life itself. While the harsh temperatures make it an unlikely candidate for harboring life as we know it, the organic molecules detected on its surface suggest that interactions between sunlight, cosmic rays, nitrogen, and methane could provide clues about prebiotic chemistry. This discovery is of profound interest, offering potential insights into the chemical building blocks of life in environments far colder and more distant than Earth. The continued study of Pluto underscores a key lesson. Complexity often arises in the most unexpected places. Its atmosphere, dynamic surface, and intriguing moons stand as a testament to the intricate and interconnected nature of planetary bodies. Through Pluto, we gain a richer understanding of the forces at play in the far reaches of our solar system, forces that govern not only the icy realms beyond Neptune, but also the fundamental processes of planetary evolution. As we move inward in our solar system, Mercury, the closest planet to the Sun, holds its own set of astonishing features that continue to captivate astronomers and space enthusiasts alike. Despite its proximity to the Sun, Mercury is a planet of extremes with no substantial atmosphere to retain heat. This absence of an insulating atmosphere leads to dramatic temperature fluctuations that define Mercury's surface. During the day, temperatures can soar to nearly 800 degrees Fahrenheit, while at night, the lack of heat retention causes temperatures to plummet to a bitter 330 degrees Fahrenheit. This stark contrast offers scientists a unique opportunity to study the effects of extreme heat and cold on planetary surfaces, providing a window into how other airless bodies in the solar system might behave under similar conditions. As the study of planets like Pluto and Mercury continues, our understanding of the solar system's inner and outer realms expands, pushing the boundaries of science and imagination. These distant and extreme worlds, though vastly different, remind us of the wonders that still await discovery. Mercury, the smallest planet in our solar system, holds many mysteries, especially regarding its geological history, which reveals evidence of a cataclysmic past. One of its most striking features is its heavily cratered surface, which closely resembles that of our moon. Among these craters is the Auroras Basin, a colossal impact crater spanning a staggering 960 miles in diameter. This basin is not only one of the largest in the solar system, but also a reminder of the violent collisions that have shaped Mercury over billions of years. Surrounding the Auroras Basin lies a terrain marked by chaotic features, which scientists believe were caused by shock waves from the impact that formed the basin. These waves spread outward, distorting the surface in complex patterns, further enhancing Mercury's tumultuous history. Mercury's surface is not only defined by its craters, but also by vast smooth plains, believed to be the remnants of ancient volcanic fields. These plains stand in sharp contrast to the planet's enormous cliffs or scarps, some of which stretch for hundreds of miles. These scarps rise over a mile above the surrounding terrain, creating dramatic ridges across the planet. The scarps are thought to have formed as Mercury cooled and contracted over billions of years, causing its crust to buckle and warp. The geological diversity of the planet gives scientists a unique window into the processes that have shaped the rocky planets in our solar system. At the heart of Mercury lies a massive iron-rich core, which extends about 85% of the planet's radius. This makes Mercury's core disproportionately large compared to other terrestrial planets. The core is not only a dominant feature in Mercury's internal structure, but also a source of its magnetic field, which, though only 1% as strong as Earth's, provides crucial insights into the planet's thermal evolution. The fact that Mercury has a magnetic field suggests that its core is at least partially molten, a phenomenon that is essential to understanding planetary magnetism and the thermal evolution of rocky planets. Despite its proximity to Earth, Mercury remains a somewhat elusive planet, primarily due to its close orbit around the Sun. The intense solar radiation makes it challenging to observe with ground-based telescopes. However, NASA's Messenger mission, which orbited Mercury from 2011 to 2015, provided groundbreaking data that has significantly expanded our knowledge of the planet. One of the most surprising discoveries from Messenger was the presence of water ice in permanently shadowed craters near Mercury's poles. These craters, shielded from the sun's rays, harbor ice deposits, suggesting that Mercury, despite its scorching proximity to the Sun, may have received icy materials delivered by comets or asteroids. This discovery challenges previous assumptions about the planet's environment and opens up new avenues for research. Mercury's peculiar orbital characteristics only add to its intrigue. It has an elliptical orbit and completes one full orbit around the Sun in just 88 Earth days. Yet, due to its 3/2 spin-orbit resonance, Mercury rotates 3 times on its axis for every 2 orbits it completes around the Sun. This results in a highly unusual day-night cycle where one solar day on Mercury, defined as the period from one sunrise to the next, lasts about 176 Earth days. This extended day length, combined with extreme temperature variations, makes Mercury a unique and challenging environment for scientists to study. With its extreme temperature fluctuations, vast volcanic plains, towering scarps, and large iron core, Mercury stands as a planet of fascinating extremes. The discovery of water ice and shadowed craters adds a layer of complexity to our understanding of this world, while its strange orbital dynamics continue to intrigue researchers. As scientists delve deeper into the mysteries of Mercury, they uncover new insights not only about the planet itself, but also about the formation and evolution of our solar system as a whole. On the other hand, Venus, often referred to as Earth's sister planet, presents an entirely different set of challenges. Venus is the hottest planet in our solar system, with surface temperatures high enough to melt lead. The reason for this extreme heat lies in the planet's runaway greenhouse effect. Venus's thick atmosphere is composed mainly of carbon dioxide, about 96%, and dense clouds of sulfuric acid, both of which play a critical role in trapping heat. The greenhouse effect on Venus begins when solar radiation reaches the planet's surface. Once absorbed, this energy is re-emitted as infrared radiation, or heat. On Earth, some of this heat escapes back into space, but on Venus, the dense carbon dioxide atmosphere acts as a blanket, trapping the heat and preventing it from escaping. This creates a vicious cycle. As the atmosphere warms, it retains even more heat, causing the temperature to climb even higher. The result is an environment that is both extreme and inhospitable, making Venus a stark contrast to Mercury, despite both planets being relatively close to the Sun. The intense heat and toxic atmosphere make Venus a challenging subject for exploration, but the study of its atmosphere continues to offer vital lessons about the dynamics of planetary climate systems. As a result, Venus's average surface temperature rises to around 900 degrees Fahrenheit, surpassing even Mercury, which is much closer to the Sun. Yet, Mercury lacks the thick, heat-trapping atmosphere that makes Venus a true planetary oven. The extreme atmospheric pressure on Venus, about 92 times that of Earth at sea level, compounds the situation. This intense pressure forces the atmosphere to retain more heat, amplifying the already fierce greenhouse effect. But the real kicker lies in Venus's sulfuric acid clouds. These clouds reflect sunlight light, preventing the surface from cooling down by radiative loss. This reflective layer not only scatters sunlight, but also diffuses visible light, ensuring that the heat gets dispersed evenly throughout the atmosphere, maintaining a constant, blistering temperature. What makes Venus particularly intriguing is its stark warning of the catastrophic power of greenhouse gases. Scientists believe that in the distant past, Venus may have enjoyed a more temperate climate, potentially even hosting liquid water on its surface. However, as solar radiation increased over millennia, it likely led to the evaporation of water. This released massive amounts of water vapor, another potent greenhouse gas, further exacerbating the warming. The relentless cycle of evaporation and warming gradually transformed Venus into the searing inferno we observe today. Venus's extreme heat is due to its thick atmosphere, rich in carbon dioxide, which produces a relentless, self-perpetuating greenhouse effect. Understanding this process doesn't just reveal the conditions on Venus, it provides a crucial lesson in how greenhouse gases can radically change planetary climates, underlining the delicate balance necessary to sustain life on planets like Earth. Mars, often dubbed the Red Planet, boasts an array of remarkable geological features that capture both the scientific imagination and our desire to understand its history. The most iconic of these is Olympus Mons, the tallest volcano in the entire solar system, towering at an astonishing height of 13.6 miles Olympus Mons is nearly 3 times the height of Mount Everest. This massive shield volcano, similar in structure to the Hawaiian Islands volcanoes, is unparalleled in scale. Another striking feature of Mars is Valles Marineris, an immense canyon system that stretches over 2,500 miles long and plunges to depths of up to 4 miles. This colossal rift, which dwarfs Earth's Grand Canyon, likely formed through a combination of tectonic forces and surface collapse due to the pulling apart of Mars's crust. The Valles Marineris offers invaluable insights into the tectonic forces that shaped Mars's surface, revealing a complex history of crustal movement and possible volcanic activity. Mars's geological features continue to fascinate scientists. Among the most intriguing are the traces of ancient water flows, evidence that liquid water once coursed across the Martian surface. Outflow channels and valley networks, such as Ares Vallis and Ma'adim Vallis, suggest that catastrophic floods once carved deep, winding paths. Meanwhile, valleys like Naneti Vallis hint at sustained water flow in Mars's distant past. These ancient watercourses fuel ongoing speculation about the potential for past life on Mars. The planet's surface is also dotted with extensive plains, vast dune fields, and polar ice caps, all of which grow and recede with the changing seasons. The northern plains, such as Vastitas Borealis, are believed to be remnants of ancient ocean beds, while the heavily cratered highlands of the southern hemisphere offer further evidence of Mars's violent geological history. Mars's polar regions present another fascinating puzzle. Comprised of layers of water ice and carbon dioxide ice, dry ice, these caps vary in thickness with each seasonal cycle. These ice caps offer direct evidence of Mars's climate change over geological timescales. Additionally, the presence of chaotic terrain, areas where large blocks of rock are scattered in seemingly random orientations, adds another layer of intrigue. This chaotic landscape likely formed from underground collapses, possibly caused by the melting of subsurface ice. These geological phenomena not only make Mars an exciting subject of scientific study, but they also provide essential clues to the planet's climatic history, its volcanic and surface processes, and the ongoing search for potential signs of habitability. Each discovery, from towering volcanoes to ancient river valleys and mysterious chaotic terrains, enriches our understanding of Mars and its potential to have supported life, shaping the broader narrative of solar system exploration. The unveiling of these features not only fuels our curiosity, but also adds a layer of complexity to our comprehension of the red planet. As scientists continue to peel back the layers of Mars, we inch closer to uncovering its secrets, and with it, the possibility that life may have once thrived on this distant world. Each new finding on Mars brings us closer to answering age-old questions about the existence of life beyond Earth. Jupiter's atmosphere, a swirling cauldron of hydrogen, helium, ammonia, and other trace gases, is the birthplace of its iconic Great Red Spot, an immense, persistent anticyclonic storm. This storm, which has raged for at least 350 years and possibly much longer, serves as a striking testament to the dynamic processes at play in Jupiter's turbulent atmosphere. Its origins and longevity are intricately tied to the planet's unique atmospheric conditions. Jupiter's rapid rotation, completing one full rotation every 10 hours, generates powerful east-west jet streams that carve out distinct bands of clouds circling the planet. These bands, known as zones and belts, move at varying speeds and in opposite directions, creating shear zones where gases violently clash against one another. The Great Red Spot resides within one of these shear zones, specifically between a westward-moving belt and an eastward-moving zone, fostering the storm's rotation. The storm itself is an anticyclone, meaning it rotates counterclockwise in the southern hemisphere, and its core is characterized by high pressure. Unlike cyclones on Earth, which generally weaken over time, Jupiter's Great Red Spot is fueled by constant energy from the planet's internal heat. Jupiter radiates more heat than it receives from the Sun, and this internal energy powers the convection currents that drive the planet's banded wind patterns and storms, feeding the Great Red Spot and contributing to its astonishing longevity. In addition, the storm's roots extend deep into the atmosphere, possibly as deep as 200 miles below the cloud tops, which further enhances its stability. The storm's distinctive red color remains a mystery, but it is believed to be caused by complex chemical reactions driven by solar ultraviolet radiation and Jupiter's atmospheric conditions. Compounds such as ammonium hydrosulfide, possibly mixed with phosphorus or sulfur, are thought to contribute to the reddish hues. These compounds undergo reactions in the turbulent, high-energy environment of Jupiter's upper atmosphere, giving the storm its iconic appearance. The intensity of the red color varies over time, suggesting changes in the chemical composition or internal dynamics of the storm itself. In addition to its color and longevity, the Great Red Spot is of monumental size. Initially, it spanned over 25,000 miles across, large enough to encompass 3 Earths side by side. However, in recent decades, it has been shrinking and is now approximately 10,000 miles in diameter. Despite this reduction in size, the Great Red Spot remains the largest known storm in the solar system. Its sheer scale and ability to endure for centuries continue to astound scientists and make it one of the most intriguing features in our exploration of the outer solar system. Saturn's rings are one of the most stunning and distinctive features in our solar system, setting the planet apart with their immense size, brightness, and complexity. Unlike the ring systems of other gas giants, such as Jupiter, Uranus, and Neptune, Saturn's rings are extraordinarily prominent and easily visible even with small telescopes. These rings are composed primarily of countless particles of ice and rock, ranging in size from tiny grains to large boulders. One remarkable aspect of Saturn's rings is their sheer scale and intricate structure. The rings extend up to 175,000 miles from the planet's equator, yet are astonishingly thin, with a thickness that ranges from about 30 feet to several hundred feet. Despite their enormous size, these rings are far thinner than they are wide, creating an almost ethereal appearance. The rings are divided into 7 primary sections, labeled A through G in order of their discovery, with the A, B, and C rings being the most prominent. These bands are separated by gaps, such as the Cassini division, a 2,920-mile wide space between the A and B rings, where fewer particles reside due to gravitational interactions with Saturn's moons. Another feature that sets Saturn's rings apart is their vivid brightness. Composed largely of water ice, the rings reflect sunlight efficiently, giving them their luminescent appearance when viewed from Earth. The high albedo reflectivity of the ice particles contributes to their brilliant, almost ethereal look, making Saturn's rings one of the most breathtaking sights in the cosmos. Their shimmering presence, visible even with the aid of small telescopes, continues to capture the imagination of astronomers and stargazers alike, adding to the mystique of this majestic planet. In stark contrast to the less prominent and darker ring systems of other gas giants, Saturn's rings exhibit an awe-inspiring dynamism and complexity. The planet's majestic rings, which stretch out over vast distances, are not static. They are constantly changing and evolving in fascinating ways. This is due in part to the gravitational interactions between Saturn and its myriad moons, over 80 in total. These moons cause a range of effects, from the creation of delicate ringlets to the formation of distinct gaps and waves that ripple through the rings like undulating water. These interactions shape and mold the structure of Saturn's rings, making them a unique feature in our solar system. Small moons, often referred to as shepherd moons, play a vital role in this dynamic system. One example is Prometheus and Pandora, 2 of Saturn's smaller moons that shepherd the F ring. Their gravitational influence works to keep the particles in the ring corralled, preventing them from scattering too far and maintaining the narrow, braided structure that is a hallmark of the F ring. As these moons interact with the ring particles, they generate extraordinary phenomena, such as spiral density waves and bending waves that propagate through the rings. These waves, traveling across the particles, offer an incredible glimpse into the physical principles that govern not only Saturn's rings, but also broader disk systems throughout the universe, from planetary rings to the protoplanetary disks around stars. Adding another layer of intrigue to Saturn's rings are the seasonal changes caused by its axial tilt of approximately 27 degrees. As Saturn completes its orbit around the Sun, which takes nearly 30 Earth years, the angle at which sunlight illuminates the rings shifts. This results in alternating periods of brilliant, dazzling illumination and phases of near invisibility. These changing perspectives provide scientists with the opportunity to study the composition, structure, and dynamics of the rings from different angles, revealing new details that were previously hidden in the shadows. The origin of Saturn's rings is equally mysterious, adding to their allure. While the precise mechanism behind their formation is still uncertain, several leading hypotheses suggest they are relatively young. One theory posits that the rings were formed from the disintegration of a comet that came too close to Saturn, while another suggests the breakup of an icy moon or the remnants of a primordial disk from which Saturn itself was formed. Regardless of their origins, these theories all point to the rings being less than 100 million years old, which makes them a transient feature on geological timescales. This short lifespan adds a sense of urgency to their study, as they are likely to disappear long before humanity can fully understand them. Saturn's rings captivate the imagination not only for their massive scale and breathtaking brightness, but also for their intricate patterns and dynamic behaviors. The gravitational interactions with the planet's moons and the ongoing mystery surrounding their origin make Saturn's rings the most scientifically intriguing ring system in our solar system. The study of these rings continues to deepen our understanding of planetary dynamics, the history of the Saturnian system, and the larger processes that shape disk systems in space. Each discovery about Saturn's rings unveils new questions and inspires further exploration of the mysterious worlds that lie within our reach. Now imagine a planet spinning almost on its side, as if a cosmic hand reached out and flicked it like a top. This is Uranus, the seventh planet from the Sun, and it is unlike any other planet in our solar system. With an axial tilt of 98 degrees, Uranus is tipped almost entirely onto its side by creating the most extreme seasons of any planet we know. Unlike Earth, which has an axial tilt of roughly 23.5 degrees, Uranus experiences seasons that are both dramatically long and wildly unpredictable. For around 42 Earth years, one of its poles is plunged into perpetual darkness and freezing temperatures, while the opposite pole basks in continuous daylight. During the planet's orbit around the Sun, which spans 84 Earth years, the poles gradually switch places, leading to a staggering reversal between long, dark winters and unrelenting sunshine. The cause of Uranus's extreme axial tilt is still a matter of scientific debate, but one prevailing hypothesis suggests that a colossal collision with an Earth-sized object early in the planet's history may have knocked it over. This impact, a cataclysmic event in Uranus's early years, could have caused the planet to lose its original upright orientation, leaving it with its bizarre tilt. As a result, the planet's atmosphere experiences drastic shifts in temperature and pressure, leading to the most extreme and erratic weather patterns in the solar system. These changes could stir winds that reach supersonic speeds, while creating dense, complex cloud formations visible even from telescopes on Earth. The bizarre seasons and atmospheric dynamics of Uranus make it an exciting subject of study for both amateur astronomers and seasoned planetary scientists alike. As the planet continues to intrigue and puzzle researchers, our understanding of its strange weather, its violent history, and its enigmatic tilt promises to expand, shedding light on the mysteries of this distant world. Neptune, the eighth and most distant planet in our solar system, stands as a striking testament to the vastness and mystery of the cosmos. With its deep blue hue and swirling atmospheric phenomena, Neptune is home to some of the most extraordinary weather patterns ever observed. Winds on this distant world can reach supersonic speeds of up to 1,300 miles per hour, far surpassing the fiercest hurricanes or typhoons on Earth. These winds, which swirl with tremendous force, create a celestial ballet of gas and cloud formations that is as captivating as it is mysterious. The force and speed of these winds on Neptune defy conventional understanding, leaving scientists with numerous questions about how such dynamics can exist in a world so far removed from the warmth of the Sun. Despite its staggering distance from the Sun and its icy, inhospitable temperature of around -373 degrees Fahrenheit, Neptune's atmosphere harbors these relentless storms. It's hard to imagine how such violent weather systems could thrive in the cold darkness of space, but there is a theory that suggests Neptune's internal heat might hold the key. This heat is surprisingly high, considering the planet's remote location, and it could be responsible for driving the extreme weather. Neptune is believed to radiate more than twice the energy it receives from the Sun, which implies the existence of an internal heat source. One leading hypothesis points to the slow gravitational compression of Neptune's fluid interior as the culprit. This process might create convection currents within the planet's atmosphere, sparking massive temperature differentials that fuel the storms and supercharged winds. The intensity of these storms raises another profound question. How do they remain so powerful without quickly dissipating? The Great Dark Spot, a massive storm similar to Jupiter's Great Red Spot, provides a prime example of Neptune's turbulent weather systems. These phenomena, as fascinating as they are perplexing, continue to draw the curiosity of scientists eager to understand the forces at play in one of our solar system's most volatile atmospheres. Beyond our solar system, another realm of mystery awaits. As astronomers peer deeper into space, they turn their attention to exoplanets, planets orbiting distant stars light years away from Earth. One of the most prominent methods used to detect these exoplanets is the transit method. This technique takes advantage of a subtle phenomenon. When a planet passes in front of its star, it causes a minuscule dip in the star's light. This dimming, though slight, occurs at regular intervals, signaling the presence of an exoplanet. By carefully monitoring the brightness of numerous stars at once, observatories like NASA's Kepler Space Telescope have made remarkable discoveries, unveiling thousands of exoplanets. Yet another approach, the radial velocity method, or wobble method, adds another layer of insight. This method observes the star's movement caused by the gravitational pull of an orbiting planet. The star's slight wobble induces shifts in its light spectrum, which can be observed as alternating blue and red shifts, a direct result of the Doppler effect. These subtle changes allow astronomers to calculate the mass of the planet and its distance from its star. Even more groundbreaking is the direct imaging method. While the brilliance of a star can often overwhelm the faint light of a planet, advanced techniques like coronagraphy, which blocks out the star's light, have enabled astronomers to capture the faint glow of distant exoplanets. These methods, though challenging, have led to breakthroughs, allowing scientists to infer a wealth of information about the size, composition, and even the atmospheric conditions of these faraway worlds. Together, these tools offer a more complete and nuanced understanding of the universe, revealing a rich tapestry of celestial bodies and helping to answer some of humanity's most profound questions. With each new discovery, the mysteries of the cosmos unfold, bringing us one step closer to understanding the potential for life and the sheer diversity of planetary systems that lie beyond our own. The universe, it seems, is far from predictable, but its vastness and complexity continue to captivate our imaginations and fuel our quest for knowledge. Delving deep into the systems throughout the vastness of the galaxy, we turn our focus to the heart of our very own solar system, the Sun. A celestial powerhouse, the Sun is made up of several distinct layers, each playing a crucial role in sustaining its energy and shape. At the core of the Sun lies its engine, the powerhouse, where the temperatures soar to around 15 million degrees Celsius. Here, nuclear fusion takes place, an extraordinary process where hydrogen atoms fuse to form helium, releasing an immense amount of energy in the form of light and heat. This energy, however, doesn't make its way to the surface instantly. It embarks on a journey that can last thousands to millions of years, gradually making its way through the Sun's various layers. Moving outward, we first encounter the radiative zone. Here, energy takes a slow, winding path, absorbed and re-emitted by atoms in a complex, zigzagging motion. This process, though incredibly slow, ensures the energy is transferred outward, inching its way towards the Sun's surface. As we move further out, we reach the convective zone. In this region, the temperature drops enough for energy to be transported by convection currents. Hot plasma rises towards the surface, cools, and sinks back down, only to be reheated again. This creates a turbulent boiling environment, similar to the bubbling of soup on a stove. The convective zone is the engine driving the Sun's dynamic activity, giving it the boiling, churning effect we observe from Earth. Above the convective zone lies the Sun's visible surface, the photosphere. This layer, with temperatures of around 5,500 degrees Celsius, is where sunlight radiates into space, casting its life-giving energy throughout the solar system. Here, we can also observe sunspots, cooler, magnetically active regions on the sun's surface that reveal the sun's magnetic activity. Above the photosphere lies the chromosphere, a layer that can be seen during a solar eclipse as a reddish glow. Beyond the chromosphere, we reach the sun's outermost layer, the corona. Despite being farther from the sun's core, the corona is surprisingly hotter than the layers beneath it, reaching temperatures in the millions of degrees Celsius. This mystery has puzzled scientists for years, as it defies expectations. The corona is also the origin of the solar wind, streams of charged particles that influence space weather and have a significant impact on planets, including Earth. Every layer of the sun, from its intensely energetic core to the outer corona, plays a vital role in sustaining the sun's radiant glow and in shaping the solar system's dynamic processes. But at the heart of it all is the process of nuclear fusion, a monumental force that powers the sun. In the core, where temperatures reach a blistering 15 million degrees Celsius and pressures are unimaginably high, hydrogen nuclei overcome their mutual repulsive forces. These nuclei, composed of protons, collide with enough force to fuse together, forming helium nuclei in a series of steps known as the proton-proton chain reaction. During this process, a tiny fraction of the hydrogen mass is converted into energy, as described by Einstein's famous equation, E equals mc squared. The energy generated in the sun's core then moves outward, first passing through the radiative zone as photons bounce between particles, slowly inching their way toward the surface over thousands to millions of years. When the energy reaches the convective zone, it is transported by turbulent currents of hot plasma, rising and sinking in a boiling motion. Finally, the energy emerges from the sun's outer layers, manifesting as the sunlight we receive on Earth. This continuous process of nuclear fusion not only sustains the sun's radiant energy, but also plays a crucial role in the creation of heavier elements. As stars evolve, larger stars fuse heavier elements, contributing to the cosmic abundance of elements that are essential for life and the formation of planets. In this way, the sun is not merely a source of light and heat, but a dynamic and vital player in the cosmic dance of creation, its energy nourishing life across the solar system and providing the building blocks for the very elements we are made of. Thus, nuclear fusion at the sun's core is far more than just a process for energy generation. It is a fundamental cosmic engine that shapes the entire universe. Through the life cycles of stars, fusion serves as the driving force behind the birth and death of stellar bodies, influencing the evolution of galaxies and the formation of elements. This incredible process not only powers stars, but also sows the seeds for a universe rich with diverse elements, integral to the fabric of our existence. The stars, through fusion, become the very forges in which the elements that make up everything, planets, life, and matter, are crafted. Sunspots, the fascinating phenomena on the sun's photosphere, emerge as dark patches against its bright surface, characterized by their lower temperatures and intense magnetic activity. These spots are more than just peculiar blemishes on the sun's face. They are windows into the sun's complex inner workings. Some sunspots can span tens of thousands of kilometers, large enough to engulf the Earth several times over. They form when the sun's magnetic fields break through the surface, disrupting the sun's regular convective currents and leading to cooler regions. These areas, with temperatures around 4,000 degrees Celsius, are a stark contrast to the surrounding sun's surface, which reaches about 5,500 degrees Celsius. The magnetic turmoil surrounding sunspots also sparks dramatic solar events such as solar flares and coronal mass ejections, CMEs, which are both awe-inspiring and potentially hazardous. Solar flares, sudden bursts of intense radiation, are caused by the release of magnetic energy from sunspots, creating powerful flashes of light, radio waves, and high-energy particles. When these flares erupt, they accelerate protons and electrons to nearly the speed of light, contributing significantly to space weather. In contrast, CMEs are even more substantial, sending vast amounts of solar plasma into space. These massive eruptions of solar wind and charged particles can take anywhere from 1 to 3 days to reach Earth. As these charged particles approach Earth, they can interact with our planet's magnetosphere, triggering geomagnetic storms. These storms affect space weather in various ways, such as disrupting satellite operations, radio communications, GPS systems, and even power grids. The high-energy radiation from solar flares can damage satellite electronics, while the plasma from CMEs can induce electric currents in power lines, potentially causing widespread electrical outages. These storms are not just technological hazards, they are also responsible for the awe-inspiring auroras, the northern and southern lights. When the charged particles collide with gases in the Earth's upper atmosphere, they excite the molecules, causing them to emit light in spectacular displays of color. Understanding sunspots and their impact on space weather is vital in our increasingly technologically dependent world. Their study provides crucial insights that help mitigate potential impacts on modern infrastructure and emphasizes the intricate relationship between our planet and its star. Solar flares and CMEs, as two of the most powerful solar phenomena, can have both breathtaking and destructive consequences. Solar flares, which emit vast amounts of electromagnetic radiation, reach Earth in just 8 minutes. Their interaction with the Earth's atmosphere can disrupt communications and navigation systems, especially those used in aviation and maritime industries. Coronal mass ejections, on the other hand, send billions of tons of charged particles into space. When these particles collide with Earth's magnetosphere, they can create geomagnetic storms that induce electric currents in power grids, leading to outages and infrastructure damage, such as the infamous 1989 blackout in Quebec. The risks to satellites are significant too, as the particle radiation can degrade their electronic components, causing malfunctions or complete failures. Yet, even amidst the chaos, the sun's energetic outbursts create beauty. The auroras born from these solar interactions paint the skies with their ethereal glow. These natural light displays, visible near the poles and occasionally at lower latitudes during strong geomagnetic storms, serve as a reminder of the dual nature of solar activity, its power to both disrupt and to inspire. The dynamic and sometimes dangerous relationship between solar phenomena and Earth underscores the importance of continuous monitoring and research. As our society becomes ever more reliant on technology, understanding and preparing for the impact of solar flares and CMEs is essential for safeguarding our infrastructure and ensuring that we can enjoy the beauty these cosmic events bring to our skies. The solar cycle is an extraordinary phenomenon that unfolds over approximately 11 years, shaping the dynamic behaviors of the sun and influencing space weather across the solar system. It is driven by the sun's magnetic field, which undergoes a significant transformation every cycle. At the start of the cycle, called the solar minimum, the sun appears relatively quiet, with fewer sunspots and minimal solar activity. As the cycle progresses, however, the intensity of the sun's magnetic field grows, leading to a dramatic increase in sunspots and solar events such as solar flares and coronal mass ejections, CMEs. These phenomena, especially during the solar maximum, trigger massive solar activity, turning the sun into a cauldron of energy and magnetic forces. During solar maximum, the sun's magnetic fields are at their peak, producing a burst of solar flares that release immense radiation. These flares can interfere with satellite communications, disrupt GPS systems, and even damage power grids on Earth. Meanwhile, coronal mass ejections, which are more frequent and potent during this phase, send charged particles colliding with Earth's magnetosphere, triggering geomagnetic storms. These storms have the potential to wreak havoc on our technological infrastructure and pose a greater risk to astronauts and passengers on high-altitude flights over the polar regions, increasing radiation exposure. The fluctuations in the solar cycle can also impact the Earth's outer atmosphere, causing it to expand and creating more atmospheric drag on satellites. This drag can alter satellite orbits, requiring recalibrations to maintain their precise positions. In addition to these technological implications, the sun's activity plays a crucial role in affecting the Earth's environment. During periods of intense solar activity, the amount of ultraviolet, UV, and X-ray radiation reaching Earth increases, impacting the ozone layer and atmospheric chemistry. Understanding the solar cycle has thus become vital for preparing and predicting the various levels of solar activity that can influence our daily lives. With the advanced capabilities of solar observatories like NASA's Solar Dynamics Observatory, SDO, and the European Space Agency's Solar and Heliospheric Observatory, SOHO, scientists are now better equipped to monitor and understand these phenomena in detail. Researchers combine a range of observational tools, from ground-based telescopes to space-based satellites, to investigate the complexities of solar behavior. Ground-based solar observatories, such as the Daniel K. Inouye Solar Telescope in Hawaii, provide the most detailed and high-resolution images of the sun's surface. These telescopes allow scientists to study sunspots, solar flares, and magnetic fields in unprecedented detail. With adaptive optics technology, they can counteract atmospheric distortions, providing clearer views of the sun's photosphere. Complementing these observations, space-based telescopes like NASA's Solar Dynamics Observatory continuously monitor the sun across multiple wavelengths, revealing dynamic processes occurring in the sun's outer layers. SDO provides crucial data on solar flares, sunspots, and magnetic field variations, helping predict the timing and intensity of space weather events. The European Space Agency's Solar and Heliospheric Observatory has also played a critical role since its launch in 1995, offering essential data on the sun's atmosphere and detecting early signs of solar flares and CMEs. As space missions evolve, exploration has taken even bolder steps. NASA's Parker Solar Probe, launched in 2018, is designed to travel close to the sun, diving into its outer corona. This groundbreaking mission measures magnetic fields, solar wind, and energetic particles, helping scientists understand the mysterious processes that heat the sun's corona and drive the solar wind. Similarly, the Solar Orbiter, developed by the European Space Agency, conducts close-range observations, capturing high-resolution images of the sun's poles, regions that have been difficult to study until now. By combining data from these groundbreaking missions, scientists are piecing together a comprehensive understanding of the sun's activity. This knowledge is key to predicting and mitigating the effects of solar events on our technological infrastructure, ensuring that we are prepared for the potential challenges that space weather presents. Similarly, the lunar cycle, another fascinating celestial phenomenon, presents a captivating rhythm of light and shadow. The moon, as it orbits Earth, undergoes a continuous transformation, shifting through various phases approximately every 29.5 days. This cycle, known as a lunation, occurs due to the complex interplay between the positions of the moon, Earth, and the sun. As the moon travels in its orbit, different portions of its sunlit side become visible from Earth, resulting in the moon's distinct phases. The cycle begins with the new moon, when the moon is positioned between Earth and the sun. During this phase, the side of the moon that faces Earth is entirely in shadow, rendering it invisible to the naked eye. As the moon moves in its orbit, it enters the waxing crescent phase. A thin crescent of the moon's surface is illuminated, and each night this crescent grows larger. When the moon reaches the first quarter phase, often called a half moon, half of its surface is visible, illuminated by sunlight. Following this, the waxing gibbous phase begins, where more than half of the moon's surface is illuminated, continuing to grow until it becomes a full moon. During the full moon phase, the moon is opposite the sun, with Earth positioned in between. This alignment allows the entire sunlit side of the moon to be visible from Earth. Afterward, the moon enters the waning gibbous phase, where the amount of light begins to decrease. The moon continues its journey through the last quarter phase, another half moon, but with the opposite half illuminated compared to the first quarter. From there, the cycle continues, providing a spectacular celestial display that connects the Earth and the moon in a dance of light and shadow. The waning crescent phase, one of the most evocative stages of the moon's cycle, marks the final steps of the moon's journey toward renewal. During this phase, the light gradually diminishes, transforming into a delicate sliver of a crescent, before the cycle returns to the new moon. This sequence of lunar phases is not only a mesmerizing natural rhythm, but also a manifestation of the intricate mechanics that govern celestial motion. The phases are caused by the varying angle from which we view the illuminated part of the moon, shaped by its relationship with Earth and the sun. Over time, these shifting phases have provided not only a celestial spectacle, but also a natural guide for timekeeping, marking the passage of days and seasons across cultures and civilizations. The waxing and waning of the moon has been used to track time and even shape cultural laws for centuries. For ancient societies, the lunar cycle symbolized the eternal motion of the universe, an ever-changing force that remains an essential part of human history. Understanding these lunar phases helps us appreciate the ongoing dance of celestial bodies and reminds us of the constant dynamism that defines our universe. The moon, with its ever-evolving phases, provides a window into the deep and intricate processes that govern the cosmos. One of the most captivating questions that has intrigued scientists for centuries is the origin of the moon. Its formation has sparked numerous theories, with the most widely accepted being the giant impact hypothesis. According to this prevailing theory, the moon was formed about 4.5 billion years ago, following a colossal collision between the early Earth and a Mars-sized body named Theia. The impact was nothing short of cataclysmic, vaporizing Theia and a portion of Earth's mantle and sending vast amounts of debris into space. Over time, this debris coalesced under the influence of gravity, eventually forming the moon. The consistency of the moon's composition, which closely matches Earth's mantle, provides strong evidence for this theory, suggesting that the two share a common origin. While the giant impact hypothesis remains the most credible explanation for the moon's formation, it is not the only theory that has been proposed. The capture theory, for instance, suggests that the moon formed somewhere else in the solar system and was later captured by Earth's gravity. However, this theory struggles to explain why the isotopic compositions of the Earth and the moon are so strikingly similar. Another theory, the fission theory, proposes that a rapidly spinning early Earth ejected a portion of its mantle, which eventually became the moon. But for this to be true, Earth would have had to spin at an impossibly high rate. A third theory, the co-formation theory, suggests that Earth and the moon formed together as a double system from the solar system's primordial accretion disk. However, this theory does not adequately explain the differences in the compositions of the two bodies. Despite these alternative theories, the giant impact hypothesis still holds the most weight in the scientific community. However, as lunar exploration progresses, new data and advanced computer simulations are providing fresh insights. Recent studies of lunar rock samples and cutting-edge modeling techniques suggest that multiple impacts, rather than a single cataclysmic collision, may have contributed to the formation of the moon. With missions like NASA's Artemis program, which aims to return humans to the moon, scientists hope to gather even more evidence that will refine our understanding of this pivotal cosmic event. The study of the moon's origin not only illuminates the early history of our planet and its satellite, but also provides critical insights into the processes that shape planetary systems throughout the universe. As humanity continues to explore the lunar surface, we are also learning more about the forces that influence the formation of other moons and planets across the cosmos. The moon's surface is an extraordinary tapestry, bearing witness to a history shaped by intense celestial forces. Among its most striking features are the lunar maria, vast dark plains formed by ancient volcanic eruptions. Despite their name, these seas are not filled with water, but instead are expansive basaltic plains, remnants of molten lava flows that solidified billions of years ago. Some of the most well-known maria include Mare Tranquillitatis, Sea of Tranquility, and Mare Imbrium, Sea of Rains, which are visible to the naked eye as dark patches on the moon's surface. These regions offer a stark contrast to the lunar highlands, which appear much lighter in color and are heavily cratered. These highlands represent the oldest part of the moon's surface and are pocked with impact craters of all sizes, telling the story of the moon's violent past. Perhaps the most impressive of these craters is the South Pole Aitken Basin, an enormous impact structure that spans a staggering 2,500 kilometers in diameter and plunges to depths of about 8 kilometers. This basin is one of the largest known impact structures in the solar system, underscoring the moon's tumultuous history as it was bombarded by meteoroids, asteroids, and other celestial bodies. The study of these craters and maria helps scientists understand the moon's geological history and provides invaluable clues about the processes that shaped our entire solar system. As we continue to gaze up at the moon, we are reminded not only of its beauty, but also of the profound mysteries it holds. mysteries that continue to captivate the imagination of scientists and stargazers alike. The moon, in all its phases, serves as both a timeless symbol of the universe's grandeur and an ongoing source of discovery, unlocking secrets that have shaped not only the Earth, but the very nature of the cosmos. The moon, our silent companion in the night sky, holds a wealth of geological secrets, each crater, ridge, and valley telling the story of its ancient past. Notably, well-known craters such as Tau and Cernus stand out with their striking central peaks and radiating streaks of ejected material. These rays, long and bright, stretch out across the lunar surface like scars from cosmic impacts. They serve as a testament to the violent forces that have shaped the moon's surface over billions of years. In addition to these dramatic features, the moon also showcases the fascinating presence of lunar rills, narrow, winding depressions that resemble valleys or channels, often extending hundreds of kilometers. These formations are believed to be the remnants of ancient lava flows or collapsed lava tubes, frozen in time as they trace the moon's volcanic history. The surface is further punctuated by scarps, cliff-like structures that hint at the moon's internal cooling and contraction. These scarps, such as the famous ones found in the region of Rimae Recta or Straight Wall, reveal that despite the lack of active plate tectonics, the moon's interior is still slowly cooling, causing its once thick crust to crack and shift. Beneath these geological spectacles lies the moon's regolith, a layer of loose, fragmented rock and fine dust generated by eons of micrometeoroid impacts. This powdery, dusty blanket covers the solid bedrock beneath, creating a stark and desolate landscape. The regolith is more than just an aesthetic feature. It is a scientific marvel, offering insight into the moon's violent history and serving as a valuable resource for future exploration. The intricate combination of maria, highlands, craters, rills, scarps, and regolith paints a vivid picture of the moon's dynamic and tumultuous geological history. In addition to its geological wonders, the moon plays a crucial role in regulating Earth's tides. Its gravitational pull creates tidal forces that cause the ocean's water levels to rise and fall in a rhythmic pattern, orchestrating the ebb and flow of our seas. Imagine the Earth as a massive sphere wrapped in a thin shell of water. As the moon's gravity tugs on this water, it creates what we know as the tidal bulge on the side facing the moon. At the same time, inertia causes a second bulge on the opposite side, giving rise to two high tides. As Earth rotates, different areas pass through these bulges, experiencing high and low tides roughly twice a day. But the moon's influence on tides is not so simple. The alignment of the sun, Earth, and moon can either amplify or moderate these tides. When the sun, moon, and Earth are in a straight line during full moons and new moons, their combined gravitational forces result in more extreme tides, known as spring tides. High tides are exceptionally high, and low tides are especially low due to the additive effect of both solar and lunar gravitational pulls. Conversely, when the sun and moon are at right angles relative to Earth during the first and third of the lunar cycle, their gravitational forces partially cancel each other out, resulting in less extreme or neap tides. The moon's influence on tides extends far beyond simple ocean movements. The rhythmic rise and fall of the tides help mix ocean waters, distributing nutrients and sustaining marine ecosystems. For human civilization, tides have played an essential role in navigation, fishing, and even the development of coastal settlements. The interaction between the tides and Earth's rotation also exerts a braking force, gradually slowing the Earth's spin over geological timescales, causing the length of our days to increase ever so slightly. This dynamic interaction between the Earth's rotation and the gravitational forces of the moon beautifully illustrates the intricate relationship between our planet and its celestial neighbor. The moon's gentle yet profound influence over Earth's tides serves as a constant reminder of the interconnectedness of the cosmos. The Apollo moon missions, which took place from 1969 to 1972, provided humanity with invaluable scientific insights and technological advancements that continue to shape our understanding of the moon and space exploration as a whole. During these missions, astronauts collected approximately 382 kilograms of lunar rocks, soil, and core samples, providing scientists with the opportunity to study the moon's composition firsthand. These samples not only deepened our knowledge of the moon's geological history, but also fueled the development of new technologies and research methodologies in space exploration. Through these groundbreaking missions, we gained a clearer understanding of the moon's role in our planet's natural systems. The Apollo missions laid the foundation for the future of lunar exploration, offering new possibilities for understanding the moon's potential as a resource hub and a stepping stone for humanity's journey beyond Earth. The moon, though seemingly silent and still, is anything but. From its stunning geological features to its essential role in shaping life on Earth, it is a celestial body that continues to intrigue and inspire us. Its deep influence on our planet's tides, its connection to Earth's history, and its potential as a key player in the future of space exploration make the moon an enduring symbol of the wonder and mystery of the cosmos. The lunar materials meticulously examined back on Earth have provided invaluable insights into the moon's composition, geological history, and the forces that have shaped its surface over billions of years. These carefully studied samples brought back during the Apollo missions revealed that the moon is primarily made of silicate minerals, similar to Earth's mantle, offering critical support to the giant impact hypothesis that suggests a colossal collision led to the moon's formation. The findings not only reshaped our understanding of the moon's origins, but also laid the groundwork for modern lunar science. The Apollo missions themselves did much more than bring back rock samples. They allowed scientists to directly assess the moon's surface. Astronauts performed extensive fieldwork, carrying out experiments, deploying scientific instruments, and collecting samples from diverse locations, such as the lunar highlands and Maria. This wealth of data allowed scientists to construct a comprehensive geological timeline of the moon's past, revealing evidence of volcanic activity and the scarred surface left by countless impacts. These findings highlighted how both internal geological processes and external bombardments from space have molded the moon into the celestial body we see today. One of the most groundbreaking achievements of the Apollo missions was the deployment of seismometers via the lunar module, which revealed the presence of moonquakes. These seismic readings offered a rare glimpse into the moon's internal structure, providing evidence of a differentiated interior composed of a crust, mantle, and a small core, challenging previous assumptions about the moon's geological makeup. Despite the lack of tectonic plates, this data suggested that the moon has a complex internal structure, much like Earth. The implications of this discovery continue to inform lunar exploration missions today. Beyond their scientific contributions, the Apollo missions sparked a revolution in technology. The cutting-edge technologies developed for space exploration, from advanced spacecraft design to life support systems, paved the way for many innovations in other fields, such as materials science and computer technology. The ripple effects of these technological advancements continue to be felt in everyday life, as the lessons learned from lunar exploration are applied in countless industries. The Apollo program also fostered international collaboration, uniting nations in the pursuit of a common goal. The inspiration drawn from these missions has motivated generations of scientists, engineers, and ordinary people, further emphasizing the potential of human ingenuity and collaboration. The Apollo mission's legacy lives on in modern lunar exploration, influencing initiatives like NASA's Artemis program, which is aiming to return humans to the moon and establish a sustainable human presence by the end of this decade. Artemis builds on the lessons learned from Apollo while leveraging state-of-the-art technology and engineering advancements. The Artemis program's uncrewed mission will test the Space Launch System, SLS rocket, and the Orion spacecraft, setting the stage for subsequent crewed missions. Artemis the Set will pave the way for more complex lunar flybys, eventually leading to Artemis 3, which will land astronauts at the lunar South Pole, a region rich in water ice and crucial scientific potential. The future of lunar exploration is not solely in the hands of NASA. International collaboration, including contributions from the European Space Agency, ESA, Russia's Roscosmos, and China's CNSA, will be pivotal in the next phase of human exploration on the moon. These agencies have outlined their plans for lunar missions, adding to the growing global commitment to exploring and understanding our closest celestial neighbor. This newfound era of cooperation, driven by advancements in technology and shared scientific goals, is setting the stage for humanity's long-term presence on the moon. As humanity sets its sights on a sustainable future on the moon, the Apollo mission's groundbreaking legacy will continue to illuminate our path forward. With space programs like Artemis leading the charge, the next chapter in lunar exploration promises to be nothing short of transformative. The moon, once a distant and mysterious world, now stands at the threshold of becoming a pivotal base for humanity's future in space, an exploration and colonization journey that will undoubtedly change the course of human history. The International Lunar Research Station, a groundbreaking initiative being developed by China and Russia, serves as a testament to the power of international collaboration. This ambitious project envisions a fully operational research outpost on the moon, combining the expertise of astronauts and robotic systems in the pursuit of advancing humanity's presence beyond Earth. Central to the success of this lunar endeavor is the development of critical technologies, particularly advancements in in-situ resource utilization, ISRU. By harnessing the moon's natural resources, such as extracting water from lunar ice, these technologies will enable the production of oxygen and fuel, ensuring that lunar outposts are sustainable and able to support future space missions. One of the primary challenges of living and working on the moon lies in overcoming the extreme lunar environment. With temperatures swinging from blistering heat to frigid cold, and harmful solar radiation constantly bombarding the surface, the need for innovative infrastructure solutions is urgent. To meet this challenge, researchers are exploring groundbreaking methods in habitat construction. One promising approach involves using 3D printing technology, which can create structures from lunar regolith, the moon's surface material. This method could provide the necessary shelter and protection for astronauts, reducing costs and the need for imported materials. Commercial entities such as SpaceX and Blue Origin are playing an integral role in this ambitious vision. SpaceX's Starship is poised to transport large payloads and crews to the moon, dramatically reducing the cost per launch and enabling more frequent and expansive missions. Meanwhile, Blue Origin's Blue Moon lander is designed to facilitate cargo and crew transport, supporting the broader goals of lunar colonization. Through these collective efforts, the moon is set to transform into a hub for scientific research, technological innovation, and a vital stepping stone for deeper space exploration. As nations and private companies join forces, the dream of establishing a human presence on the moon is becoming an imminent reality. This presence will not only provide invaluable experience in living and working in extraterrestrial environments, but will also lay the groundwork for future missions to Mars and beyond. By establishing this permanent foothold, humanity will gain critical insights into the challenges of multiplanetary living, positioning itself for the next giant leap in our quest to explore the stars. The moon, once a distant aspiration, is quickly emerging as an essential gateway to the rest of the solar system. Stars, much like the moon, present a staggering variety of forms and features, each telling a unique story in the grand narrative of the cosmos. At one end of the stellar spectrum are the small but abundant red dwarfs, stars that often possess less than half the mass of our sun. These stars burn their fuel so slowly that they can live for trillions of years, far surpassing the lifespan of stars like our own. With surface temperatures ranging from 3,000 to 4,000 Kelvin, red dwarfs emit a faint, cool reddish light, distinguishing them from the hotter, more luminous stars that dominate the celestial stage. As we move up the scale, we encounter stars like our Sun, a G-type main sequence star, often referred to as a yellow dwarf. Despite its seemingly modest designation, the Sun is significantly larger and more luminous than many other stars in our galaxy, providing the necessary heat and energy for life on Earth. Beyond the Sun, the universe introduces us to the majestic blue giants and even more enormous blue supergiants. These massive stars, such as Riel and Betelgeuse in the Orion constellation, boast surface temperatures ranging from 10,000 to over 30,000 Kelvin, emitting brilliant blue and white light. These stars, often tens or even hundreds of times larger than our Sun, are dazzling beacons in the night sky, captivating astronomers and stargazers alike with their spectacular brilliance and power. As we explore these celestial giants, we gain insight not only into the universe's incredible diversity, but also into the processes that govern the birth, evolution, and eventual death of stars. From the smallest red dwarfs to the most massive blue supergiants, each star offers a glimpse into the vast cosmic cycle, reminding us of the immense scale and complexity of the universe we inhabit. However, their grandeur comes at a staggering cost. Blue supergiants, the celestial giants of the universe, burn through their nuclear fuel at a ferocious pace, using it up far quicker than their smaller counterparts. This intense energy consumption results in lifespans that are strikingly short, lasting only a few million years. In the final stages of their lives, many of these stars face a spectacular and violent end, the catastrophic explosion of a supernova. The remnants of these extraordinary stellar events, often left behind as neutron stars or black holes, become some of the most enigmatic objects in the cosmos, ultimate celestial mysteries that continue to both puzzle and fascinate scientists. The birth of stars, though, is a truly awe-inspiring process, a cosmic symphony unfolding in the vast cold reaches of space. It all begins in stellar nurseries, vast dark clouds of gas and dust that drift through the arms of galaxies. These nurseries are primarily made of hydrogen and helium, and they silently stretch across the universe, waiting for gravitational forces to stir them into motion. Over time, pockets of this interstellar gas begin to contract and clump together under the weight of gravity. As these clumps grow more massive and dense, the pressure within them rises, heating up the core. The temperature climbs steadily until it reaches a critical threshold of about 10 million Kelvin, at which point nuclear fusion ignites, marking the birth of a new star. It's almost surreal to imagine the quiet whispers of gravity initiating this process, an unseen force that eventually leads to the roaring blaze of nuclear fire at the heart of the newborn star. As the star grows, it often creates stunning visual phenomena. The surrounding gas and dust, remaining from its formation, spirals into protoplanetary disks, spinning in space like cosmic jewelry. Over millions of years, some of these disks will eventually form planets, while others may dissipate into the vastness of space. In regions like the Orion Nebula, these stellar birthplaces come to life in extraordinary ways, with towering pillars of gas and dust spiraling around infant stars, glowing with the light of newly formed suns. The powerful interplay of radiation pressure and gravity gives birth to intricate, fleeting structures in the nebula, a living testament to the incredible forces at work. This process, lasting millions of years, is a testament to the profound power and beauty of the universe, ensuring that the cycle of star formation continues. These stars, born from the very fabric of the cosmos, populate the universe with new sources of light, energy, and ultimately life. The life cycle of a star is a grand narrative unfolding over billions of years. It begins in these stellar nurseries, vast clouds scattered across galaxies, where gravity's invisible hand pulls the gas together. From these clouds, protostars emerge, and once nuclear fusion ignites in their cores, they officially become main sequence stars, spending the majority of their existence in this stable phase. This phase is governed by a delicate balance between gravity, pulling matter inward, and the outward pressure created by nuclear fusion in the core. Our own sun, for instance, has been in this phase for about 4.6 billion years and is expected to remain in this stage for another 5 billion years, providing a sense of stability to the planets that orbit it. However, as stars like the sun begin to exhaust their hydrogen fuel, their fates diverge dramatically, dictated by their mass. Stars that are similar in size to our sun will eventually expand into red giants, their outer layers puffing up to immense proportions. As these outer layers are shed, they create stunning planetary nebulae, colorful clouds of gas and dust that tell the story of a star's death. Beneath these layers, what remains is a dense core, an incredibly hot white dwarf. Over billions of years, these white dwarfs will cool, fading into the cold silence of space. In contrast, massive stars, those far greater than our sun, experience much more dramatic and cataclysmic endings. After burning through elements like helium, carbon, and finally iron, the core of the star collapses under the relentless pull of gravity, triggering a supernova explosion. These explosions are so powerful that they can briefly outshine entire galaxies, releasing vast amounts of energy and enriching the surrounding space with heavy elements. This cosmic scattering of elements forms the building blocks for future stars and planets, ensuring that the cycle of creation continues. The remnants of these massive stars, depending on their mass, may become neutron stars, or if their mass is sufficient, collapse even further into black holes. These black holes, with their gravitational pull so intense that not even light can escape, remain some of the most mysterious objects in the universe. Thus, the life cycle of a star is not just a tale of birth and death. It is a magnificent saga of transformation, of creation and destruction, of energy and matter being constantly recycled across the cosmos. It contributes endlessly to the evolution of the universe, driving the very forces that shape the galaxies and life itself. The stars' births, their lives, their deaths, these cosmic phenomena continue to inspire and reveal deep mysteries of the universe, guiding our understanding of everything from the smallest particles to the vastness of space itself. When a supernova explodes, it's not just an end, but a beginning, one of the most spectacular and transformative events in the universe. These cosmic explosions signal the death of massive stars, but they do so much more than destroy. They lay the foundation for cosmic rebirth. As a star collapses in on itself, the resulting supernova releases an unfathomable amount of energy. This cataclysmic release scatters the outer layers of the star across the surrounding interstellar space, enriching it with heavy elements like iron, oxygen, and silicon. These elements, forged in the heart of the star through nuclear fusion, were previously locked away in the star's core. The expelled material forms supernova remnants, vast clouds of enriched gases that fuel the future of the galaxy. These remnants serve as the building blocks for the next generation of stars, planets, and even life itself. As the shockwave from the supernova ripples outward, it triggers the compression of nearby clouds of gas and dust, setting off a chain reaction of star formation. Regions of the galaxy that were once quiet are now alive with potential. The Orion Nebula, a prime example, sits in an area dense with the remnants of past stellar explosions, now illuminated by the birth of new stars. Here, in these stellar nurseries, new generations of stars rise from the ashes of the old, keeping the cycle of cosmic rebirth alive. It's a continuous dance of creation and destruction, ensuring that the universe remains ever-evolving and dynamic, a cosmic tapestry woven together by the remnants of the past and the promise of the future. But supernovas don't only give birth to new stars. They also give birth to something far more mysterious and enigmatic: black holes. These celestial giants are the remnants of the most massive stars, those with masses greater than 20 times that of our Sun. When such a star exhausts its nuclear fuel, it can no longer resist the relentless pull of gravity. Its core collapses under the pressure, compressing matter to an unimaginable degree, creating a singularity, a point of infinite density. The process begins with the implosion of the star's core, creating a neutron star if the conditions are right. But for the most massive of stars, even the formation of a neutron star can't halt the collapse. The core continues to compress until eventually a black hole forms, a region of space so dense and powerful that not even light can escape. Surrounding this singularity is the event horizon, the point of no return. Anything that crosses this boundary is irretrievably drawn into the black hole. Despite their fearsome reputation as destructive monsters of the cosmos, black holes play an essential role in the universe's balance. Their intense gravitational fields influence the formation and movement of galaxies, and they warp the very fabric of space-time itself. Though first predicted by Einstein's theory of general relativity, it wasn't until advancements in technology, like the detection of gravitational waves by instruments like LIGO, that we could confirm their existence. These waves, which are ripples in space-time caused by cataclysmic events like black hole mergers, have provided direct evidence of these cosmic giants. Thus, from the death of a massive star emerges not only a black hole, one of the universe's most mysterious phenomena, but also the continuation of an eternal cycle. Destruction and creation, intertwined, ensure that the cosmos remains a dynamic, ever-changing system. The death of a star gives birth to something profoundly new, feeding the unending dance of cosmic evolution across the universe. In the vast expanse of our universe, binary star systems present one of the most captivating phenomena, offering a dynamic stage for studying stellar behavior and evolution. These systems consist of two stars locked in a gravitational embrace, orbiting around a common center of mass. This mutual orbit, much like a celestial ballet, reveals a complex interaction between the two stars, each influencing the other's motion with its gravitational pull. It's a natural, dynamic laboratory where astronomers can observe and test theories about stellar physics, an opportunity to unlock secrets hidden deep within the heart of stars. The gravitational dance in binary star systems can vary dramatically, with some systems exhibiting nearly circular orbits while others trace highly elliptical paths. These variations are more than just visually striking. They significantly influence the evolutionary paths of the stars. In systems with more eccentric orbits, the stars are periodically drawn closer together before being cast apart, creating a rhythm of gravitational attraction that directly impacts the star's internal processes. The proximity and motion within these systems hold the key to understanding not only the stars themselves, but also their individual life cycles. In some cases, the gravitational tug-of-war between the stars in a close binary system can have profound consequences. Mass can be transferred from one star to the other, altering their fates in remarkable ways. Take, for example, a red giant star. As it expands, it may shed its outer layers, which are then absorbed by a smaller companion star. This exchange of matter can lead to dramatic changes, such as the companion star becoming a white dwarf. If the transferred material accumulates and ignites on the surface of the white dwarf, it can trigger a violent explosion known as a nova. The intense radiation from such events provides invaluable insights into the processes of stellar evolution. But the story doesn't end there. In some binary systems, particularly those with very close orbits, interactions can escalate to more extraordinary phenomena, such as the emission of gravitational waves or even star mergers. These events, which occur when two stars collide or merge, offer a deeper glimpse into the mysteries of the universe. They can yield insights into the very nature of matter, energy, and the forces at play in the cosmos. What truly sets binary star systems apart, however, is the moment one of the stars evolves into a compact object, such as a white dwarf, neutron star, or even a black hole. These dense remnants of stellar collapse wield immense gravitational force. As they pull matter from their companion stars, they create accretion disks, hot, swirling masses of gas and dust that emit powerful X-rays detectable from Earth. Such phenomena have been observed in systems like Cygnus X1, where a stellar mass black hole pulls matter from a nearby companion star, offering some of the earliest and most compelling evidence for the existence of black holes. Binary star systems are not just spectacular cosmic displays. They are critical to our understanding of the universe. Through their complex interactions and diverse behaviors, they serve as crucial tools in exploring the fundamental principles that govern stellar life and death. Each system offers a unique perspective on the forces of gravity, mass, and energy, allowing scientists to test and refine models of stellar dynamics in ways that would be impossible with isolated stars alone. Beyond the realm of binary systems, the stars themselves have been a source of wonder and myth for millennia. Humans have long looked to the night sky, tracing patterns and creating constellations that represent stories, legends, and celestial landmarks. From the ancient Babylonians to the Greeks and various other cultures around the world, constellations provided a way to understand and navigate the heavens. Unlike binary systems, however, constellations aren't groups of stars bound together by gravity or proximity. Rather, they are a perspective-based collection of stars that, from our vantage point on Earth, appear to form recognizable patterns. These celestial groupings may not have physical connections, but they are integral to our understanding of the night sky and its ever-changing dynamics. Binary star systems and constellations alike remind us that the universe, with all its beauty and complexity, offers a never-ending story of discovery and wonder. In ancient times, the stars were not just distant points of light scattered across the heavens. They were celestial maps, guiding the lives of those who looked to the skies for direction and meaning. Acting as a celestial roadmap, constellations were crucial to human navigation and understanding of the cosmos. Mariners, for example, would rely on familiar patterns like Big Dipper, part of the constellation Ursa Major, to chart their courses across vast and unknown seas. These star patterns were the compass of the ancient world, helping seafarers determine their longitude and latitude with astonishing accuracy, even long before the invention of modern navigational tools. Farmers, too, had their lives shaped by the stars. They used the constellations to signal the changing of the seasons, noticing when certain groups of stars appeared or disappeared at specific times of the year. These celestial signals helped farmers time their planting and harvesting, ensuring the survival of their crops. But the significance of the stars extended beyond practical use. Constellations were deeply embedded in the cultural and religious practices of ancient civilizations. The Greeks, for instance, turned the sky into a vast canvas of gods, heroes, and mythical creatures. Stars were seen as the homes of their gods, and their stories immortalized in constellations. Take the story of Orion, the mighty hunter. His image was woven into the stars, forever chasing after the great celestial hare, Lepus, with his loyal companions, the two constellations of Canis Major and Canis Minor. Over time, astronomy evolved, and by the 20th century, the International Astronomical Union, IAU, formalized the boundaries of the 88 constellations we recognize today. These clear boundaries have become an essential tool for modern scientists and astronomers, aiding in the cataloging and study of celestial bodies. The IAU ensured that every inch of the night sky belonged to a specific constellation, allowing for more accurate observations and better understanding of our universe. However, the enduring fascination with constellations isn't just about science. These celestial patterns continue to captivate our imaginations and inspire awe, evoking a sense of wonder and curiosity about the vast cosmos. But there is more to these constellations than their beauty. In a way, they are mnemonic devices, helping us navigate the night sky and locate distant stars, nebulae, and galaxies. Through the lens of history and science, constellations also reflect humanity's deep-rooted desire to impose order on the cosmos and find meaning in the stars. Among the vast tapestry of stars, some constellations stand out, not just for their striking patterns, but for the rich myths and stories that accompany them. One of the most iconic is Orion, easily recognizable by the distinctive belt of 3 stars aligned in a row. In Greek mythology, Orion was a hunter so skilled and handsome that he caught the eye of the gods, yet his legendary prowess led to his tragic end, either by the sting of a giant scorpion, represented by the constellation Scorpius, or in other versions of the myth, through divine retribution. Regardless of the details, the heroic tale of Orion's rise and fall continues to mesmerize stargazers. Another famous constellation with a rich mythological history is Ursa Major, more commonly known as the Big Dipper. In the Northern Hemisphere, the 7 bright stars of the Big Dipper form part of a larger pattern that resembles a great bear. Native American folklore often tells of a bear pursued by 3 hunters, reflecting stories passed down through generations. In contrast, Greek mythology offers a different perspective, with the constellation representing Callisto, a nymph turned into a bear by the jealous goddess Hera. The story ends with Callisto being placed among the stars by Zeus, alongside her son, Arcas, whose constellation Ursa Minor represents the little bear. Together, these constellations remain eternal symbols of transformation and familial bonds, forever bound in the celestial dome. Another constellation with an intriguing backstory is Corona Borealis, marked by its distinctive W shape. According to Greek mythology, this constellation represents the crown of the queen, Copa, whose vanity led to her tragic downfall. Copa boasted that her beauty surpassed even that of the sea nymphs, who were dear to Poseidon, the god of the sea. In retribution, Poseidon condemned her to the night sky, where she would be doomed to spin around the celestial pole on her throne, often appearing upside down, a constant reminder of her hubris. These constellations, along with others like Pegasus, Andromeda, and Leo, are more than just patterns in the sky. They are the threads of a rich cultural tapestry woven from myth, history, and human imagination. Each constellation tells a story, whether it's of gods, heroes, or transformation, reflecting the timeless human penchant for storytelling. Their legacy endures, not just in the study of astronomy, but in the mythology that continues to inspire and enrich our understanding of the universe. The Milky Way, our cosmic home, is not just a mere collection of stars. It is a vast, spiraling masterpiece, a swirling dance of stars, gas, dust, and dark matter, each element playing its part in an intricate cosmic choreography that's across the heavens. At the heart of this expansive structure lies the galactic center, a region so dense it defies imagination. Dominating this core is a supermassive black hole, Sagittarius A, with a mass about 4 million times that of our Sun, a force so powerful that it governs the very dynamics of the galaxy itself. Around this tumultuous center is the galactic bulge, a sprawling sphere of ancient stars and dense star clusters that spans thousands of light years. As you move outward from the bulge, the most striking features of the Milky Way become apparent: its elegant spiral arms. These arms, named for their sweeping curves, are the birthplaces of stars, vast regions where new stars are born in nebulae, their fiery glow illuminating the galactic canvas. Our solar system resides in one of these arms, the Orion arm, a minor spiral situated between the larger Perseus and Sagittarius arms. Here, the stars are young, brilliant, and full of life, surrounded by the dark clouds of gas and dust that form the backdrop of this celestial nursery. The structure of the Milky Way is not static, it is alive, constantly evolving through the cosmic dance of gravity. The spiral shape of the galaxy is maintained by density waves, gravitational ripples that travel through the galaxy, compressing gas and triggering new stars to form. These waves sweep through the gas clouds like a cosmic wind, creating areas of intense star formation along the arms of the galaxy. Encasing this spiraling structure is the galactic disk, a thin, flattened plane where most of the stars reside, rotating around the galaxy's center. Above and below the disk lies a vast, diffuse halo of ancient stars and globular clusters, some of the oldest known objects in the universe. This halo is also thought to be rich in dark matter, an invisible substance that exerts gravitational pull but emits no light. It's this mysterious dark matter that influences the overall mass and rotation of the Milky Way. Beyond the halo lies the outer fringes of the galaxy, a sparsely populated region where solitary stars and faint streams of stars drift. These are the remnants of ancient galactic mergers, slowly dissolving into the cosmic sea. Despite its apparent emptiness, this expanse plays a crucial role in understanding the Milky Way's formation, providing clues about past interactions with other galaxies. It is here in this distant outer edge that we glimpse the long, intertwined history of our galaxy's evolution. The Milky Way's grand design, spanning over 100,000 light-years across, is a reflection of cosmic interactions that have shaped its evolution over billions of years. It is a galaxy in motion, its structure a living testament to the forces that drive the universe. Within this spiraling city of stars, countless star systems, including our own, find their place in the vast celestial tapestry. Galaxies themselves are colossal structures that make up the universe, classified into distinct types based on their shapes and compositions. The Milky Way belongs to the category of spiral galaxies, which are among the most visually captivating. These galaxies are defined by their graceful, winding arms that extend from a central bulge. The arms themselves are regions of intense activity, with young, hot blue stars illuminating the dark expanse, forming what is known as a grand design spiral. Some spiral galaxies are barred, meaning a bar-like structure of stars cuts through the central bulge, giving them a distinctive appearance. In contrast to spirals, elliptical galaxies appear far more uniform. They are oval in shape, lacking the complex structure of spiral arms, and are typically populated by older, red stars. These galaxies, while visually simpler, still carry the stories of the universe's past, offering insights into the processes of cosmic evolution. Whether spiral or elliptical, each galaxy type tells its own story, adding another layer of complexity to the grand narrative of the cosmos. As we peer into the vastness of the Milky Way and beyond, we are reminded of the dynamic and ever-evolving nature of the universe. The intricate beauty of our galaxy and the diversity of galaxies across the cosmos are a testament to the incredible forces and processes that have shaped the very fabric of our existence. From the heart of the galaxy to the furthest reaches, the Milky Way is not just a collection of stars. It is a living, breathing entity, a cosmic masterpiece in constant motion. In the vast expanse of the universe, galaxies come in all shapes and sizes, each with its own unique story and evolutionary path. Among the most fascinating are elliptical, spiral, and irregular galaxies, each representing a distinct phase in the cosmic life cycle. Elliptical galaxies, often appearing calm and composed, tell a tale of galactic aging. Studies of their population suggest that these galaxies have exhausted much of their interstellar gas, leaving behind little material for new star formation. As a result, elliptical galaxies are quieter and less dynamic compared to their spiral counterparts. It is believed that elliptical galaxies form through the collisions and mergers of smaller galaxies, events that can disrupt their initial structures and create the more uniform, featureless appearance we observe today. Over time, these galactic mergers consolidate stars into a central bulge, making them appear as massive, settled systems filled mostly with older red stars. Though their past is one of chaos and interaction, the elliptical galaxy of today is often still and serene. In stark contrast to the orderly elliptical galaxies, irregular galaxies showcase a wild and untamed form. Lacking the symmetry of their spiral and elliptical cousins, irregular galaxies are often smaller and display a chaotic structure. Within these galaxies, regions of intense star formation are scattered across, interspersed with pockets of older stars. The irregularity often results from gravitational interactions with nearby galaxies or the aftermath of past galactic collisions. Unlike elliptical galaxies, irregular galaxies are often brimming with gas and dust, fueling continuous star formation and making them some of the most active structures in the universe. Their turbulent histories and diverse appearances stand as testament to the forces that shape the cosmos, revealing the unpredictable beauty of the universe's evolution. Then there are the spiral galaxies, magnificent with their sweeping arms, home to vigorous star formation. These galaxies, like our very own Milky Way, continue to dazzle with their dynamic nature. Unlike elliptical galaxies, which are more static, spiral galaxies maintain an ongoing process of creation. They are living, breathing structures, continuously giving birth to new stars and maintaining their place as some of the universe's most beautiful and complex entities. As we explore these three types of galaxies, spiral, elliptical, and irregular, we are reminded of the vast diversity in the cosmos. Their varying shapes and behaviors reveal the complex and fascinating processes that have shaped the universe over billions of years. Each galaxy type contributes to the magnificent, ever-evolving tapestry of the universe, shedding light on the role of cosmic forces in creating and sustaining these celestial bodies. In the grand expanse of galaxies, some stand out not just by their form, but by their immense size. Among the largest known galaxies, one looms as a true giant, IC 1101. Situated over 1 billion light-years away in the Virgo constellation, IC 1101 is a breathtaking example of cosmic scale. Spanning an astonishing 6 million light-years, it is roughly 60 times the diameter of our Milky Way. This colossal galaxy is home to hundreds of trillions of stars, many of which are older and redder, indicating that IC 1101 has long since ceased active star formation. Its monumental size is a result of countless galactic mergers over billions of years, steadily accumulating mass and dimensions through gravitational interactions. IC 1101's sheer scale and age give us a glimpse into the deep history of the universe, a reminder of how galaxies can grow and evolve over unimaginable timescales. Not far behind, ESO 306-17 offers another extraordinary example of galactic size. Though not as vast as IC 1101, ESO 306-17 still stretches across an immense 1 million light-years in diameter. Situated 500 million light-years away, this elliptical galaxy is surrounded by an impressive array of globular clusters, hinting at a complex and violent past marked by frequent mergers and interactions. The presence of these clusters gives further insight into the galaxy's history, suggesting a period of intense gravitational forces at work, shaping its present form. These massive structures continue to intrigue astronomers, offering clues about the formation and evolution of galaxies in the universe. Another cosmic giant is found in the heart of the galaxy cluster Abell 2029, which is anchored by the enormous elliptical galaxy NGC 6166. Though not as large as IC 1101, NGC 6166 stands out for its colossal central black hole and powerful radio emissions. This galaxy forms the core of one of the largest known galaxy clusters, contributing to its vast gravitational footprint. The dynamics of this galaxy cluster shed light on the intricate and often violent interactions that take place in these crowded cosmic regions, where galaxies collide, merge, and transform under the immense influence of gravity. NGC 6166 serves as a reminder of the complex processes that shape the universe, providing invaluable insights into the role of dark matter, gravitational forces, and cosmic evolution. The study of these colossal galaxies and their complex histories offers astronomers a rare opportunity to witness the processes that govern galaxy formation and evolution. By observing these cosmic leviathans, scientists gain a deeper understanding of how galaxies grow, the role of dark matter in shaping their structures, and the impact of galactic mergers on the broader universe. These giants are not just physical objects, but windows into the past, offering a glimpse into the forces that have shaped and continue to shape the cosmos. At the heart of these galactic evolutions lies the story of the universe itself. The formation of galaxies is a process that stretches back to the earliest moments after the Big Bang, when the universe was a hot, dense soup of hydrogen and helium. As the universe began to cool, small fluctuations in density allowed gravity to begin its work, pulling gas and dark matter together to form the first proto-galaxies and stars. This process, known as the cosmic web, laid the groundwork for the creation of larger structures over time. Through a series of mergers and accretions, smaller galaxies combine to form larger, more complex systems. This hierarchical buildup is a cornerstone of the lambda cold dark matter model, which describes how galaxies evolve over billions of years. As galaxies merged and grew, their mass increased, stirring up the gas within them and creating the conditions for new star formation. These events of galactic interaction are key to understanding the growth and transformation of galaxies. The process is not always smooth, as mergers often lead to disruptions in the galactic structure, sparking bursts of new star formation or triggering the collapse of gas clouds into supermassive black holes. Despite the chaos, these processes drive the evolution of galaxies, creating the rich diversity of galactic structures we observe in the universe today. The study of galaxies, both the small and the immense, offers us a window into the workings of the universe, revealing the forces of gravity, dark matter, and cosmic evolution that shape the very fabric of space and time. These galaxies, each with their own unique history, are not just objects of scientific study, but symbols of the creative power of the cosmos, forever transforming as they collide, merge, and evolve. In the vast, uncharted reaches of the universe, galaxies undergo an incredible transformation. Often they interact with one another in a cosmic dance, triggering bursts of star formation known as starbursts. These stellar explosions aren't just temporary phenomena. They represent significant moments in a galaxy's life cycle, marking periods of intense creativity within the cosmos. Mergers between galaxies are a key part of this ongoing narrative, and their impacts can be nothing short of dramatic. When spiral galaxies collide, their orderly arms and swirling structures often crumble, giving way to the chaotic forces at play. The result? The birth of elliptical galaxies, round and settled, formed from the turbulent union of their spiral predecessors. The evidence of such transformations can be found in the clusters of galaxies scattered throughout the universe. These clusters, dense with galaxies, are more likely to contain elliptical forms, suggesting that they've undergone multiple mergers over cosmic time. It's as if the universe itself is reshaping its galaxies, turning them into new forms that can stand the test of time. Meanwhile, galaxies like our Milky Way are typically found in more serene, less crowded regions of space. They avoid the disruptive collisions that are so common in more densely populated areas. This allows them to maintain their iconic spiral shape for much longer, preserving their beauty and structure as they grow. As they continue to interact with other cosmic forces, the spiral galaxy's life evolves, carrying with it a story of survival in an ever-changing universe. But galaxies aren't just passive victims of cosmic forces. They also actively evolve. Take, for example, the spiral galaxy. Over billions of years, it gradually transforms its interstellar gas into new stars, fostering a lively environment for the birth of new celestial bodies. However, once the gas supply begins to dwindle, star formation slows, and the galaxy's youthful blue-hued appearance gives way to a more mature, redder tone. As the stars age and the galaxy transitions, its character shifts. This aging process is deeply intertwined with the life cycles of supernova explosions and the mysterious forces lurking in the centers of galaxies, supermassive black holes. These black holes aren't just passive observers. Their intense gravitational forces shape the very heart of galaxies, regulating star formation, expelling gas, and influencing the galactic environment. Together with the explosive power of supernovae, these forces continually reshape the galaxy, ensuring that even as a galaxy ages, it remains a dynamic, ever-changing entity. A galaxy's journey is not just about internal growth, but also about external forces that shape its destiny. Dark matter and dark energy, two of the universe's most enigmatic components, play critical roles in a galaxy's formation and evolution. Though invisible to the naked eye, these forces exert profound gravitational influence on galaxies, guiding their development and behavior. Dark matter, which makes up around 85% of the universe's mass, is a quiet but powerful force. It doesn't emit, absorb, or reflect light, making it impossible to detect with conventional observational methods. But even though it's hidden, it's far from passive. Dark matter acts as the very scaffold upon which galaxies are built. In the early universe, regions of slightly higher dark matter density acted as gravitational wells, pulling in normal matter and allowing proto-galaxies to form. Without dark matter, galaxies would lack the gravitational pull needed to hold their stars, gas, and dust together. Observations of galaxy rotation curves, where galaxies spin faster than expected based on their visible mass, provide strong evidence that these invisible dark matter halos are essential for holding galaxies intact. The influence of dark matter doesn't end there. When galaxies collide, their dark matter halos pass through one another with minimal disruption. This is because dark matter interacts primarily through gravity rather than electromagnetism, which allows it to seamlessly navigate through the collision. In fact, dark matter can actually accelerate the rate at which galaxies merge, altering the size, shape, and structure of the resulting galaxies. It's as if dark matter is subtly orchestrating the evolution of the universe's most massive structures. The largest structures in the universe, such as galaxy clusters, owe their existence to dark matter. It binds together hundreds, even thousands of galaxies into colossal gravitationally bound groups, forming the largest cosmic structures that we can observe. These clusters are not just fascinating objects in their own right, they're also a testament to the power of dark matter's influence. On the other hand, dark energy plays a different yet equally significant role in shaping the universe. While dark matter pulls things together, dark energy drives them apart. It's thought to be responsible for the accelerated expansion of the cosmos, a process that has been ongoing ever since the Big Bang. Dark energy's influence on galaxy formation and structure is more subtle, but it is no less profound. Its effects are woven into the fabric of space-time itself, pushing galaxies further apart as the universe continues to expand. Together, dark matter and dark energy form the invisible backbone of the universe. They shape galaxies, drive their evolution, and influence every aspect of the cosmos's grand narrative. The universe, it seems, is not only sculpted by the visible forces we can see, but also by the unseen powers that lurk just beyond our detection. And as we continue to explore the vast cosmic expanse, we uncover more about these mysterious forces that define the very structure and destiny of the galaxies. In the vast expanse of the universe, it's theorized that dark energy plays a pivotal role in the accelerated expansion that has been confirmed through the observation of distant supernova and the cosmic microwave background radiation. While this expansion might seem to have a broad and global impact, its effects ripple across the universe, particularly influencing the galaxies. As the universe expands at an ever-increasing rate, the gravitational pull between galaxies weakens. This gradual weakening means that future mergers and interactions between galaxies are less likely to occur, shaping the destiny of the cosmic neighborhood. Moreover, dark energy is integral to the large-scale structure of the universe, shaping the cosmic web that connects clusters of galaxies and the vast voids between them. Together with dark matter, dark energy forms the unseen foundation upon which the universe is built. Dark matter, by providing the invisible mass that holds galaxies together, and dark energy, driving the expansion of the universe, create create the cosmic dynamics we observe today. These enigmatic forces are fundamental in understanding the intricate dance of galaxies and their role in the grand architecture of the universe. Among the many galaxies that dot the universe, the Andromeda Galaxy, also known as M31, stands out as a key player in our cosmic neighborhood. Located approximately 2.5 million light-years away from the Milky Way, it is the closest spiral galaxy to our own and one of the largest members of the local group, which includes about 54 galaxies. Andromeda's importance is not only due to its sheer size and proximity, but also because of the impending collision between it and the Milky Way, an event that will reshape both galaxies in profound ways. Andromeda, slightly larger than the Milky Way, contains over 1 trillion stars, vastly more than the Milky Way's 200 to 400 billion stars. This immense mass allows Andromeda to exert significant gravitational influence over the local group. As these two massive galaxies draw nearer to each other, driven by their mutual gravitational pull, they are converging at a speed of about 70 kilometers per second. This colossal collision is expected to occur in roughly 5 billion years, and will likely result in the merging of both galaxies into a single, larger elliptical galaxy. This future galaxy has already been nicknamed Milkomeda, Milkdromeda, or Milkdromeda, reflecting the union of the two. While the collision may sound catastrophic, there's no need to fear. The vast emptiness between the stars means that direct stellar collisions will be exceedingly rare. Instead, the merger will trigger dramatic gravitational interactions that will profoundly transform the structure of both galaxies. Their spiral forms will be disrupted, potentially leading to the formation of a large elliptical galaxy. Additionally, the supermassive black holes at the centers of both galaxies may eventually merge, releasing gravitational waves detectable across the universe, a testament to the immense power of these cosmic events. Galaxy mergers, such as the one expected between the Milky Way and Andromeda, are not rare in the universe. They play a vital role in the evolution of galaxies, contributing to the formation of new stars and reshaping galactic structures. In the case of Andromeda, its proximity to our galaxy offers astronomers a rare opportunity to study galaxy formation in real time. Observing Andromeda provides invaluable insights into the dynamics of star formation, the behavior of galaxies over time, and how different galaxies evolve based on their environment and internal processes. The Milky Way and Andromeda are like cosmic partners, each reflecting and influencing the other. Their impending collision highlights the fluid and ever-changing nature of the universe. Far from being an event to fear, it is a reminder that nothing in the cosmos is permanent. The fate of the Milky Way and Andromeda will serve as a testament to the dynamic, interconnected web of the universe. And though the future of these two galaxies may seem uncertain, the constant movement and transformation of the cosmos ensures that there is always something new to discover. As galaxies collide and merge, they redefine the universe's architecture, proving that on both the largest and smallest scales, change is the only constant in this vast, mysterious expanse we call the cosmos. When galaxies collide, the cosmic ballet between them begins, marked by intricate gravitational forces that shape the destiny of stars, black holes, and the very structure of the galaxies involved. These collisions are far from simple crashes. Instead, they are an elaborate interpenetration of massive cosmic bodies, each star, gas cloud, and even dark matter within the galaxies influencing one another through complex interactions. In the early stages, galaxies do not merely collide as solid objects. They pass through each other in a dramatic and graceful dance. This dynamic engagement can trigger bursts of star formation as immense gas clouds are compressed and ignited, forming new stellar nurseries. The phenomenon, often referred to as a starburst phase, results in dazzling displays of new stars lighting up the regions where the galaxies interact. A striking example of this process can be seen in the Antennae galaxies, where the collision has spurred the birth of numerous new stars, causing the galaxies to shine brighter than they ever could have on their own. These newly formed stars can number in the tens or even hundreds, significantly influencing the luminosity and the evolution of the merging galaxies. The gravitational forces at play cause the original shapes of the galaxies to distort, warping them into unfamiliar, sometimes unrecognizable forms. These tidal forces stretch the galaxies into long, elegant tails, streams of stars and gas expelled into the void of intergalactic space. A similar phenomenon can be observed in systems like the interacting galaxies of the Stephan's Quintet. As the galaxies continue their collision course, the process doesn't end with a simple merging. Instead, their repeated passages through each other gradually dissipate the ordered rotational structures typically found in spiral galaxies. This relentless dance often results in the creation of an elliptical galaxy, a more rounded, less structured form that represents a new chapter in the evolution of the merged cosmic bodies. The supermassive black holes at the hearts of the galaxies may also be drawn together, eventually merging and unleashing gravitational waves that ripple through the fabric of space-time. In some cases, this merger can lead to the formation of powerful quasars or active galactic nuclei that shine so intensely they outshine the combined light of all the stars in their host galaxies. Beyond these spectacular effects, galaxy collisions are also pivotal in shaping the larger structure of the universe. These transformative events play a central role in the hierarchical model of galaxy formation, where smaller galaxies collide and merge to form larger galaxies over vast spans of time. This process explains the incredible diversity of galaxies observed today, from the beautifully structured spirals to the more amorphous and elliptical shapes. In galaxy clusters, the gravitational interactions between colliding galaxies can also affect the distribution of dark matter and intergalactic gas, significantly altering the dynamics of the entire cluster. Moreover, the remnants of these colossal collisions, new galaxies formed from the merging of older ones, along with the vast streams of stars and gas ejected into space, serve to enrich the intergalactic medium. These materials, forged in the hearts of stars, provide the building blocks for future generations of star formation across the universe. Thus, galaxy collisions are not just destructive, they are vital, creative events that perpetuate the ongoing cycle of cosmic evolution. The collision of galaxies reshapes the very landscape of the universe, driving star formation, altering galactic structures, and facilitating the growth of supermassive black holes. Speaking of black holes, these enigmatic objects have long captivated scientists and stargazers alike. A black hole is a region of space where the gravitational pull is so intense that nothing, not even light, can escape its grasp. These cosmic phenomena are the end result of massive stars, typically around 20 times the size of our Sun, that collapse under their own gravity after exhausting their nuclear fuel. The core of the star compresses to a point where both density and gravity become infinitely large, creating what is known as a singularity. Surrounding this singularity lies the event horizon, a boundary beyond which nothing can escape, rendering black holes essentially invisible to direct observation. Despite their elusiveness, astronomers have developed several clever techniques to detect black holes. One primary method involves observing the behavior of nearby stars and gas clouds. If a star orbits an unseen companion, its motion can reveal the presence of a black hole. The gravitational effects caused by the black hole's immense mass distort the star's orbit, providing a telltale sign of its existence. Another critical method is the detection of X-rays emitted by the accretion disk, a swirling, glowing mass of gas and debris being pulled toward the black hole. As this material is accelerated and heated to extreme temperatures, it emits high-energy radiation just before crossing the event horizon. Recent advancements in gravitational wave astronomy, thanks to observatories like LIGO and Virgo, have also opened a new window into the study of black holes. By detecting the ripples in space-time caused by the collision and merger of black holes, scientists are able to gather invaluable data about these mysterious objects. Through these groundbreaking methods, the once invisible black holes are slowly being revealed, and we are beginning to understand them with greater clarity. The event horizon, the point of no return surrounding a black hole, remains one of the most fascinating and mysterious aspects of these celestial phenomena. It represents a boundary beyond which not even light can escape. The reason for this is tied to the immense gravitational force that governs black holes. This force is so powerful that once matter or radiation crosses the event horizon, it is pulled inexorably inward toward the singularity, forever lost to the universe. To visualize this, imagine space as a stretched fabric, Massive objects like black holes warp this fabric, creating a deep well. The event horizon is the boundary surrounding this well, and just outside of it, the escape velocity required to break free from the black hole's gravity equals the speed of light. Once you cross this boundary, nothing, not even light, can escape. This boundary raises intriguing questions about physics, particularly in the realms of information theory. What happens to information that falls into a black hole? Is it lost forever, or is it preserved in some unknown way? These are questions that continue to puzzle scientists and provoke thought about the fundamental nature of reality itself. The event horizon isn't a physical surface. It's a conceptual boundary that pushes the limits of our understanding of physics, particularly as shaped by the laws of general relativity. Black holes, those enigmatic and mesmerizing objects of the cosmos, come in three primary categories, each with its own formation process and mass, revealing the awe-inspiring diversity of these space phenomena. Let's embark on a journey to explore these mysterious objects in greater detail. First, we have stellar black holes. These are the most common type and are born from the death of massive stars. Typically, stars around 20 times heavier than our sun meet their fate when they run out of nuclear fuel. Unable to resist the inward pull of gravity, the core collapses under immense pressure, and a stellar black hole is formed. These black holes generally possess a mass ranging from a few solar masses to several tens of solar masses, but their creation is just the beginning of their captivating story. Then there are the supermassive black holes, giants that dominate the centers of most galaxies, including our own Milky Way. These titans can have masses ranging from millions to billions of times that of our sun, and yet their exact formation process remains one of the greatest mysteries in astrophysics. Some theories suggest that these massive objects grow through the merger of smaller black holes, while others propose that they formed by the rapid accumulation of gas and stellar material in the early universe. Regardless of how they came to be, these supermassive black holes are not just passive giants. They have a profound impact on their host galaxies. They regulate star formation and even shape the overall structure of the galaxy, influencing everything from stellar dynamics to the formation of galactic clusters. Lastly, there are the elusive intermediate mass black holes, a class that lies somewhere between the stellar and supermassive varieties. These black holes have masses ranging from 100 to 100,000 solar masses and are particularly difficult to detect. Their formation mechanisms are not fully understood, but they are believed to arise from the merging of smaller black holes or the direct collapse of massive gas clouds. Although elusive, their existence is crucial for understanding the evolutionary bridge between stellar black holes and the supermassive ones. By studying these intermediate black holes, scientists hope to unlock the secrets of how black holes grow and evolve throughout the universe, offering new insights into the larger cosmic picture. Each of these black hole types, from the relatively small stellar black holes to the gargantuan supermassive ones, speaks to the incredible complexity and dynamism of the universe. They each tell a story of cosmic evolution, revealing the astonishing ways in which matter and energy interact under the most extreme conditions imaginable. But black holes are not the only cosmic oddities that captivate scientists and stargazers alike. Another object that continues to intrigue is the neutron star. A neutron star is one of the densest objects in the universe, emerging from the explosive aftermath of a supernova. Imagine a sphere with a diameter of only about 12 miles, yet containing a mass 1.5 to 2 times that of our sun. This stellar remnant is left behind when a massive star, typically between 8 to 20 times the mass of our sun, runs out of nuclear fuel and undergoes a gravitational collapse. As the core contracts under the immense force of gravity, the outer layers are expelled in a supernova explosion, sending material into space. But the core, in a spectacular display of extreme physics, continues to collapse, with protons and electrons combining to form neutrons due to the crushing pressure. The result is a neutron-rich core that stabilizes into a neutron star, an object so dense that a sugar cube-sized piece of neutron star material would weigh as much as all of humanity combined. Neutron stars also possess magnetic fields of astonishing strength and rotate at incredible speeds. In fact, some of them are observed as pulsars, rotating neutron stars that emit beams of electromagnetic radiation from their magnetic poles. These pulsars flash at incredibly regular intervals, creating one of the most precise cosmic clocks known to science. The study of neutron stars not only provides insights into the extreme physics of stellar remnants, but also raises profound questions about the nature of matter and gravity. As we continue to peer into the depths of space, neutron stars remain among the most fascinating objects in the universe, offering a glimpse into the future of stars and the mysteries of our cosmos. In the end, the existence of black holes and neutron stars underscores the complexity and wonder of our universe. Each type, whether black hole or neutron star, challenges our understanding of space and time, urging us to push the boundaries of science and explore the unknown. Their formation processes, their impacts on the universe, and the mysteries they hold promise to keep scientists captivated for generations to come. These celestial objects serve as natural laboratories, offering a rare glimpse into the most extreme conditions of the universe. For instance, the composition and state of matter inside a neutron star are subjects of vigorous scientific inquiry, intertwining fields from quantum mechanics to general relativity. The study of these dense remnants not only fuels our understanding of fundamental forces, but also helps refine our comprehension of the behavior of matter at densities far exceeding anything encountered on Earth. The research surrounding these stellar objects brings us face to face with the edge of physics, pushing the boundaries of knowledge about the universe's most enigmatic entities. Pulsars and magnetars are specialized types of neutron stars, each showcasing an incredible diversity of behaviors and characteristics that make these objects stand out among the cosmos's most extreme phenomena. Pulsars, for instance, are neutron stars that emit beams of radiation from their magnetic poles. As these stars rotate, and assuming their magnetic poles aren't aligned with their rotational axis, the emitted radiation sweeps across space like the focused beam of a lighthouse. If one of these beams points toward Earth, we detect it as regular pulses of radiation, hence the name pulsar. The pulsations of these objects can occur at remarkably regular intervals, ranging from milliseconds to seconds, making pulsars some of the universe's most precise natural clocks. The precision of these pulses has allowed astronomers to use them for testing the fundamental laws of physics, including general relativity. Pulsars are more than just mysterious stars. They are crucial tools in our ongoing quest to unravel the universe's deepest secrets. Magnetars, on the other hand, represent a more extreme subset of neutron stars, distinguished by their extraordinarily strong magnetic fields, thousands of times more powerful than those found in typical neutron stars or even pulsars. These magnetic fields can be up to 1 quadrillion times stronger than Earth's own magnetic field. Magnetars tend to rotate relatively slowly, with rotation periods ranging from a few seconds to several minutes, which distinguishes them from the rapidly spinning pulsars. These intensely powerful magnetic fields result in dramatic surface activity, often leading to violent outbursts manifested as intense bursts of X-rays and gamma rays. These high-energy emissions can disrupt the star's crust, composed of ultra-dense neutron-rich matter, triggering phenomena like starquakes and further bursts of energy. Through their powerful emissions, magnetars offer a unique window into the understanding of magnetic fields and high-energy astrophysics, challenging current theories of these forces. Both pulsars and magnetars, with their contrasting behaviors, enrich our understanding of neutron stars, providing key insights into the extreme environments and fundamental physics governing these dense remnants. Among the myriad of black holes and neutron stars discovered, a few have garnered particular renown due to their unique properties, historical importance, or groundbreaking science they facilitated. One of the most famous black holes is Cygnus XX1, located in the constellation Cygnus about 6,000 light-years from Earth. Discovered in the early 1970s, Cygnus X1 was one of the first strong candidates for a black hole. This binary system includes a blue supergiant star and its compact companion, the black hole, which emits powerful X-rays as it accretes matter from the supergiant. The discovery of Cygnus X1 was pivotal in solidifying the concept of black holes in astrophysics, proving their existence beyond theoretical constructs, and marking a significant breakthrough in our understanding of the universe's most mysterious objects. In the world of neutron stars, the Crab pulsar stands as one of the most iconic. Located at the heart of the Crab Nebula, this pulsar is the remnant of a supernova explosion recorded by Chinese astronomers in 1054 AD. The Crab pulsar rotates 30 times per second, emitting pulses of radiation across various wavelengths, including radio waves, optical light, X-rays, and gamma rays. It is one of the most intensely studied pulsars, offering a wealth of information about pulsar wind nebula, magnetic fields, and the mechanics of supernova remnants. The Crab pulsar continues to provide vital clues about the life cycles of stars and the energy dynamics of the universe, making it an invaluable subject of study in modern astrophysics. Together, pulsars, magnetars, and black holes form a rich tapestry of celestial phenomena that challenge our understanding of physics and deepen our knowledge of the cosmos. They not only illuminate the extreme environments that shape the universe, but also provide the scientific community with natural laboratories for studying the laws of physics under the most unimaginable conditions. The synchronization of observations across different electromagnetic spectrum bands has made the Crab pulsar a cornerstone in multi-wavelength astronomy. This celestial object, a rapidly rotating neutron star, sends out regular pulses of energy in various wavelengths from radio to X-rays. Its study has provided significant insights into the behavior of neutron stars and the extreme environments they inhabit, allowing scientists to observe the interaction between matter and intense magnetic fields. The Crab pulsar remains a vital tool for exploring the physics of pulsars, offering a unique laboratory for understanding the fundamental laws of nature. Similarly, another monumental black hole is Sagittarius A, the supermassive black hole residing at the center of our Milky Way galaxy. Invisible to optical telescopes, its presence is inferred by observing the rapid orbits of nearby stars. These stars move in ways that suggest they are being strongly influenced by a massive unseen object. Through radio and infrared observations, astronomers have mapped these stellar orbits, which confirm that the black hole has an astounding mass, approximately 4 million times that of the Sun. This discovery has opened a window into the study of supermassive black holes, providing critical insights into their role in galaxy formation and evolution. Sagittarius A is not just a cosmic curiosity, it is a cornerstone of modern astrophysics, shaping our understanding of how galaxies evolve and the forces that govern their dynamics. On the topic of neutron stars, one of the most significant discoveries in astrophysics was made with PSR B1919+21, the first pulsar ever detected. Discovered in 1967 by Jocelyn Bell and Anthony Hewish, its periodic radio pulses were initially interpreted as signals from extraterrestrial intelligence. However, further investigation revealed that it was a rapidly rotating neutron star emitting beams of radio waves. This discovery was revolutionary, as it marked the beginning of a new era in astrophysical research. Neutron stars, with their intense magnetic fields and high rotational speeds, have become a key focus for studying the extreme physics of matter. The discovery of PSR B199+21 opened new avenues for research, including the behavior of matter in these dense objects and the physical processes that govern them. These famous black holes and neutron stars are not just objects of cosmic fascination. They are fundamental to advancing our understanding of stellar evolution, gravitational theory, and the extreme states of matter. Through them, we can probe the deepest questions about the universe, challenging and expanding the limits of modern physics. They offer a glimpse into the most extreme conditions in the universe, from the crushing gravity of black holes to the incredible density and magnetic fields surrounding neutron stars. Each discovery brings us closer to understanding the very nature of the cosmos and the forces that shape it. In contrast, the Big Bang Theory remains the prevailing cosmological model explaining the origin of the universe. According to this model, the universe began approximately 13.8 billion years ago from an incredibly hot, dense state and has been expanding ever since. It is crucial to note that the term Big Bang does not refer to an explosion in the traditional sense. Rather, it marks the origin of space-time itself. The event that sparked the expansion of the universe led to the creation of all matter and energy that exists today. Though the term Big Bang was coined somewhat pejoratively by British astronomer Fred Hoyle, it has become widely accepted as the name for this groundbreaking cosmological model. One of the strongest pieces of evidence supporting the Big Bang theory is the cosmic microwave background, CMB, radiation, first detected in 1965 by Arno Penzias and Robert Wilson. The CMB is a faint glow that permeates the entire universe, believed to be the afterglow of the Big Bang itself. It provides a snapshot of the infant universe just 380,000 years after its birth, offering crucial insight into the early stages of cosmic development. The CMB is remarkably uniform, with tiny fluctuations that correspond to the seeds of all current cosmic structures, galaxies, stars, and planets. Another key piece of evidence comes from the observation of the redshift of galaxies, first described by Edwin Hubble. Hubble found that galaxies appear to be moving away from us, with their light shifting toward the red end of the spectrum. This redshift is a direct indication that space itself is expanding, aligning with the predictions made by Albert Einstein's theory of general relativity. When this expansion is traced backward, it implies that the universe was once far more condensed. The observation of the redshift has become one of the most compelling pieces of evidence for the expanding universe model, showing that the cosmos has been stretching and evolving since its inception. The Big Bang theory also finds support in the abundance of light elements such as hydrogen, helium, and traces of lithium. These elements were formed during the first few minutes after the Big Bang, when temperatures and pressures were so high that nuclear reactions could occur, creating the primordial elements in the exact quantities observed today. This process, known as Big Bang nucleosynthesis, provides further validation for the theory, as the observed abundance of these elements matches the predicted values. Taken together, these lines of evidence provide a comprehensive framework for understanding the universe's origin and its subsequent evolution. The Big Bang theory not only explains current observations, but also continues to guide new discoveries. It has transformed our understanding of the cosmos, providing the foundation for many of the most exciting developments in modern cosmology and astrophysics. Through this model, scientists are piecing together the history of the universe from its explosive birth to its ongoing expansion. And as we continue to explore the depths of space, the Big Bang theory remains the cornerstone of our understanding of the universe's vast and mysterious nature. As it evolves over billions of years, determining the age and size of the universe relies on a sophisticated blend of observational astronomy, theoretical physics, and advanced mathematical modeling. One of the fundamental techniques to measure its age involves studying the cosmic microwave background radiation, CMB, which is often described as the oldest light in the universe. This relic radiation, a remnant from the Big Bang, was first detected by Arno Penzias and Robert Wilson in 1965. It serves as a direct window into the early universe. By carefully analyzing the tiny fluctuations in the CMB, scientists can infer crucial cosmological parameters such as the rate of expansion of the universe, commonly known as the Hubble constant. Microwave observatories like the Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck satellite have provided incredibly precise measurements of these fluctuations, leading to the most accurate estimates of the universe's age. Current calculations suggest the universe is approximately 13.8 billion years old. Another key approach to estimating the universe's age involves studying the oldest known star clusters, specifically globular clusters. These densely packed groups of ancient stars provide a lower bound for the universe's age. By determining the age of the oldest stars within these clusters, astronomers can refine the age derived from the CMB data. Understanding stellar evolution and nucleosynthesis is essential in determining the ages of these stars. These stellar age estimates are in close agreement with the calculations based on the CMB, further confirming the universe's age as several billion years old. This corroborates the results derived from cosmic background studies, forming a solid foundation for our understanding of the universe's timeline. Measuring the size of the universe, especially the observable universe, is closely intertwined with understanding its expansion. Edwin Hubble's groundbreaking observation that galaxies are receding from us, more distant galaxies moving faster, paved the way for estimating the cosmic scale. The Hubble constant, which quantifies this expansion rate, is critical in calculating distances across the cosmos. Modern techniques, such as using Type 2a supernovae as standard candles, refine the value of the Hubble constant. Type 2a supernova, a type of exploding star, have intrinsic brightness that is well understood, making them perfect tools for distance measurement. Additionally, baryon acoustic oscillations, BAO, which are periodic fluctuations in the density of visible baryonic matter, provide another key cosmic ruler. By combining the Hubble constant with the current age of the universe, scientists can estimate the size of the observable universe. Since light travels at a finite speed, looking out into space is also looking back in time. Thus, the observable universe forms a sphere around us with a radius of about 93 billion light-years. This figure is far larger than what would be expected by simply multiplying the age of the universe by the speed of light, as space itself continues to expand. These integrated methods, examining the CMB, star clusters, supernovae, and cosmic expansion, allow scientists to piece together a remarkably accurate picture of both the age and size of the universe. This research offers profound insights into the cosmos's observable boundaries and its dramatic history. The cosmic microwave background, CMB, is more than just a faint microwave radiation filling the entire universe. It is the afterglow of the Big Bang, presenting itself as a pervasive radiation that was discovered accidentally by Arno Penzias and Robert Wilson in 1965. This CMB represents the residual heat left over from the universe's first moments, dating back to approximately 380,000 years after the Big Bang. During this period, the universe had cooled enough for protons and electrons to combine into neutral hydrogen atoms, making the universe transparent and allowing light to travel freely for the first time. The CMB serves as a snapshot of the universe at this infant stage. Its significance to cosmology cannot be overstated. The near-perfect uniformity of the CMB, with temperature variations of only about 1 part in 100,000, aligns perfectly with predictions from the Big Bang model, which posits that the early universe was homogeneous and isotropic. These minute temperature fluctuations are far from random. They represent the seeds of all current cosmic structures, galaxies, stars, and planets, indicating areas of slightly varying densities that gradually grew over billions of years. Detailed measurements of the CMB, particularly from missions like WMAP and the Planck satellite, have provided a treasure trove of cosmological data. These observations have allowed scientists to refine the values of several critical cosmological parameters, such as the Hubble constant, the universe's rate of expansion, and the density of ordinary matter, and dark energy. By meticulously analyzing the CMB, scientists have also been able to determine the universe's age with remarkable precision, currently estimated at around 13.8 billion years. Moreover, the CMB has revealed evidence of cosmic inflation, a rapid expansion of the universe that occurred immediately after the Big Bang. Information encoded in the temperature and polarization patterns of the CMB supports this inflationary model, providing valuable insights into the universe's first fractions of a second. These groundbreaking studies open up exciting avenues for understanding fundamental physics, exploring energies far beyond what we can currently achieve in laboratory experiments. The continuous pursuit of knowledge in this field allows scientists to not only confirm key cosmological theories, but also to deepen our understanding of the universe's origins, evolution, and ultimate fate. As we continue to explore these cosmic mysteries, we unlock even more profound questions about the nature of reality itself, pushing the boundaries of human understanding ever further into the vast and uncharted expanse of the cosmos. Cosmic background radiation, an essential signature of the universe's birth, serves as an invaluable relic, offering a whisper of the explosive origins of the cosmos and its ongoing evolution. This faint glow, known as the cosmic microwave background, CMB, is more than just a faint echo. It is a cosmic fossil, frozen in time, revealing the earliest moments of the universe. The CMB presents a detailed roadmap of the universe's formation, an imprint from the Big Bang that continues to guide our understanding of the cosmos, tracing its journey from a hot, dense state to the vast, complex structure we observe today. This radiation, is the backdrop against which all of modern cosmology is measured, offering clues to the conditions of the early universe. By studying the patterns of this radiation, scientists can peer back in time to when the universe was just a few 100,000 years old, providing insight into its birth and evolution. These faint signals are critical not only in understanding the universe's origins, but also in shaping future astrophysical research. As our tools and techniques improve, the cosmic relic continues to reveal new layers of information, ensuring that it remains an indispensable part of the scientific quest to comprehend the universe. But the study of the universe's expansion doesn't stop there. Scientists employ multiple techniques to measure the rate at which the universe is stretching, focusing particularly on distant galaxies and the light they emit. The redshift phenomenon, first systematically studied by Edwin Hubble in the 1920s, is one of the most fundamental ways to track this cosmic expansion. As galaxies move away from us, their light gets stretched due to the expansion of space, shifting it toward the red end of the electromagnetic spectrum. This redshift, detectable through spectroscopic techniques, can be quantified by comparing the light emitted from galaxies to the known wavelengths of elements in the laboratory. The amount of redshift is directly proportional to a galaxy's velocity and distance, providing scientists with a measurable indicator of how fast galaxies are receding from us. This, in turn, gives a direct measurement of the rate of expansion of the universe. The relationship between a galaxy's velocity and its distance from Earth is encapsulated in Hubble's law, where the Hubble constant h serves as the key to understanding this expansion. Through Hubble's law, we can calculate the velocity v of a galaxy based on its distance d from us, with h squared being the proportionality constant, v equals h out d. To measure this constant with precision, astronomers need accurate distance measurements to far-off galaxies. This is achieved through methods such as the use of standard candles. One such standard candle is the type Ia supernova, a stellar explosion with a consistent intrinsic brightness. By comparing the known luminosity of these supernovae to their observed brightness, astronomers can calculate the distance to the galaxies they inhabit. By combining the distances of these supernovae with their redshifts, scientists can refine the value of the Hubble constant, offering a clearer understanding of the rate at which the universe is expanding. In addition to redshift and standard candles, another crucial avenue for understanding the universe's expansion lies in the study of cosmic background radiation, CMB. This afterglow of the Big Bang, uniform across the sky but with tiny temperature fluctuations, holds vital clues about the early conditions of the universe. Space missions such as the Wilkinson Microwave Anisotropy Probe, WMP, and the Planck satellite have mapped these fluctuations with unparalleled precision. By studying these variations in temperature, scientists can extract key parameters about the universe's structure, including its geometry and the rate at which it has been expanding over time. The data collected from the CMB bolsters measurements made through the study of distant galaxies and supernovae, offering a more complete and cohesive picture of the universe's expansion history. Each of these observations, whether from the redshift of galaxies or the delicate fluctuations in the CMB, reinforces our understanding of how the cosmos has evolved from its chaotic beginnings into the vast, organized structure we observe today. Finally, scientists turn to baryon acoustic oscillations, BAO, as a tool for measuring cosmic distances. BAO refers to periodic fluctuations in the density of visible matter caused by sound waves propagating through the early universe. These sound waves, which left their imprint on the distribution of galaxies, serve as a cosmic ruler, helping astronomers measure the scale of the universe at various stages of its evolution. By mapping these oscillations across the cosmos, scientists can determine distances with remarkable precision, further refining our understanding of the universe's expansion rate. These complementary methods, redshift, the CMB, supernova, and BAO, combine to form an intricate framework that allows us to trace the history of the universe's expansion. With each breakthrough and each new mission, we move closer to understanding the true nature of the cosmos, and ultimately, the profound origins that have shaped everything we see today. As we continue to explore these cosmic phenomena, we come closer to answering the ultimate question: How did we get here, and what lies ahead in this ever-expanding universe? In the vast expanse of the cosmos, one of the most fundamental and intriguing questions is about the ultimate fate of the universe. For centuries, astronomers have been striving to unlock the secrets behind the vastness of space and its continuous evolution. To do this, they've developed increasingly sophisticated methods to measure and track the expansion of the universe. One of the most crucial breakthroughs has come from refining the distance measures necessary to calculate this expansion rate. These techniques, using observations of distant galaxies, supernovae, cosmic background radiation, and large-scale cosmic structures, form the backbone of our understanding of space's constant stretching since the Big Bang. These approaches don't stand in isolation. Instead, they work together, converging to offer an evolving and intricate picture of the universe's expansive nature. By combining these observations, astronomers are able to piece together how space itself has been growing and evolving, shaping the very universe we inhabit today. Yet despite the advancements in understanding, the ultimate fate of the universe remains one of the most profound questions in cosmology. And it continues to spark scientific debate and speculation. One of the leading theories on the universe's end is the Big Freeze. The freeze, also known as heat death. This scenario relies heavily on the mysterious force of dark energy, which is thought to be responsible for the accelerating expansion of the universe. Should this accelerated expansion continue unchecked, galaxies would eventually drift further apart, isolating them from one another. Over billions, or even trillions of years, this would reduce interactions, halting galaxy mergers and star formation. As time progresses, stars will run out of their nuclear fuel, and no new stars will be born. The universe will slowly be left in a state dominated by cold, dark remnants, white dwarfs, neutron stars, and black holes. These remnants will slowly lose energy, and even black holes may eventually evaporate through a process known as Hawking radiation. The result? A cold, sparse universe filled only with low-energy photons and elementary particles, a state of inactivity and extreme cold where all the energy once present has been dispersed. But there's another theory that contrasts sharply with the Big Freeze, the Big Crunch. This hypothesis posits that the universe's expansion might one day halt and reverse. If the gravitational pull of matter, including the elusive dark matter, becomes stronger than the repulsive force of dark energy, the universe will begin to contract. Galaxies will be drawn toward each other, increasing the density and temperature throughout the cosmos. Eventually, the universe could collapse into a singular point, akin to the conditions of the Big Bang. This scenario suggests the possibility of a cyclic universe where expansion and contraction occur repeatedly in an endless loop. The universe, it seems, could be in a perpetual cycle of birth, death, and rebirth. Building on the idea of cyclic expansion and contraction, some theorists propose the Big Bounce. This theory suggests that after the universe reaches a dense, collapsed state similar to the Big Crunch, quantum gravitational effects could cause a rebound, an explosive release of energy that leads to another Big Bang, and thus another cycle of expansion. This theory merges the principles of quantum mechanics with general relativity to offer an explanation of the universe's behavior at extreme densities, where traditional physics breaks down. The Big Bounce offers a fascinating glimpse into a universe that continually renews itself, offering an eternal, self-regenerating cosmos. Another, more dramatic possibility is the Big Rip, a scenario rooted in certain models of dark energy, particularly one known as phantom energy. This form of dark energy grows stronger over time, eventually overpowering all other forces in the universe. In this model, as dark energy's influence intensifies, it could tear apart galaxies, stars, planets, and even atomic nuclei. The fabric of space itself would be ripped apart, and every form of matter would be obliterated. The Big Rip predicts a catastrophic end where the force driving the universe's expansion becomes so powerful that nothing can withstand it, leading to the complete disintegration of everything in existence. Finally, there's the heat death, often confused with the Big Freeze, but differing in its emphasis on thermodynamic equilibrium. This scenario predicts that the universe will reach a state of maximum entropy, where energy is uniformly distributed and no differences in temperature remain. At this point, no processes or work can occur, as there will be no energy gradients to drive them. The universe will become a featureless, lifeless expanse, the thermodynamic arrow of time having reached its inevitable conclusion. Each of these theories presents a unique vision of the universe's end, influenced by our current understanding of dark energy, dark matter, and the intricate dynamics of space itself. As astronomers continue to refine their measurements and observations, the answer to this cosmic riddle may come into sharper focus, unveiling the destiny of the universe in ways we've yet to imagine. Theories about dark matter and dark energy continue to evolve, reshaped and refined as our understanding deepens. With advancements in observational technologies such as the James Webb Space Telescope, JWST, and gravitational wave detectors, the cosmos holds more secrets than we could have ever imagined. These groundbreaking tools will play a pivotal role in narrowing down models and providing greater clarity on one of the most profound questions of all, the universe's ultimate fate. Dark matter and dark energy are not just speculative ideas. They are integral to the universe's very structure. And as we unravel these enigmatic forces, we are not just exploring cosmic mysteries, we are reimagining the fabric of reality itself. Dark matter, one of the most elusive substances in the universe, has captivated the scientific community. Its presence is inferred not by sight, but by its gravitational effects on visible matter, radiation, and the large-scale structure of the universe. For decades, scientists have studied the rotational curves of galaxies as one of the first signs of dark matter's existence. When astronomers observe the rotation speeds of stars, particularly those on the outskirts of galaxies, they find that they are moving much faster than predicted by the visible mass alone. This unexpected motion points to an invisible gravitationally bound mass, dark matter. Further evidence emerges from gravitational lensing, where light from distant galaxies bends around massive galaxy clusters. The degree of bending far exceeds what would be expected from visible matter, once again suggesting the presence of dark matter. Yet, detecting dark matter directly remains an immense challenge. To overcome this, scientists have designed highly sensitive detectors placed deep underground to shield them from cosmic rays and other background radiation. These experiments, including the Cryogenic Dark Matter Search, CDMS, and the Xenon Dark Matter Experiment, strive to detect rare interactions between dark matter particles and normal matter. Additionally, particle accelerators like the Large Hadron Collider, LHC, aim to generate dark matter particles through high-energy collisions, pushing the boundaries of our understanding even further. On the other hand, dark energy, an even more mysterious force, is believed to be the cause behind the accelerated expansion of the universe. Its existence was first hinted at in the 1990s, when astronomers observed that distant supernovae appeared dimmer than expected, suggesting that the rate of the universe's expansion is increasing rather than slowing down. Incredibly, dark energy accounts for approximately 70% of the universe's total energy content, yet its true nature remains one of the most profound mysteries in science. To study dark energy, astronomers employ various methods, with one of the most significant being the observation of large-scale structures like galaxy clusters and cosmic voids. Surveys such as the Sloan Digital Sky Survey, SDSS, and the Dark Energy Survey, DES, map out the distribution of these structures to track how they evolve over time. Another crucial tool in understanding dark energy is the cosmic microwave background, CMB radiation. Instruments like the Planck satellite provide a detailed map of the CMB, allowing scientists to infer both the universe's geometry and its expansion history. Additionally, the study of baryon acoustic oscillations, BAO, sound waves from the early universe imprinted in the galaxy distribution, offers important insights into the rate of expansion influenced by dark energy. Looking to the future, missions like the upcoming Euclid satellite and the JWST promise to provide unprecedented data on dark matter and dark energy. These missions, combined with ground-based observatories such as the Vera-C Rubin Observatory's Legacy Survey of Space and Time, LSST, will deliver comprehensive sky surveys, which will be instrumental in our quest for understanding the universe's mysterious forces. Moreover, these observational efforts are supported by theoretical work aiming to integrate dark matter and dark energy into the frameworks of particle physics and general relativity. The study of dark matter and dark energy is not just about exploring the unknown, it is about pushing the boundaries of human understanding. By combining observations, experiments, and theoretical insights, scientists continue to challenge the limits of what we know about the universe, gradually piecing together the vast, intricate puzzle of its composition and ultimate destiny. As our knowledge of dark energy and dark matter expands, it finds itself intertwined with another exciting field: the search for exoplanets, or planets outside our solar system. Since the first confirmed detection of exoplanets in 1992, orbiting the pulsar PSR B1257+12, our ability to discover and study these distant worlds has advanced at an extraordinary pace. Thousands of exoplanets have now been cataloged, each offering a unique glimpse into the diversity of planetary systems across the cosmos. The methods used to detect exoplanets are as varied as the planets themselves. One of the most effective techniques is the transit method, where astronomers monitor the brightness of a star over time. When an exoplanet passes directly between its star and the observer, it causes a temporary dimming of the star's light. By measuring this dimming, astronomers can determine the planet's size, orbital period, and even some of its atmospheric properties. NASA's Kepler Space Telescope revolutionized this method by discovering over 2,000 confirmed exoplanets, observing a fixed field of stars and detecting the tiny dips in brightness caused by planetary transits. Another widely used technique is the radial velocity or Doppler method, which measures the wobble of a star caused by the gravitational pull of an orbiting planet. As the star moves toward and away from us, its light shifts in color, a phenomenon known as the Doppler effect. By analyzing these shifts with precision spectrometers, scientists can determine the mass and orbit of the exoplanet. Ground-based telescopes, such as those using the HARP spectrograph in Chile, have been crucial in detecting exoplanets through this method. Gravitational microlensing presents yet another fascinating technique for discovering exoplanets. In this method, the gravitational field of a massive object, like a star, bends the light from a background star. If a planet orbits the intervening star, it can cause a temporary brightening of the background star's light, a phenomenon known as a microlensing event. This method is particularly useful for finding planets at great distances, even in systems located thousands of light years away. Though precise alignments are required, microlensing is often used in conjunction with other methods to pinpoint distant exoplanets. Direct imaging is an increasingly important method for studying exoplanets, especially larger ones that are far from their parent stars. This technique involves capturing images of the planets by blocking out the intense light from their stars, often using instruments like coronagraphs or star shades. Advances in adaptive optics and technology have made it possible to directly image exoplanets, offering insights into their atmospheres and characteristics. The upcoming James Webb Space Telescope is poised to push the limits of direct imaging, enabling scientists to study exoplanet atmospheres in unprecedented detail. In the years to come, as these groundbreaking methods and technologies continue to evolve, we will unlock more secrets about exoplanets. Each discovery, whether large or small, brings us closer to understanding the complex dynamics of planetary systems beyond our own, and perhaps the possibility of finding life in distant worlds. Astrometry measures the precise changes in a star's position in the sky caused by the gravitational influence of an orbiting planet. Though less commonly used due to the need for extraordinarily accurate measurements, astrometry remains an incredibly powerful tool for detecting planets, particularly those with longer orbital periods. These methods, whether used individually or in combination, allow scientists to characterize exoplanets by determining their masses, radii, orbital distances, and atmospheric compositions. Each new discovery helps to expand our understanding of planetary formation and the potential for habitability, bringing us closer to answering one of humanity's most profound questions: is there life beyond our solar system? With missions like NASA's TESS, Transiting Exoplanet Survey Satellite, and the James Webb Space Telescope, alongside upcoming projects such as ESA's Plato, planetary transits and oscillations of stars, the search for exoplanets continues to captivate the world of modern astronomy. These groundbreaking missions are pushing the boundaries of our knowledge, and with each new advancement, the possibility of finding life elsewhere seems ever more tangible. Scientists utilize several sophisticated techniques to detect exoplanets, each tailored to reveal different aspects of a planet's characteristics. These methods capitalize on the subtle yet powerful effects planets exert on their host stars. One of the most successful and widely employed methods is the transit technique. This method involves observing a star's light and detecting periodic dips in brightness caused by a planet passing directly between the star and the observer. When this happens, the planet momentarily blocks a portion of the star's light, resulting in a detectable reduction in brightness. These transits can reveal vital details about a planet's size and orbital period. NASA's Kepler Space Telescope has identified over 2,000 confirmed exoplanets using this technique. By further analyzing the way the star's light changes as it filters through the planet's atmosphere during a transit, scientists can also infer the chemical makeup of that atmosphere, detecting gases like hydrogen, helium, and water vapor, key indicators of potential habitability. Another cornerstone technique in the search for exoplanets is the radial velocity method, also known as the Doppler method. This method relies on the gravitational tug between a star and its orbiting planet. As a planet orbits, its gravitational pull causes the star to shift in position, albeit by a very small amount, resulting in shifts in the star's spectral lines. These shifts are detectable through the Doppler effect. When the star moves toward Earth, its light is blue shifted. When it moves away, it is red shifted. High-precision spectrometers, such as the HARPS High-Accuracy Radial Velocity Planet Searcher at the La Silla Observatory in Chile, can measure these minute shifts in velocity with remarkable accuracy. This method not only helps determine a planet's minimum mass, but also provides insight into the eccentricity of its orbit. Then there is gravitational microlensing, a fascinating technique that takes advantage of the gravitational field of a star to magnify the light from a more distant background star. When these stars align perfectly, the gravitational lensing effect can reveal a planet's presence. If a planet orbits the foreground star, it can cause a noticeable anomaly or blip in the light curve. This is known as a microlensing event. This technique is particularly adept at detecting planets that are far from their host stars, including those in systems thousands of light years away, which might otherwise be missed by traditional methods. In the thrilling quest to understand our universe, the study of exoplanets remains a frontier of unparalleled excitement. Through each of these advanced techniques, scientists are revealing new worlds, some of which might just hold the secrets to life beyond Earth. As technology improves and new missions are launched, the field of exoplanet research will continue to evolve, inching ever closer to uncovering the mysteries of distant planets and the possibility of life elsewhere in the cosmos. Direct imaging is a technique that involves capturing visual or infrared images of distant planets. By strategically blocking out the light from their host stars, usually with the help of tools like coronagraphs or star shades to minimize the star's glare, scientists can peer deeper into the cosmos and observe planets that would otherwise be too faint to detect. Despite the challenges, especially considering how dim planets are compared to their blinding stars, recent advancements in adaptive optics and the deployment of space telescopes have revolutionized this method, making it increasingly viable for planetary research. This method is not just about capturing images, it's about unlocking the mysteries of exoplanet atmospheres and even weather patterns. By analyzing the light that planets emit or reflect, scientists can gather detailed data on their atmospheric composition, surface conditions, and even signs of potential habitability. Direct imaging also provides valuable insights that go beyond just a planet's appearance, allowing us to glimpse the dynamic processes at play on these distant worlds. With technological innovations, this once daunting method has become a cornerstone in the growing field of exoplanet research. Astrometry, on the other hand, is the study of the precise movements of stars. By detecting the tiny wobbles caused by the gravitational pull of orbiting planets, astronomers can infer the presence of planets that might be otherwise undetectable. While the technique demands extraordinarily high precision because the positional changes are so minuscule, astrometry is invaluable for detecting massive planets in wide orbits, even though it's less commonly used due to the technological hurdles it presents. Interestingly, these methods often work in tandem. For instance, planets detected through the transit or radial velocity methods can be further studied using direct imaging or by analyzing their atmospheres during transits. Together, these techniques form a multi-layered approach that allows scientists to gather more comprehensive data, piecing together the puzzle of planetary systems beyond our own. As missions like NASA's TESS, Transiting Exoplanet Survey Satellite, the James Webb Space Telescope, JWST, and ESA's Plato, planetary transits and oscillations of stars provide increasingly detailed observations, our ability to detect, study, and understand exoplanets has reached new heights. The future of exoplanet research is brimming with promise, opening new frontiers in the search for extraterrestrial life. The habitability of an exoplanet hinges on several key factors, with the most critical being its potential to support liquid water, an essential ingredient for life as we know it. Central to this is the exoplanet's location within its star's habitable zone, often referred to as the Goldilocks zone, where conditions are just right for liquid water to exist. Not too hot and not too cold. The exact distance of this zone from the star varies depending on the star's type and luminosity. For example, around a sun-like star, the habitable zone stretches roughly from 0.95 to 1.37 astronomical units AU from the star, with 1aing the distance from Earth to the Sun. For smaller, cooler stars like M-dwarfs, the habitable zone is much closer. Finding an exoplanet within the habitable zone is a significant step in assessing its potential for life. However, size and composition also matter. Ideally, a potentially habitable exoplanet should be Earth-sized, meaning its radius and mass are similar to our own planet. This suggests that the planet may have a rocky surface, as opposed to being a gas giant. Planets that are too large may accumulate thick hydrogen-helium atmospheres, making them more akin to Neptune or Jupiter than Earth. Conversely, planets much smaller than Earth could struggle to retain a substantial atmosphere, which is vital for maintaining liquid water and protecting life from harmful stellar radiation. Another critical factor is the planet's atmosphere. A planet's atmosphere regulates its surface temperature through the greenhouse effect, distributes heat, and provides essential gases that could support biological processes. For an exoplanet to be truly habitable, it needs to maintain an atmosphere that is stable enough to support life. This includes a balance of gases like oxygen, carbon dioxide, and nitrogen, which are essential for biological processes. Moreover, a stable atmosphere can also help protect potential life from harmful radiation emitted by the host star, adding another layer of complexity to the search for life beyond Earth. As we continue to explore the cosmos with ever more sophisticated tools and techniques, the prospect of finding a habitable exoplanet, and possibly even life, becomes increasingly within reach. The future of exoplanet exploration promises to be a thrilling journey into the unknown, expanding our understanding of the universe and our place within it. In the vast expanse of the universe, there lies a thrilling mystery, the search for exoplanets, planets that orbit stars beyond our sun, where life as we know it might one day thrive. But what makes a planet truly habitable? A crucial element is its atmosphere, thick enough to trap heat, yet not so dense as to create a runaway greenhouse effect, like the one suffocating Venus. This delicate balance is one of the key factors in determining whether life could ever find a foothold on a distant world. Water vapor, carbon dioxide, and traces of gases like methane and oxygen are all indicators that can signal a planet's potential to harbor life. These elements are the building blocks of life on Earth, and their presence on another world is one of the first clues scientists look for. The most cutting-edge telescopes and spectrometers allow scientists to peer into the depths of these distant atmospheres, unlocking secrets hidden within the starlight. During an exoplanet's transit, when it passes in front of its host star, powerful instruments can capture this light, filtering it through the planet's atmosphere. As the light passes through, it interacts with the molecules in the atmosphere, leaving behind subtle clues known as absorption lines. These fingerprints reveal a planet's atmospheric composition, offering tantalizing glimpses of what might be present: water vapor, carbon dioxide, methane, or even the more mysterious substances. By studying these spectral signatures, scientists can piece together a picture of a world far beyond our reach. But the search doesn't end with atmospheric analysis. Direct imaging is another exciting technique, although more challenging. Imagine being able to take a photograph of a distant exoplanet as it orbits its star. Instruments like the James Webb Space Telescope, JWST, and the Extremely Large Telescope, ELT, use adaptive optics and coronagraphs to block out the blinding glare of the star, allowing the faint light of the planet to shine through. This breakthrough in technology makes it possible to study the reflected light of an exoplanet, revealing crucial details about its temperature, weather patterns, and, importantly, its potential habitability. Yet, the search for habitable planets goes beyond the chemistry of their atmospheres. The nature of the star that these planets orbit plays a pivotal role in determining whether life could ever exist. Stars that are too volatile, those prone to frequent, intense solar flares, can strip away a planet's atmosphere, leaving it exposed to harsh radiation. Such conditions make it nearly impossible for life to thrive. On the other hand, stars like our Sun, stable and long-lived, offer the perfect environment for life to flourish. Even cooler stars, like M dwarfs or red dwarfs, have their advantages. Despite their dimmer and cooler nature, they boast incredibly long lifespans and have habitable zones closer to their surface, increasing the chances of life. However, their propensity for flares poses a significant risk, casting doubt on their ability to support life in the long term. In addition to the star, the planet's axial tilt and orbital eccentricity play important roles in shaping its climate. A planet's axial tilt affects its seasons, while its orbital eccentricity, the shape of its orbit, can influence the severity of these seasons. A stable climate is essential for life to thrive, and even small shifts in these factors could make the difference between a livable world and a barren one. Moreover, the presence of a magnetic field acts as a shield, protecting the planet's atmosphere from the harsh solar winds and cosmic radiation that would otherwise strip it away. Some planets stand out as particularly promising candidates. Proxima Centauri b, for example, orbits within the habitable zone of the closest star to our Sun. Then there's the TRAPPIST-1 system, a wonder of exoplanet discovery with 7 Earth-sized planets, several of which reside in the star's habitable zone. These worlds are tantalizingly close to our grasp, and with the help of new missions and the latest in telescope technology, the potential for life on these planets seems within reach. The next generation of space telescopes, such as the James Webb Space Telescope, JWST, and the Extremely Large Telescope, ELT, are poised to provide deeper insights into these distant worlds. With their advanced instruments, they'll analyze exoplanet atmospheres with unprecedented precision, searching for potential biosignatures, chemical markers that could indicate the presence of life. As these telescopes scan the skies, astronomers are not just looking for signs of alien life, but also searching for clues that might reveal new ways of thinking about habitability, forcing us to rethink what it means for a world to support life. The search for habitable exoplanets is far from straightforward. It is a complex dance of many factors: atmosphere, star stability, axial tilt, magnetic field, and more, each contributing to the delicate balance that may one day support life. And as we continue to make strides in our understanding, the dream of finding another Earth among the stars draws ever closer. In the end, this quest to explore distant worlds may not just answer the question of whether we are alone in the universe, but also redefine the very nature of life itself. As astronomers look out into the vastness of space, hundreds of light years away, they are not just studying distant planets, they are peering into our future, into a time when humanity may look to the stars not only for answers, but also for a place to call home. In the vast stretches of space, one of the most intriguing and promising candidates for the search of extraterrestrial life is Proxima Centauri b, an Earth-sized planet orbiting within the habitable zone of Proxima Centauri. This star, the closest to our Sun at a mere 4.24 light-years away, has captured the imagination of scientists and dreamers alike. Discovered in 2016, Proxima Centauri b's position in the habitable zone allows for the possibility of liquid water on its surface, an essential ingredient for life as we know it. Ongoing observations aim to unravel the mysteries of its atmosphere, surface conditions, and its potential for harboring life, making it an especially tantalizing target in humanity's quest for otherworldly neighbors. But Proxima Centauri b is not alone in the universe. Another exciting set of worlds lies within the TRAPPIST-1 system, where 7 Earth-sized exoplanets orbit an ultra-cool dwarf star located just 39 light-years away. Among these planets, 3, TRAPPIST-1e, TRAPPIST-1f, and TRAPPIST-1g, exist within the habitable zone, the region where liquid water could potentially exist. The orbits of these planets are so tight that a year on one could last only a few Earth days. Spectroscopic studies have already begun to provide vital insights into the atmospheric composition of these exoplanets. Their size, density, and proximity to their host star suggest that they may host liquid water, offering a glimmer of hope for the potential of life. The TRAPPIST-1 system has become a natural laboratory, providing an invaluable opportunity for scientists to study exoplanetary atmospheres and assess whether life could exist beyond Earth. In the broader search for life, the Drake equation stands as a remarkable intellectual tool, guiding our understanding of the vast unknown. Devised by astrophysicist Frank Drake in 1961, this equation seeks to estimate the number of active, communicative extraterrestrial civilizations within our Milky Way galaxy. It serves as a framework to break down the complexities of the search for extraterrestrial intelligence, SETI, into manageable factors. These factors include the rate of star formation in the galaxy, the fraction of stars that host planets, and the likelihood of planets in these systems being capable of supporting life. The equation goes further, considering the chances of life developing intelligence and, eventually, technologies capable of interstellar communication. Despite some factors remaining speculative, especially concerning the emergence of life and the development of intelligence, the equation remains a vital tool for scientists. As our understanding of the cosmos advances through new discoveries, the factors within the Drake equation are refined, allowing scientists to adapt and expand their search for other civilizations. Missions like Kepler, which have provided valuable data on exoplanets, continue to inform the equation, shedding light on the profound and existential question: are we alone in the universe? With each step forward, the quest driven by the Drake equation grows ever more intricate and ambitious, continuing to evolve with the expanding boundaries of human knowledge. The Apollo missions stand as monumental milestones in the annals of human achievement, their echoes resonating through time as some of the most extraordinary feats in the history of space exploration. Apollo 11's iconic landing on the moon in 1969 marked a watershed moment, one that forever etched itself into the collective memory of humanity. On that historic day, astronauts Neil Armstrong and Buzz Aldrin became the first humans to set foot on another celestial body. Their accomplishment, a remarkable testament to human ingenuity and perseverance, showcased the boundless potential of mankind when it dares to dream the impossible. Armstrong's famous words, "That's one small step for man, one giant leap for mankind," still reverberate today, symbolizing the significance of this unprecedented venture. But the Apollo program was far more than a symbolic act of planting a flag and leaving footprints on the moon. It ushered in an era of scientific discovery with over 840 pounds of lunar rocks, soil, and cores brought back to Earth. These invaluable treasures fundamentally transformed our understanding of the moon's composition, revealing intricate details of its geological history. Yet, the missions were not merely about reaching and returning from the moon. They embodied the power of scientific exploration and technological advancement, showcasing humanity's potential to push the boundaries of knowledge and discovery. The technological innovations driven by Apollo were far-reaching. The Saturn V rocket, the most powerful rocket ever built, successfully propelled astronauts beyond Earth's gravity, making the impossible possible. But the Apollo missions also contributed significantly to advancements in computing, engineering, and even materials science. The scientific experiments left behind on the lunar surface, seismometers, retroreflectors, and more, provided invaluable data about the moon's internal structure and its interaction with Earth. Apollo 12 through Apollo 17 continued the legacy, expanding the scope of lunar exploration. Extended surface explorations, the deployment of scientific instruments, and the introduction of the lunar roving vehicle allowed astronauts to travel farther from their landing sites, deepening our understanding of the moon's surface and unlocking new realms of possibility. These groundbreaking achievements laid the groundwork for contemporary space exploration, serving as an enduring source of inspiration. They showcase the remarkable possibilities that arise when human ambition and scientific inquiry intertwine, creating an unstoppable force driving humanity's thirst for exploration. The Apollo program left behind not just footprints on the moon, but a legacy of exploration that would inspire generations to come. And yet the legacy of Apollo did not fade into the past. It evolved. The International Space Station, ISS, stands today as one of the most significant milestones of global collaboration and scientific inquiry. Orbiting Earth approximately 250 miles above the surface since 1998, the ISS serves as an invaluable platform for conducting experiments that would be impossible under Earth's gravity. Through long-duration missions, scientists have been able to study the effects of microgravity on the human body, gaining crucial insights into muscle atrophy, bone density loss, and fluid shifts within the body. These findings have led to the development of countermeasures that will be vital for future astronauts who embark on extended journeys to Mars and beyond. But the ISS is not confined to biology alone. It has become a laboratory for a diverse range of scientific disciplines. In physics, the microgravity environment has enabled the exploration of phenomena like fluid dynamics and combustion, unlocking new ways to study basic principles of matter. Instruments aboard the station have monitored cosmic rays, searched the universe for dark matter, and observed Earth's atmosphere, oceans, and land surfaces, providing critical data to track climate change and natural disasters. The ISS has not only contributed to groundbreaking scientific discoveries, but also fostered unprecedented international collaborations, strengthening diplomatic ties among the countries involved. Through these collaborations, technological advancements have been made, further demonstrating the unity that space exploration can inspire. Looking ahead, the ISS remains a beacon of scientific progress and a crucial stepping stone for the future exploration of deeper space. Its continued presence in low Earth orbit offers unparalleled opportunities for studying both the human body and the world beyond our planet. The insights gained from this work will be vital for humanity's next great journey to the moon, Mars, and beyond. As we set our sights even further, the Mars rovers Curiosity and Perseverance represent the vanguard of humanity's quest to unravel the mysteries of the Red Planet. Launched by NASA, these advanced robotic explorers are tasked with delving into Mars's history and assessing its potential to have hosted life. Curiosity, which landed in Gale Crater in 2012, has focused on investigating whether Mars ever had the environmental conditions capable of supporting microbial life. Equipped with a suite of cutting-edge scientific instruments, Curiosity has been analyzing rock and soil samples for organic compounds and other chemical indicators of habitability. Its groundbreaking discoveries, such as the detection of ancient riverbeds and the identification of complex organic molecules, provide compelling evidence that Mars may have been hospitable to life billions of years ago. Building upon Curiosity's achievements, Perseverance, which touched down in Jezero Crater in 2021, dives even deeper into the search for signs of past life. Equipped with even more sophisticated technology and instruments, Perseverance is tasked with exploring the Martian surface in ways never before attempted. It seeks not only to uncover the planet's history, but also to understand how its environment might have supported life in its ancient past. In this age of scientific discovery, humanity's ability to explore the farthest reaches of space stands as a testament to the power of human curiosity and ambition. With each step, whether it be Armstrong's first footfall on the moon or Perseverance's search for signs of life on Mars, we are pushing the boundaries of what is possible. These missions, past, present, and future, represent the relentless pursuit of knowledge that will continue to shape the future of space exploration for generations to come. One of the primary missions of NASA's Perseverance rover on Mars is to collect soil and rock samples that could harbor biosignatures, potential traces left by ancient microbial life. These samples are not just for mere collection. They are intended to be returned to Earth in a future mission where they will undergo detailed laboratory analysis. In addition to this groundbreaking mission, Perseverance is equipped with cutting-edge technology designed to study the planet's geology and climate. Its objective is not only to explore Mars' surface, but also to scout out potential landing sites for future human missions. But that's not all. Perseverance has a remarkable companion, Ingenuity, a small helicopter that has already proven that powered flight on another planet is possible. This technological marvel opens new doors for aerial exploration, offering a vantage point that has never been available before on Mars. Together, these two explorers are doing far more than just advancing our scientific knowledge. They are laying the foundation for the eventual human exploration of the Red Planet. Each breakthrough discovery brings us closer to understanding Mars in unprecedented detail, transforming our view of this mysterious world one finding at a time. On the other side of the solar system, the twin Voyager spacecraft have been on a different kind of journey, one that has taken them far beyond the planets into the uncharted reaches of interstellar space. Launched in 1977, the Voyager missions were initially designed for a grand tour of the outer planets, with the goal of capturing data from Jupiter, Saturn, Uranus, and Neptune. The Voyagers delivered astonishing close-up images of these distant worlds, providing humanity with a deeper understanding of their characteristics. Voyager 1 and Voyager 2 revealed Jupiter's swirling rings, the mesmerizing atmospheres of Saturn and Neptune, and the volcanic activity on Io, one of Jupiter's moons, discoveries that changed the way we view our solar system. As if these planetary explorations weren't enough, both Voyager spacecraft have traveled far beyond the planets, entering interstellar space. They are now the first human-made objects to leave the heliosphere, the protective bubble of solar wind that surrounds our solar system. Even in this vast, silent expanse, the Voyagers continue to transmit valuable data back to Earth, shedding light on the interstellar medium and the space beyond our sun's influence. These missions not only deepen our understanding of the solar system, but also push the boundaries of human knowledge, forever altering how we perceive our place in the galaxy. Meanwhile, the New Horizons mission, launched in 2006, epitomizes a singular quest to explore Pluto and the Kuiper belt. After a nearly decade-long journey, New Horizons made its closest approach to Pluto in 2015, revealing stunning images and data that radically changed our perception of this distant dwarf planet. Pluto, once considered a mere icy rock, is now understood to have a rich geological landscape, with towering mountains and vast plains of nitrogen ice. This discovery challenged previous assumptions about how such a cold and distant world could look. Riding on the success of its Pluto flyby, New Horizons was then directed toward a secondary target in the Kuiper belt, a celestial object known as Aurokoth. This flyby, completed in 2019, offered humanity a rare glimpse into the early solar system, showing a primordial world with a smooth, unblemished surface that has remained largely unchanged for billions of years. These discoveries not only satisfy our curiosity, but also serve as critical pieces in understanding the building blocks of our solar system. Both the Voyager and New Horizons missions stand as testaments to humanity's insatiable curiosity. They represent the boundless quest for knowledge that drives us to explore the farthest reaches of space. These spacecraft have delivered invaluable scientific data and have illuminated the vast, unexplored frontiers that await us in the cosmos. Each milestone in their journeys is a reminder of the immense possibilities that space exploration holds, and how far we can push the boundaries of human achievement. As we look to the future, the next generation of space missions promises to build on these extraordinary accomplishments. NASA's Artemis program, aiming to return humanity to the moon, is an ambitious step toward exploring and colonizing space. By the mid-2020s, NASA plans to land the first woman and the next man on the lunar surface. But the real objective lies in the long-term vision of establishing a sustainable human presence on the moon by the end of the decade. The Lunar Gateway, a space station in orbit around the moon, will serve as a critical hub for future lunar missions. Scientists aim to study the moon's surface and its potential resources, like water ice buried in the permanently shadowed craters at the poles. These resources could be used for life support and fuel, making lunar habitation not just a dream, but a viable reality. Beyond this, lunar missions will delve into understanding the moon's geology, its origins, and its history, providing clues about the early solar system and the formation of Earth itself. The moon is more than just a destination. It's a testing ground for the technologies needed for deeper space exploration, including the life support systems required for missions to Mars. As humanity sets its sights on the red planet, Mars missions will ask even more profound questions, not just about the planet's potential to support life, but about our own existence in the universe. The challenges ahead are monumental, but so too are the possibilities for discovery and advancement. Humanity's journey to the moon, Mars, and beyond is not just about exploration for its own sake. It is a transformative process that shapes our understanding of the cosmos and our place within it. With each new mission, we unlock more of the universe's mysteries, propelling us toward the next great frontier in the endless expanse of space. Future missions led by NASA, along with private companies like SpaceX, are setting their sights on Mars as the next frontier for human exploration. These groundbreaking missions will build on the accomplishments of robotic pioneers like Curiosity and Perseverance. Rather than just sending machines to study the red planet, these missions are laying the groundwork for human colonization by developing advanced habitats capable of withstanding Mars's extreme conditions. The focus will be on mastering in situ resource utilization, which includes extracting water from the Martian soil and producing oxygen. Equally important is the creation of sustainable energy solutions, which are critical for long-term human survival on the planet. The scientific goals of Mars missions are just as ambitious. Researchers are looking for definitive evidence of past or present life on Mars, a quest that involves studying its climate, geology, and history in minute detail. This will require drilling deep into the Martian surface and returning samples to Earth for extensive analysis. By understanding Mars's atmospheric evolution and surface changes over millions of years, scientists hope to uncover clues to the planet's past habitability. These missions not only aim to answer fundamental questions about the planet itself, but also serve to prepare humanity for the day we might live on another world. This quest represents a bold step towards safeguarding the future of our species, ensuring that we are not confined to a single planet. Each leap forward on Mars is a monumental step toward becoming an interplanetary civilization. Fueled by the spirit of exploration and an insatiable thirst for knowledge, these missions will serve as the bedrock for human presence beyond Earth. Space telescopes such as the Hubble Space Telescope and the James Webb Space Telescope, JWST, are revolutionizing our understanding of the universe. Their ability to peer deep into the cosmos has offered groundbreaking views of galaxies, nebulae, and distant stars, insights that ground-based observatories simply cannot provide. Since its launch in 1990, the Hubble Space Telescope has captured breathtaking images of faraway galaxies and nebulae, unveiling the universe's secrets. Among its many discoveries, Hubble confirmed the accelerated expansion of the universe, a groundbreaking finding that led to the theorization of dark energy as the driving force behind this expansion. Hubble's ability to observe the universe in ultraviolet, visible, and near-infrared wavelengths has given us a profound understanding of stellar life cycles and galaxy formation. Its observations of the early universe have also allowed astronomers to study the formation of the first galaxies and stars, shedding light on the conditions that existed shortly after the Big Bang. The launch of the James Webb Space Telescope in December 2021 marked a new era in cosmic exploration. Operating primarily in the infrared spectrum, JWST can peer through dense cosmic dust clouds, revealing parts of the universe that were previously obscured. One of its primary missions is to observe the first light-emitting objects formed in the early universe and investigate the evolution of the first galaxies. Its advanced instruments allow scientists to study the atmospheres of exoplanets in incredible detail, looking for signs of potentially habitable conditions or even biosignatures that could suggest the presence of life. JWST will also play a pivotal role in understanding star and planet formation. By observing the molecular clouds where new stars and planetary systems are born, it will offer unparalleled insights into the processes that give rise to planets, and potentially to life itself. Through high-resolution spectral analysis, JWST will explore the chemical compositions of these regions, bringing us closer to understanding how the building blocks of life are formed and how planetary systems evolve. The collaboration between space agencies and private companies promises not only to answer the mysteries of our solar system, but also to reveal the deeper truths of our universe, transforming how we see our place in the cosmos. Together, Hubble and the James Webb Space Telescope, JWST, form an extraordinary duo, each equipped with its own specialized abilities that perfectly complement one another. Their combined power has revolutionized our understanding of the cosmos, offering humanity a glimpse into the vast and enigmatic universe like never before. This partnership has expanded the very boundaries of what we thought we knew, propelling us toward new frontiers in astronomical discovery. One of the most mind-boggling elements of this exploration is the discovery of dark matter, an invisible and mysterious force that plays a vital role in the structure of the universe, yet remains almost completely undetectable by traditional telescopes. While invisible to our instruments, dark matter exerts its influence through its gravitational effects, bending the very fabric of space-time itself. It is one of the most crucial components of the universe, making up approximately 27% of the total mass and energy content. But despite its dominance in the cosmic order, it has remained a puzzle. To put it into perspective, the ordinary matter that makes up stars, planets, and galaxies accounts for a mere 5% of the universe, while the remaining 68% is made up of another mysterious force, dark energy, which causes the universe's accelerated expansion. Understanding dark matter alongside its elusive counterpart is essential to grasp the full picture of the cosmos, and this has been humanity's ongoing pursuit for nearly a century. The discovery of dark matter traces its roots back to the 1930s when astronomer Fritz Zwicky first observed something strange. He noticed that galaxies in the Coma cluster were moving at speeds that defied explanation, based on the mass that was visible. This anomaly led to the hypothesis of an unseen force, later identified as dark matter. But it wasn't until the 1970s that Vera Rubin's groundbreaking work on the rotation curves of spiral galaxies confirmed Zwicky's theory. Rubin demonstrated that the outer regions of galaxies were rotating far faster than could be explained by the visible matter alone. This, she argued, was clear evidence that some unseen mass, later termed dark matter, was exerting the necessary gravitational pull to hold galaxies together. In modern cosmology, dark matter serves as a scaffolding for the formation of structure in the universe. During the early stages of cosmic evolution, dark matter clumped together under gravity, forming what we now refer to as the cosmic web. This web serves as the foundation for galaxy formation. Without it, the universe would look drastically different. Galaxies, clusters, and superclusters would not have formed in the way we observe today. Dark matter's effects can also be observed in gravitational lensing, a phenomenon in which light from distant objects is bent by the gravitational field of massive objects, like galaxy clusters. This bending reveals hidden regions of dark matter, allowing scientists to map its distribution across the universe. However, despite years of research and numerous hypotheses, including the possibility of weakly interacting massive particles, WIMPs, and axions, the precise nature of dark matter remains unknown. Unveiling its true identity could unlock critical gaps in the standard model of particle physics, potentially offering a glimpse into some of the deepest and most profound mysteries of existence. At the heart of this mystery lies dark energy, a force that works in opposition to gravity, pushing the universe to expand at an accelerating rate. Unlike dark matter, which has a noticeable gravitational effect, dark energy appears to defy gravity. First discovered in the late 1990s through observations of distant type Ia supernovae, dark energy now constitutes around 68% of the universe's mass energy content. Researchers study this enigmatic force primarily through observational cosmology, employing several techniques to measure its effects. A key approach involves the use of type Ia supernovae as standard candles. These exploding stars have a known intrinsic brightness, allowing scientists to measure distances across vast cosmic expanses. By comparing the observed brightness to the redshift of these supernovae, astronomers can gauge the rate of the universe's expansion. The surprising results? Galaxies are moving away from each other faster than ever before, confirming the presence and influence of dark energy. The interplay between dark matter and dark energy shapes the universe in ways we are only beginning to understand. Together, they represent the unseen forces that govern the cosmos, guiding the formation of galaxies, stars, and the very structure of the universe itself. As we push the boundaries of space exploration with advanced telescopes like Hubble and JWST, our quest to unlock the secrets of dark matter and dark energy grows ever more urgent. For in these cosmic mysteries may lie the answers to some of the universe's most profound questions. This surprising discovery hinted at the presence of an unknown force actively counteracting gravity, which would later be termed dark energy. But how can we learn more about this elusive entity? One of the most powerful methods is studying the cosmic microwave background, CMB radiation, the afterglow of the Big Bang. By analyzing detailed measurements of the CMB conducted by missions like the Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck satellite, scientists have uncovered a treasure trove of data. This data illuminates the conditions of the universe during its early moments and its subsequent evolution. Variations in the CMB provide insights into the universe's geometry, composition, and expansion history, underscoring the profound impact of dark energy on cosmic evolution. Another significant approach lies in large-scale structure surveys. These surveys, including groundbreaking projects like the Sloan Digital Sky Survey, SDSS, and the Dark Energy Survey, DES, map the distribution of galaxies across vast cosmic distances. This allows astronomers to track the evolution of cosmic structures over time and how dark energy shapes them. One particularly invaluable tool is baryon acoustic oscillations, BAOs, which are periodic fluctuations in the density of visible matter. BAOs act like a cosmic ruler, allowing scientists to measure the scale of cosmic structures and observe how dark energy influences the expansion rate of the universe at various stages of its history. On the theoretical side, dark energy sparks a rich and ongoing dialogue within the field of fundamental physics. One dominant theory posits that dark energy is a property of space itself, encapsulated by the cosmological constant lambda found in Einstein's equations of general relativity. However, other theories suggest that dark energy is a dynamic field, sometimes referred to as quintessence, which evolves over time. Some more radical ideas even propose that modifications to gravity at cosmic scales could account for this mysterious force. These varied theoretical approaches, when combined with observational data, create a multifaceted understanding of dark energy, even as its true nature remains one of the universe's greatest mysteries. As we look to the future, upcoming missions like the James Webb Space Telescope, JWST, and the Wide Field Infrared Survey Telescope, WIRST, are poised to offer even deeper insights into the cosmos. These missions hope to gather more detailed observational data that could help unlock the secrets of dark energy, inching us ever closer to a comprehensive understanding of the forces that shape our universe. But dark energy is not the only mystery unraveling in the cosmos. Gravitational waves, ripples in the very fabric of space-time itself, were first predicted by Albert Einstein in 1916 as a consequence of his general theory of relativity. According to Einstein, massive objects that accelerate, such as binary neutron stars, black holes, or supernovae, disturb space-time, generating waves that propagate outward at the speed of light. These waves carry energy away from their source, offering a new way to observe the universe, independent of traditional electromagnetic radiation. The first direct detection of gravitational waves occurred on September 14, 2015, thanks to the Laser Interferometer Gravitational Wave Observatory, LIGO. This monumental discovery confirmed the existence of gravitational waves and opened a new era in astrophysics. LIGO detects these waves using a technique called laser interferometry. The observatory consists of two identical facilities, one in Livingston, Louisiana, and the other in Hanford, Washington. Each facility features two 4 kilometers long arms arranged in an L shape, with high-powered lasers splitting into 2 beams that travel down these arms, reflecting off mirrors at the ends. When a gravitational wave passes through Earth, it stretches and compresses space, causing tiny changes in the distance between the mirrors. These minuscule alterations, on the order of 1,000th of a proton's diameter, create an interference pattern, signaling the presence of a gravitational wave. The first ever detected event, GW150914, originated from the merger of 2 black holes roughly 1.3 billion light-years from Earth. These black holes, with masses 29 and 36 times that of the Sun, spiraled together and eventually merged into a single, more massive black hole. This cataclysmic event released an extraordinary amount of energy in the form of gravitational waves, providing direct evidence for the existence of binary black hole systems and their mergers. Since then, gravitational wave astronomy has blossomed with numerous detections, including the famous neutron star merger GW170817, which was observed in both gravitational waves and electromagnetic signals. This event marked the dawn of multi-messenger astronomy, a new era of observing the universe through multiple types of signals. Continued advancements, including upgrades to LIGO and the addition of other detectors like Virgo in Italy and Kagra in Japan, promise to deepen our understanding of the cosmos. These developments may soon reveal unknown astrophysical processes and offer fresh insights into the fundamental nature of gravity itself. However, the universe still holds other perplexing phenomena. Fast radio bursts, FRBs, are one of the most mysterious and enigmatic signals discovered in modern astrophysics. These brief but powerful bursts of radio waves last only a few milliseconds, yet in that fleeting moment, each burst can release as much energy as the Sun emits over the course of an entire day. The origin of these bursts remains largely unknown, but their intense energy output and rapid duration challenge our current understanding of astrophysical processes. These discoveries, from the detection of dark energy and gravitational waves to the mystery of fast radio bursts, are propelling us into an exciting new era of cosmic exploration. As we continue to probe these cosmic phenomena, we inch closer to solving some of the universe's most profound mysteries, potentially unlocking the keys to the very fabric of space and time. Since its discovery in 2007, fast radio bursts, FRBs, have captivated the scientific community. Dozens of these enigmatic signals have been identified, and with each new discovery, the questions surrounding their origins and underlying mechanisms have only deepened. One of the primary challenges that scientists face in studying FRBs is pinpointing their exact origin. While some of these bursts are one-time events, others, such as FRB 121102, have been observed to repeat, suggesting the possibility of multiple sources or mechanisms at play. The identification of repeating FRBs has led to significant breakthroughs in our understanding, including the localization of one repeating source to a star-forming region in a dwarf galaxy located approximately 3 billion light-years away. This discovery provides valuable clues, yet it still leaves many hypotheses on the table, ranging from highly magnetized neutron stars known as magnetars to the dramatic collapse of black holes. Some even speculate that the signals could be the result of extraterrestrial civilizations harnessing powerful energy sources. Another tantalizing mystery in the realm of cosmic signals is the WOW signal, which was detected in 1977 by the Big Ear radio telescope. This intense, non-repeating narrowband radio signal exhibited the characteristics of an artificial origin, sparking widespread speculation about potential intelligent communication from extraterrestrial beings. Despite multiple follow-up efforts, no similar signals have ever been detected, leaving the origin of the WOW signal an unresolved enigma. These unexplained phenomena challenge our current astrophysical models and push the limits of our observational capabilities. The study of FRBs has the potential to significantly enhance our understanding of the intergalactic medium. As radio waves travel through space, they interact with electrons, causing dispersion and delaying the arrival times of different frequencies. By analyzing this dispersion, scientists can gain crucial insights into the density and distribution of intergalactic matter. This provides a novel tool to probe the cosmos on a large scale, offering a deeper understanding of the universe's structure. Moreover, the investigation of these mysterious signals has driven the development of more advanced detection methods and instruments. Radio telescopes like CHIME, Canadian Hydrogen Intensity Mapping Experiment, ASCAP, Australian Square Kilometre Array Pathfinder, and others are leading the charge in monitoring the sky for elusive bursts. Their efforts have not only increased the detection rate of FRBs, but also enabled the creation of a more detailed catalog, advancing radio astronomy and data analysis techniques in the process. In some ways, FRBs and other unexplained cosmic signals are more than just fascinating phenomena. They serve as catalysts for scientific and technological progress, expanding our understanding of the universe and potentially unveiling new insights into the fundamental principles of physics. As we continue to explore these enigmatic signals, we find ourselves on the frontier of astrophysical research, where every breakthrough could potentially reshape our comprehension of the universe. One such concept that could be profoundly impacted is the theory of parallel universes and the multiverse. This speculative idea suggests that our universe might be only one of many distinct, possibly infinite universes. Several theories support the existence of these parallel worlds, each proposing different aspects of physics and cosmology. One prominent theory is the many worlds interpretation, MWI, of quantum mechanics, first proposed by physicist Hugh Everett in 1957. According to MWI, every quantum event with multiple possible outcomes causes the universe to split into separate branches, each representing a different outcome. For example, if a particle has a 50-50 chance of being in one of two states, the universe would split into two, with each branch realizing one of the states. This implies that every conceivable outcome of every event occurs in some world, leading to an enormous, possibly infinite number of parallel universes, each with its own distinct history and future. Another theory that supports the multiverse concept comes from inflationary cosmology, specifically the theory of eternal inflation formulated by physicist Alan Guth and others. This theory posits that the rapid expansion of space following the Big Bang did not cease uniformly. While some regions of space stopped inflating and formed distinct universes like our own, other regions continued to inflate, leading to the formation of bubble universes, each potentially governed by different physical constants and properties. These bubble universes could never interact with each other, making their detection incredibly difficult. However, this theory suggests that an incredibly diverse array of parallel realities exists within an ever-expanding, inflating space. The idea of a multiverse challenges our understanding of the cosmos, pushing the limits of current scientific exploration and leaving open the tantalizing possibility of infinite, unexplored realities. In theoretical physics, string theory introduces an intriguing concept, the landscape multiverse. According to this theory, our universe may not be unique. Instead, it could be just one of many possible configurations of fundamental strings. Each configuration represents a different vacuum state with distinct physical constants. This multitude of configurations creates a landscape, a multiverse where each universe exists under its own set of physical laws, and each could have different particle types, dimensions, and interactions. The potential diversity of these universes suggests an infinite array of possibilities, which could radically alter our understanding of reality. But that's not all. String theory also introduces the brain multiverse, a fascinating idea stemming from certain interpretations of string theory and M theory. Imagine our universe as a three-dimensional brain floating in a higher dimensional space. Other brains could exist parallel to ours, each representing a different universe. These brains might occasionally interact or even collide, leading to extraordinary cosmic events, such as the Big Bang. This theory suggests that the universe we know could be just one piece of a much grander and far more complex cosmos. While empirical evidence for these parallel universes is still elusive, the concept stirs both scientists and philosophers to explore profound questions about existence and the nature of the universe itself. Although these ideas are speculative, they are exciting and open the door to new possibilities. The search for empirical evidence continues, and advancements in theoretical models and observational techniques may one day offer more concrete insights into this mysterious realm. For instance, studying cosmic phenomena like quasars and blazars provides a glimpse into the high-energy universe, offering us crucial information about the cosmos's most energetic processes. Quasars, short for quasi-stellar objects, are among the most luminous and energetic objects in the universe. They were first identified as powerful radio sources in the 1960s, but their true nature soon became clear. Quasars emit radiation across the electromagnetic spectrum from visible light to gamma rays, making them visible across vast cosmic distances. This extreme luminosity is due to the accretion of matter into a supermassive black hole at the quasar's core. As material spirals into the black hole, it forms an accretion disk, converting gravitational energy into electromagnetic radiation, often outshining the entire galaxy. Blazars are a specific subset of quasars. They are unique because their jets point almost directly toward Earth. This alignment causes relativistic beaming, where the light from the jets becomes intensified, making blazars appear even brighter and more variable. There are two primary categories of blazars: BL Lacerti objects, BL-lax and flat-spectrum radio quasars, FSRQs, based on the emissions from these objects. The study of blazars has yielded crucial insights into the formation of jets, particle acceleration, and the interactions between these jets and the interstellar medium. To study these enigmatic objects, astronomers utilize a variety of observational tools that span the entire electromagnetic spectrum. Radio telescopes such as the Very Large Array, VLA, and the Atacama Large Millimeter Submillimeter Array, ALMA, capture the radio emissions of quasars and blazars, helping scientists understand the structure and dynamics of their jets. Optical and ultraviolet observations from ground-based observatories and space telescopes, like the Hubble Space Telescope, shed light on the accretion disk and surrounding regions. Meanwhile, X-ray observatories like Chandra and gamma-ray telescopes, such as the Fermi Gamma-Ray Space Telescope, probe the high-energy emissions, offering clues about particle acceleration mechanisms and energy dissipation in jets. Spectroscopic analysis plays an essential role in this research. By studying the spectra of quasars and blazars, scientists can determine their redshift, revealing the distance and the rate at which the universe is expanding. Spectroscopy also provides crucial information about the chemical composition, velocity, temperature, and density of the material near the supermassive black hole, helping to model the physical conditions in these extreme environments. In addition to observational techniques, theoretical models and numerical simulations help scientists interpret their data. These models simulate the dynamics of accretion disks, magnetic fields, and jet formation processes, deepening our understanding of the underlying physics of quasars and blazars. The synergy between observation and theory is essential for unraveling the complex mechanisms behind these phenomena, ultimately shedding light on the life cycle of galaxies, the growth of black holes, and the evolution of the universe itself. The study of quasars and blazars not only enhances our knowledge of these remarkable cosmic objects, but also offers profound insights into the fundamental processes shaping the cosmos. Through continued exploration, scientists are piecing together a broader and more intricate picture of the universe, one that may challenge everything we think we know about reality. In the vast, mysterious expanse of the universe, the search for life beyond Earth is one of the most profound scientific pursuits. Astrobiology, a fascinating interdisciplinary field, is at the heart of this quest, blending biology, chemistry, physics, and astronomy. The primary goal of astrobiology is to answer some of humanity's most fundamental questions. Are we alone in the universe? How might life adapt to survive in the most extreme environments? From the formation of the first structures in the early universe to the energetic feedback mechanisms that shape the evolution of galaxies, astrobiology tackles these colossal questions by focusing on the origins, distribution, and potential future of life throughout the cosmos. But the journey of discovery is far from straightforward. It spans both Earth-based environments and extraterrestrial realms, guiding researchers to places where life as we understand it could potentially exist. Astrobiologists look to our own solar system, scouring planets and moons in search of clues that might reveal whether life ever existed or continues to thrive beyond Earth. Mars, with its surface chemistry and past evidence of liquid water, has long captured the imagination of scientists. Recent discoveries, such as seasonal methane plumes and dark streaks on the Martian surface, suggest that liquid water might still flow, albeit intermittently, on this red planet. Methane, a key indicator of biological processes, further deepens the mystery. While geological processes could account for its presence, the idea that microbial life may have left its mark on Mars's ancient history and possibly still exists in its subsurface is a tantalizing possibility. But Mars is just one chapter in this cosmic story. The icy moons of Jupiter and Saturn, Europa and Enceladus, respectively, have become some of the most exciting targets in the search for life beyond Earth. Both moons possess subsurface oceans, warmed by tidal forces, creating an environment that could sustain microbial life. Astrobiologists focus on these moons not only for their potential to harbor life, but also for the remarkable similarities they share with some of the harshest environments on Earth, such as hydrothermal vents and acidic hot springs. The study of extremophiles, organisms that thrive in Earth's most hostile conditions, plays a pivotal role in advancing astrobiology. From organisms living in scalding hot springs to those flourishing in the toxic, acidic depths of volcanic vents, extremophiles demonstrate life's astonishing ability to survive and adapt to environments considered inhospitable. These resilient organisms have expanded our understanding of life's potential to survive in extreme conditions, which in turn helps scientists develop better strategies for searching for extraterrestrial life. The discovery of extremophiles thriving in environments such as sulfuric hot springs, deep-sea vents, and even radioactive waste informs the study of distant worlds like Mars and the icy moons of Jupiter and Saturn. By studying extremophiles, researchers have developed novel biosignature detection techniques aimed at identifying signs of life in the atmospheres of distant exoplanets. Understanding the unique metabolic and chemical processes that allow extremophiles to thrive under extreme conditions enables scientists to refine their criteria for detecting life in the most inhospitable environments. This knowledge is invaluable in guiding future missions to distant planets and moons, enhancing humanity's ability to detect and understand extraterrestrial life forms. Astrobiology is not just a field of study, but a journey into the unknown. With each new discovery, we draw closer to understanding the immense possibility of life throughout the universe. Whether it's in the frozen oceans beneath Europa's icy surface, the dark streaks on Mars, or the extraordinary organisms living in Earth's most extreme environments, we are unraveling the mysteries of life beyond Earth. This thrilling frontier promises to deepen our understanding of life, the universe, and our place within it. As the search continues, we stand on the edge of a discovery that could change everything. The universe is vast and filled with possibilities, and with every step, we inch closer to unlocking the secrets of life in the cosmos. The icy moons of Jupiter and Saturn, specifically Europa and Enceladus, stand at the forefront of the search for microbial life beyond Earth. These moons, with their hidden oceans and active geologic processes, offer the most promising environments in our search for life beyond our planet. Europa, one of Jupiter's largest moons, is particularly intriguing due to its thick, icy crust that conceals a vast, global ocean of liquid water. This water remains liquid thanks to the tidal forces exerted by Jupiter's immense gravity, which heats Europa's interior. Observations from the Galileo spacecraft, followed by more recent data from the Hubble Space Telescope, have revealed what could be plumes of water vapor erupting from Europa's surface. This discovery hints at the possibility of a dynamic subsurface ocean beneath the icy shell, an ocean that could harbor life. Enceladus, Saturn's icy moon, has also captured the attention of scientists due to its striking geysers. These geysers, which shoot water vapor, organic molecules, and even salts into space, emanate from the moon's south pole, offering direct evidence of activity in its subsurface ocean. This ocean, much like Europa's, is heated by hydrothermal activity on the seafloor, making Enceladus another prime candidate for microbial life. The presence of liquid water, energy from tidal forces, and chemical building blocks, such as organic molecules, create an environment that is ripe for life, providing the essential ingredients for microbial existence. As such, these moons are key targets for future missions aiming to explore the potential for life beyond Earth. The search for life extends to Mars as well, where missions such as the Perseverance rover are actively studying the planet's geology, climate, and potential biosignatures. Mars, once believed to be a warm, watery world, might have supported life in its distant past. Perseverance is currently examining Jezero Crater, a site thought to have once housed a river delta and lake. By studying sedimentary rocks that could trap organic molecules, the rover aims to uncover any signs of ancient microbial life. The insights gained from these missions are invaluable in advancing our understanding of planetary habitability. Data gathered on Mars on past water activity, organic chemistry, and the planet's ancient climate directly informs our understanding of how life could have developed there and what conditions might support life today. Moreover, the technology developed for Mars missions is contributing to future explorations of Europa, Titan, and beyond. Instruments like the Sample Analysis at Mars, SAM, on the Curiosity rover can detect organic compounds and measure isotopic ratios, helping scientists decipher the planet's ancient environment and its potential for life. These techniques will be instrumental in studying other celestial bodies, such as Europa, where the upcoming Europa Clipper mission will assess the moon's habitability. Similarly, the Dragonfly mission to Titan, Saturn's largest moon, will explore its organic-rich atmosphere and surface, looking for signs of chemical processes that could be related to life. Each of these missions adds layers of insight, refining our search and approach for detecting life and enhancing our understanding of where and how to look for life elsewhere in the cosmos. The discovery of extraterrestrial life would be nothing short of revolutionary, transforming our understanding of biology, the origins of life, and our place in the universe. Finding even the simplest microbial life forms would suggest that life is not unique to Earth's specific conditions. It could mean that life might be more common throughout the cosmos than we have ever imagined. Such a discovery would require a fundamental shift in our thinking about what constitutes a habitable environment, expanding the range of conditions in which life might thrive. It would also ignite profound philosophical, cultural, and theological debates. If life exists beyond Earth, what does that mean for humanity's role in the universe? What responsibilities do we have toward other forms of life? These questions would spark reflection, deepening our understanding of ourselves and our place in the cosmos. The impact of discovering life beyond Earth would likely ripple through society in ways we can't yet fully predict. Much like the space race in the mid-20th century, the search for extraterrestrial life could drive significant technological advancements. New innovations in space exploration technologies could lead to breakthroughs in materials science, communication, data analysis, and more, benefits that could be applied here on Earth. Ultimately, finding life beyond Earth would not only change our scientific and technological landscape, but would profoundly reshape our worldview, sparking a new era of exploration, discovery, tech, and understanding. In their search for biosignatures on exoplanets, scientists employ groundbreaking strategies, utilizing state-of-the-art technology and a profound understanding of what constitutes life. Central to this pursuit is the deployment of powerful space telescopes, each equipped with sophisticated instruments capable of analyzing light emitted by distant stars and the planets that orbit them. The James Webb Space Telescope, for example, was specifically designed to detect chemical signatures in the atmospheres of exoplanets by analyzing the light passing through them during a transit. By carefully studying the absorption lines in the light spectrum, scientists can identify crucial molecules such as oxygen, methane, and water vapor, compounds that are often associated with biological activity. The significance of this is immense. These molecular signatures could point to the presence of life, potentially signaling biological processes taking place far beyond our solar system. But Webb is just one part of a larger network of advanced technologies dedicated to uncovering these distant signs of life. The European Space Agency's Ariel, Atmospheric Remote Sensing Infrared Exoplanet Large Survey mission, for example, aims to survey a wide variety of exoplanetary atmospheres. This ambitious project will further expand our understanding of the conditions that might support life on other worlds. In addition to these space-based missions, scientists also use direct imaging, an innovative technique that blocks out the blinding light of a planet's host star. This allows the faint light reflected off the exoplanet to be studied in detail. This method is capable of revealing surface features and atmospheric compositions, making it possible to detect potential biosignatures like chlorophyll or other pigments associated with photosynthesis, a key indicator of life on Earth. On Earth, observatories like the Extremely Large Telescope, ELT, under construction in Chile, will complement these space-based efforts. The ELT will offer high-resolution imaging and spectroscopy capabilities, enabling detailed studies of exoplanetary atmospheres and surfaces. This will allow astronomers to search for anomalies, such as unexpected gas abundances or unique surface colors, that could point to the existence of biological activity. These tools are instrumental in the ongoing quest to detect life, as scientists systematically scan the galaxy for the subtle signs of life across distant and diverse exoplanetary environments. Meanwhile, the prospect of human colonization of Mars, an endeavor that continues to captivate the imagination, presents both significant challenges and exhilarating opportunities. Mars stands as the most viable target for human settlement, thanks to its proximity to Earth and its intriguing potential to support human life. NASA, SpaceX, and other organizations are vigorously developing technology and strategies that could pave the way for sustainable human presence on the Red Planet. NASA's Artemis program, which aims to return humans to the Moon, is considered a critical stepping stone toward Mars. The idea is to test key technologies on the Moon before implementing them on Mars, allowing scientists to fine-tune systems for interplanetary travel and habitation. SpaceX, led by Elon Musk, is at the forefront of this effort with the Starship, a spacecraft designed to transport both humans and cargo to Mars. Musk's ambitious goal is to create a self-sustaining colony on Mars, one that could eventually thrive without constant resupply missions from Earth. A central concept in this vision is in situ resource utilization, ISRU, the idea of harnessing local Martian resources to create water, oxygen, and building materials. Mars's atmosphere, though thin, is rich in carbon dioxide, which can be processed to produce oxygen through electrolysis. Additionally, the planet's regolith, its surface layer of soil, could provide essential materials for constructing habitats, allowing humans to build shelter and survive without relying entirely on imports from Earth. These technological innovations are key to ensuring that Mars becomes a feasible home for humanity. In this ever-expanding realm of exploration, both the search for alien life and the ambition to colonize new worlds highlight the incredible potential of human ingenuity. Whether we're studying distant exoplanets or preparing to live on Mars, the scientific and technological strides being made today will shape the future of space exploration for generations to come. However, immense challenges remain, including radiation protection, as Mars lacks the magnetic field and thick atmosphere required to shield its surface from the deadly cosmic rays and solar radiation that flood space. Without these natural barriers, astronauts would face unprecedented risks, making their psychological and physiological well-being a central concern during long-duration missions both on Mars and en route. Addressing this challenge is critical as we continue to push the boundaries of human exploration beyond Earth. Moreover, developing sustainable life support systems, reliable communication networks, and food production methods is paramount to the success of any Martian colony. These advancements are not just theoretical. Extensive research on Earth is already underway, utilizing closed-loop systems to simulate the conditions of space. One key example of this is the high seas habitat in Hawaii, an analog environment designed to test life support systems and solve the very challenges astronauts will face when living on Mars. Through these simulations, researchers are testing everything from air purification to resource recycling to ensure that humans can thrive on the Red Planet. While these technological and logistical hurdles are daunting, the progress made in recent years is fueling a growing optimism. The dream of creating self-sufficient colonies on Mars is no longer just the stuff of science fiction, but a goal driven by a blend of scientific curiosity, technological innovation, and the enduring human spirit of exploration and survival. Space agencies around the world are meticulously developing strategies to address the myriad challenges of long-duration space travel, preparing for missions that will take humanity to Mars and beyond. These efforts represent a monumental step toward making Mars a second home for mankind. One of the most pressing concerns in space exploration is the health and well-being of astronauts during extended periods in space. The microgravity environment of space presents significant risks to human health, including muscle atrophy and bone density loss. To mitigate these effects, space agencies like NASA and ESA have designed advanced exercise regimens and specialized equipment, such as resistive exercise devices, that are tailored to maintain astronauts' physical health while in space. Research on artificial gravity, including rotating sections of spacecraft, is also being explored as a potential long-term solution to combat the harmful effects of weightlessness. But radiation exposure remains one of the biggest obstacles. Space travelers face heightened levels of cosmic rays and solar radiation once they leave Earth's protective magnetosphere. To safeguard astronauts, spacecraft shielding is constantly being improved. Agencies like NASA are investigating innovative materials such as water and polyethylene shielding, alongside pioneering concepts like magnetic fields that could create protective force fields around spacecraft. These advancements will be crucial for ensuring astronauts are not harmed by radiation during their journey to Mars. In addition to physical health concerns, providing medical care during deep space missions is a top priority. With the vast distances involved, astronauts may be millions of kilometers from Earth, making timely medical intervention a complex challenge. Advanced technologies like telemedicine and compact medical kits capable of handling a wide range of health issues are critical to ensuring that astronauts remain healthy throughout their mission. However, these systems need to be continuously improved to address the unpredictable nature of space travel. Equally vital is the mental resilience of astronauts. Long space missions can lead to feelings of isolation, confinement, and stress. To combat this, agencies are incorporating psychological training before the mission and designing spacecraft interiors to enhance crew comfort. In-flight support systems, including virtual reality experiences that replicate aspects of Earth's environments, aim to alleviate feelings of isolation. Moreover, the development of autonomous systems and artificial intelligence aboard spacecraft will allow crews to operate independently when communication delays, often inevitable on such long journeys, make real-time contact with mission control impossible. Through these technological advancements, rigorous training programs, and innovative research, space agencies are shaping a multifaceted approach to tackling the complexities of long-duration space travel. These efforts are laying the groundwork for humanity's exploration of the final frontier, making it possible for astronauts to live and work on Mars. Private companies like SpaceX are also playing an increasingly pivotal role in the future of space exploration. SpaceX, in particular, has revolutionized the space industry with its innovative technologies, cost-effective solutions, and ambitious goals. Historically, space exploration was dominated by government agencies like NASA, Roscosmos, and ESA. However, the entry of private companies has ushered in a new era of commercial spaceflight, marked by rapid advancements and dramatically reduced costs. SpaceX, for example, has made significant strides in developing reusable rocket technology, particularly with the Falcon 9 rocket, which can return and land after delivering its payload. This breakthrough has drastically reduced the cost of launching payloads into space, enabling more frequent and economical missions. SpaceX's achievements have not only expanded the potential for space exploration, but have also ignited new possibilities for humanity's future beyond Earth. As private companies continue to push the envelope, they are creating new opportunities for the development of Martian colonies, making it increasingly plausible that humans will one day live on Mars. This collaboration between government agencies and private innovators is forging a path toward a future where space exploration and the colonization of other planets become a reality. One of the most transformative contributions of SpaceX and other private companies is their pivotal role in facilitating missions to the International Space Station, ISS, and beyond. Through groundbreaking partnerships and technological advancements, these companies are reshaping the future of space exploration. SpaceX, in particular, has emerged as a key player in the new era of commercial space ventures, with its Dragon spacecraft serving as a crucial lifeline for NASA's ongoing missions. Dragon is not just transporting supplies, it's carrying astronauts, enabling NASA to focus its resources on the bold ambitions of deep space exploration, including missions to Mars and the Moon. This collaboration between the private sector and NASA is not merely about fulfilling logistical needs. It represents a seismic shift in the landscape of space exploration. SpaceX's partnership under NASA's Commercial Crew Program helps alleviate the financial and operational burden on the agency while propelling humanity closer to its dream of reaching distant planets. The Dragon spacecraft has become synonymous with efficient, reliable space travel, key to sustaining the ISS and paving the way for more complex missions. But the story doesn't end there. SpaceX's audacious Starship project aims to push the boundaries even further, designing a fully reusable spacecraft capable of ferrying humans to Mars. This monumental ambition is not just about exploring a neighboring planet, it's about making interplanetary travel a reality. With Starship, SpaceX envisions a future where humans are no longer confined to Earth, but are able to live, work, and thrive on distant planets, particularly Mars. This aligns perfectly with long-term goals of planetary colonization, setting the stage for humanity to become a truly interplanetary species. As we look toward the future, the involvement of private companies is not just accelerating the pace of space exploration, it is revitalizing the entire space industry. SpaceX is just one example of how private enterprise is spurring innovation across the sector. Initiatives like Starlink, which aims to provide global satellite internet coverage, and Blue Origin's efforts to develop space tourism and lunar landers demonstrate a rapidly diversifying space economy. This competitive yet collaborative spirit is breathing new life into the space industry, ensuring that the vision of space exploration is no longer solely in the hands of governmental agencies, but shared with the broader global community. The involvement of companies like SpaceX, Blue Origin, and Virgin Galactic is making space exploration more accessible and inviting than ever before. Space tourism, in particular, is poised to become one of the most exciting and rapidly growing industries of the coming decades. Initial ventures into space tourism have already begun, with companies offering suborbital flights that allow participants to experience weightlessness and breathtaking views of Earth from the edge of space. Virgin Galactic, for instance, has designed a spacecraft that provides a brief but awe-inspiring moment of weightlessness, offering passengers a taste of what it's like to be among the stars. Blue Origin's New Shepard rocket is another example, offering a fully automated suborbital flight that reaches the Kármán line, the recognized boundary of space. But the future of space tourism promises to be far more ambitious. While these early suborbital flights are a thrilling preview, the industry is preparing for a leap toward orbital tourism. Imagine staying in space hotels, living and working in microgravity, conducting scientific experiments, and gazing down at Earth from orbit. Companies like Axiom Space are already planning to establish commercial modules on the International Space Station, which may eventually evolve into independent space stations. These ventures are only the beginning, as more advanced and larger-scale space habitats are being envisioned, offering humans extended stays in space for recreation, research, and even work. As technological advancements continue and the costs of launching and sustaining human presence in space decrease, we are likely to see even more extraordinary developments. Space tourism could eventually extend beyond orbital flights to include trips to the Moon or even Mars. SpaceX's Starship, with its capacity to transport large numbers of people and cargo, could one day take tourists on circumlunar missions, offering a once-in-a-lifetime experience of orbiting the Moon. In the more distant future, lunar and Martian colonies might become the new frontier for tourism, allowing travelers to explore alien landscapes and contribute to the pioneering efforts of space colonization. This rapid evolution in space tourism will not only expand humanity's reach into the cosmos, but also fuel incredible technological innovations. Advances in life support systems, habitat construction, and in-situ resource utilization ISRU will make such journeys safer, more efficient, and sustainable. As private companies continue to develop new technologies and drive competition in the industry, the dream of living among the stars will no longer be a far-off fantasy, but an achievable reality. Ultimately, the growth of space tourism will serve as a catalyst for global interest in space exploration. As more people experience the wonders of space firsthand, the desire to push the boundaries of human exploration will only grow stronger. With each new mission, every technological breakthrough, and each step toward colonizing other worlds, we are drawing closer to a future where humanity isn't just a single-planet species, but a truly interplanetary one. As we venture beyond Earth, the possibilities are endless, and the next chapter of space exploration is waiting to be written. Asteroid mining stands as a groundbreaking frontier in humanity's quest to become a multiplanetary species, offering the tantalizing promise of a future where the resources of the cosmos are within our reach. However, this bold vision is not without its complexities and challenges, making it a subject of intense debate. On the one hand, asteroid mining could provide essential resources that are increasingly scarce on Earth, potentially revolutionizing industries across the globe. On the other, the technical, economic, legal, and environmental hurdles present serious concerns that cannot be ignored. The potential benefits of asteroid mining are vast. Asteroids floating in the vast expanse of our solar system are rich in valuable resources, metals such as iron, nickel, and cobalt, alongside precious metals like platinum and gold. These materials are crucial to industries on Earth, particularly in electronics and renewable energy technologies. For example, the rise of electric vehicles, solar panels, and advanced electronics hinges on the availability of such rare and precious metals. By mining asteroids, humanity could secure a consistent and abundant supply of these materials, alleviating the pressure on Earth's dwindling resources. Asteroid mining also promises to help mitigate the environmental degradation caused by terrestrial mining operations. Extracting these resources from space would reduce the destructive impact of mining on our ecosystems, particularly in areas that are already overexploited. But that's not all. Certain asteroids are known to contain water, a vital resource that could be broken down into hydrogen and oxygen. This process could produce fuel for deep space missions, offering a more sustainable and cost-effective means of exploring the solar system. As we venture farther into space, having a reliable source of fuel in orbit could greatly enhance our ability to explore distant planets and moons. Moreover, asteroid mining could catalyze a new era of economic growth and technological innovation. The development of mining technologies for use in the harsh environment of space would likely push the boundaries of engineering, fostering advancements in robotics, artificial intelligence, and material science. These innovations would not only benefit space exploration, but could also lead to breakthroughs on Earth. The commercial viability of asteroid mining has the potential to create new markets, jobs, and industries, fueling a new economy that is based in space. This could pave the way for a space-based economy, one that thrives on the utilization of off-world resources and fosters continued exploration. Beyond economic growth, asteroid mining could strengthen national security. By securing a steady supply of critical raw materials, countries could reduce their dependence on geopolitically sensitive terrestrial sources, thus insulating themselves from supply chain disruptions caused by global conflicts. This could provide nations with greater economic stability, ensuring that essential resources are available even in times of geopolitical turmoil. However, these promises come with significant risks and challenges. The technical and logistical obstacles of asteroid mining are immense. Identifying the right asteroids, reaching them, and establishing efficient methods for extracting and processing their resources present a host of difficulties. The extreme conditions of space, extreme temperatures, radiation, and the challenges of operating in microgravity make mining operations far more complicated than anything attempted on Earth. The costs of these missions are astronomical, and the infrastructure required for large-scale mining does not yet exist, creating further uncertainty about the feasibility of these ventures. In addition, the legal and ethical implications of asteroid mining remain unclear. The Outer Space Treaty of 1967, the primary international agreement governing space activities, provides little clarity on the ownership and exploitation of extraterrestrial resources. This ambiguity could lead to disputes between nations and private entities over the rights to space resources. The potential for conflict is compounded by concerns about the environmental impact of mining activities. Disrupting celestial bodies and accumulating space debris could have far-reaching consequences, potentially threatening the integrity of Earth's orbital environment and hindering future space missions. Despite these challenges, asteroid mining offers the potential to revolutionize resource acquisition and drive technological and economic progress. To realize these benefits, however, careful consideration must be given to the technical, economic, and ethical challenges involved. It will require international collaboration to create a framework that balances the promise of space resource utilization with the responsibility to preserve the space environment for future generations. The complexities of space exploration are too great for any one nation to handle alone. By pooling resources, sharing risks, and working together, nations can tackle the immense challenges of asteroid mining and unlock the full potential of space. The future of humanity's place in the cosmos depends on our ability to work together to turn this vision into reality. In the vast expanse of space, collaboration between nations is not just a matter of convenience. It is the key to exploring the unknown and expanding human knowledge. The International Space Station, ISS, stands as a shining example of such collaboration, a testament to the power of international partnerships in advancing scientific discovery. Built through the combined efforts of the United States, Russia, Japan, Canada, and the European Space Agency, ESA, the ISS has become a symbol of unity in the pursuit of space exploration. Orbiting Earth as a floating laboratory, it enables research that benefits all of humanity, pushing the boundaries of science in ways that would be impossible for any single nation to achieve alone. Beyond the ISS, collaborative efforts in space exploration continue to yield groundbreaking discoveries. Take the James Webb Space Telescope, JWST, for example, a joint project developed by NASA, the European Space Agency, ESA, and the Canadian Space Agency. This ambitious telescope is designed to peer deeper into the universe than ever before, capturing images of the earliest galaxies and stars that formed after the Big Bang. The combined expertise and resources of these space agencies are vital to the success of such an ambitious mission, highlighting how shared efforts can lead to profound scientific advancements that benefit all of humankind. In addition to telescopes and space stations, international partnerships extend to planetary exploration, exemplified by missions like ExoMars. This joint venture between the European Space Agency, ESA, and Russia's Roscosmos is dedicated to searching for signs of life on Mars, one of the most intriguing and challenging goals in space exploration. Such missions benefit from the diverse expertise and unique perspectives that each nation brings, whether in the form of advanced technology, scientific knowledge, or problem-solving approaches. This pooling of resources and intellectual capital results in more thorough planning, more accurate data analysis, and better solutions to the myriad challenges that arise in space exploration. Moreover, international collaborations foster geopolitical goodwill and trust. The cooperation required for joint space missions can serve as a powerful diplomatic tool, easing tensions between countries. When nations come together to explore space, they not only share in the excitement of discovery, but also demonstrate a commitment to peace and cooperation. Space becomes a shared domain, one where the achievements and benefits of exploration are accessible to all, transcending borders and promoting global harmony. The Artemis Accords, led by NASA, embody this spirit of international cooperation in space. These agreements establish a framework for the sustainable and peaceful exploration of the Moon, focusing on transparency, the peaceful use of lunar resources, and international collaboration. The Accords promote the idea that space exploration should be a cooperative endeavor that benefits everyone, ensuring that future generations can continue to explore the Moon, Mars, and beyond with a spirit of unity and shared purpose. However, despite the many advantages, international collaboration in space is not without its challenges. Differing national priorities, regulations, and policies can create complex negotiation processes requiring careful coordination and management. Intellectual property rights, data sharing, and the distribution of roles and responsibilities are just a few of the issues that must be carefully managed. Yet, these challenges do not overshadow the immense benefits that such collaborations bring. By working together, nations can achieve far more than they could individually, pushing the boundaries of human knowledge and ensuring that the exploration of space is conducted in a way that benefits all of humanity. Space exploration continues to inspire as meteor showers light up the night sky with their dazzling displays of shooting stars. These celestial events are more than just beautiful spectacles. They serve as a reminder of the cosmic wonders that lie beyond our planet. Meteor showers, such as the Perseids, are among the most famous and reliable annual events, known for their bright, fast meteors and high activity rates. Every August, stargazers are treated to a stunning display with up to 60 meteors per hour at their peak. The Perseids originate from the debris left behind by Comet Swift-Tuttle, a cosmic trail that has enchanted observers for centuries. As the meteors streak across the sky, some even produce fireballs, exceptionally bright meteors that stand out against the brilliance of the others. Another notable meteor shower is the Geminids, which graces the December skies. Unlike many other meteor showers that are linked to comets, the Geminids are associated with a rocky asteroid named 3200 Phaethon. This shower is unique in that its meteors move slowly across the sky and can appear in a variety of colors, including hues of yellow, blue, and green. At its peak, the Geminids can produce over 100 meteors per hour, making it one of the most prolific and reliable meteor showers. Those brave enough to venture out into the chilly winter nights are rewarded with a dazzling celestial display that lights up the night sky. Meteor showers occur when Earth passes through streams of cosmic debris left behind by comets or asteroids. As these small particles, often no bigger than grains of sand, enter Earth's atmosphere at high speeds, they vaporize due to friction with the atmospheric gases, creating the brilliant streaks of light we call meteors. Each meteor shower is named after the constellation from which the meteors appear to radiate, known as the radiant point. For example, the Perseids appear to radiate from the constellation Perseus, while the Geminids seem to radiate from Gemini. The regularity and predictability of meteor showers are due to Earth's annual passage through the debris trails left by their parent objects, which maintain their orbits around the Sun. This cosmic choreography ensures that year after year, meteor showers continue to captivate and inspire, providing a dependable and awe-inspiring spectacle that connects us to the vast and ever-changing universe beyond our planet. Auroras, also known as the Northern and Southern Lights, are one of the most mesmerizing natural phenomena observed in Earth's polar regions. These stunning light displays are a beautiful reminder of the dynamic interplay between our planet and the Sun. Occurring when charged particles, mainly electrons and protons, emitted by the Sun interact with Earth's magnetic field and atmosphere, auroras captivate both the curious and the scientifically inclined. The Sun constantly releases a stream of charged particles called solar wind, which upon reaching Earth interacts with the planet's magnetosphere. While most of the particles are deflected by the magnetosphere, some are funneled towards the polar regions where the magnetic field lines converge. At altitudes between 60 and 300 miles, these charged particles collide with the gases in Earth's upper atmosphere, mainly oxygen and nitrogen, exciting their atoms and causing them to emit light as they return to their ground state. This stunning visual display is what we know as auroras. The colors of auroras depend on the type of gas and its altitude. Oxygen, for instance, can produce green or red light, with green being more common at lower altitudes between 60 and 150 miles, and red appearing at higher altitudes above 150 miles. Nitrogen, on the other hand, emits a bluish or purplish red light. The intensity and occurrence of auroras are also influenced by solar activity, such as solar flares and coronal mass ejections, CMEs, which can send even more charged particles into Earth's magnetosphere. During periods of heightened solar activity, auroras are more frequent, and their displays can be seen at lower latitudes, providing a dazzling spectacle in regions like Scandinavia, Canada, Alaska, and Antarctica. The dynamic nature of auroras, which can appear as gently waving curtains, spirals, or explosive bursts of light, reminds us of the intricate relationship between the Sun and Earth. These breathtaking phenomena serve as a cosmic reminder of the forces shaping our solar system, inspiring both wonder and scientific inquiry. The unpredictability of auroras coupled with their beauty continues to captivate observers, making them a truly awe-inspiring natural light show. But auroras are not the only cosmic phenomena that spark curiosity. Eclipses and transits, other spectacular celestial events, have long drawn the gaze of both amateur stargazers and seasoned astronomers. A solar eclipse, for example, occurs when the moon passes between the Earth and the Sun, casting a shadow on our planet. These eclipses come in different types: total, partial, and annular. A total solar eclipse, in which the moon completely covers the sun, is a rare and breathtaking occurrence, plunging the daytime into darkness and revealing the sun's ethereal corona. These moments of total solar obscuration present unique opportunities for scientific study, especially regarding solar atmospherics, which help to advance our understanding of solar phenomena. In contrast, lunar eclipses occur when Earth comes between the sun and the moon, casting its shadow onto the lunar surface. Unlike solar eclipses, lunar eclipses are visible from anywhere on the nighttime side of the Earth and can last for several hours. The sight of a total lunar eclipse, or blood moon, is particularly striking, as the moon takes on a deep red hue caused by the scattering of sunlight through Earth's atmosphere, a process known as Rayleigh scattering. Lunar eclipses are not only captivating, but provide valuable insights into the moon's environment and surface composition. They offer both astronomers and the public an opportunity to witness a celestial event that has fascinated humans for millennia. Likewise, planetary transits, when a planet passes directly between the Earth and the Sun, are rare yet highly significant astronomical events. The transits of Mercury and Venus, for example, present a remarkable spectacle, as the planet appears as a small dark disk moving across the face of the Sun. These transits are rare, with Mercury transits occurring about 13 to 14 times per century, while Venus transits happen in pairs separated by more than a century. Aside from their visual appeal, transits are scientifically valuable as they help refine our understanding of planetary orbits and have played pivotal roles in measuring astronomical units and calibrating distances in the solar system. In addition to transits, conjunctions, when two celestial bodies appear very close to one another in the sky, also captivate stargazers. The Great Conjunction of Jupiter and Saturn, which occurs roughly every 2 decades, is especially noteworthy. During this event, the two planets align closely, providing a beautiful and symbolic display in the night sky. Each of these cosmic events, whether it's the mesmerizing auroras, the captivating eclipses, or the rare transits and conjunctions, offers not only spectacular visual experiences, but also critical opportunities for scientific research. They deepen our understanding of the vast universe in which we live, and their beauty and mystery continue to inspire awe across the globe. They enable astronomers to gather crucial data on celestial mechanics, atmospheric dynamics, and the solar and planetary characteristics that shape our universe. Bridging the gap between the curious observer and the scientist, these observations unite humanity in a shared quest for understanding the cosmos. Gamma-ray bursts, GRBs, along with other high-energy phenomena, have profoundly reshaped our comprehension of the universe, revealing the intricate and often violent dynamics behind some of the most powerful and catastrophic events in cosmic history. Gamma-ray bursts are intense flashes of gamma radiation, the most energetic form of light, lasting from mere milliseconds to several minutes. These bursts are generally classified into 2 main types: short-duration GRBs, which last less than 2 seconds and are believed to result from the merger of neutron stars, and long-duration GRBs, which typically last longer and are linked to the collapse of massive stars that form black holes. These fleeting but intensely powerful events offer scientists a unique window into the most extreme conditions in the universe. The study of gamma-ray bursts has provided significant revelations about stellar death, black hole formation, and the behavior of matter under such extreme circumstances. In fact, these bursts release more energy in a few seconds than the sun will emit over its entire 10 billion year lifetime. This immense burst of energy offers an unparalleled natural laboratory for studying relativistic physics, particularly the mechanics of jet formation and propagation. As these gamma-ray bursts often originate from highly relativistic jets, streams of particles moving at speeds approaching the speed of light, Astronomers can examine their afterglows across various wavelengths, from X-rays to optical and radio waves. This broad spectrum of observation allows scientists to probe the environment surrounding the burst, uncovering vital details about the interstellar medium and even the host galaxy itself. Other high-energy phenomena, such as supernovae and active galactic nuclei, AGN, also play critical roles in enhancing our cosmic understanding. Supernovae, the explosive deaths of massive stars, are responsible not only for distributing heavy elements throughout the universe, enriching the interstellar medium, but also for serving as powerful cosmic distance markers. The study of Type 1 supernova has been instrumental in measuring these distances and, in turn, led to the groundbreaking discovery of the universe's accelerating expansion, a revelation attributed to the mysterious force known as dark energy. This discovery has profoundly impacted modern cosmological models and deepened the enigma surrounding the nature of dark energy, posing critical questions about the ultimate fate of the universe. Active galactic nuclei, powered by supermassive black holes at the centers of galaxies, emit enormous quantities of high-energy radiation as they accrete matter. Observing AGNs has expanded our understanding of black hole growth, galaxy evolution, and the complex relationship between central black holes and their host galaxies. By examining AGNs across the electromagnetic spectrum, including gamma rays, X-rays, and radio waves, scientists have been able to uncover key processes such as the dynamics of accretion disks, the formation of relativistic jets, and the feedback mechanisms that regulate star formation in galaxies. The ongoing investigation into gamma-ray bursts and other high-energy phenomena continues to provide invaluable insights into the universe's most energetic and transformative events. These studies not only shape our understanding of stellar evolution, black hole physics, and galaxy formation, but they also influence the broader field of cosmology. As astronomers continue to push the boundaries of astrophysics, they are uncovering the fundamental processes that govern the universe, leading to new discoveries and shaping the future of both observational and theoretical research in the field.